start the first panel. Thanks. Let's go ahead and start the first panel discussion. If Jen, David, and Victor would come down, that would be great. Wheelchairs, yes. As I said, David Bauman is the lead for HRP. Victor Glover has been an active member of the planning committee through this past 9 months. And Jen Fogarty is with Trish, and so that'll be interesting. And David is first.
Sure. Yeah, if you could pull up the charts. All right, good morning, everyone. I really appreciate the invitation from IAASS and our hosts at OSU. It's really great to be here and hear the progress that y'all have made on the HRP-C and to be able to share some of the lessons learned that we've had going forward. So you can go to the next slide. Before I get started, and I am going to go through these charts fairly quickly so you have plenty of opportunity to talk with Victor Glover. I do want to highlight that this is a very important week for us at NASA. Tomorrow's our day of remembrance, where we remember the crews of Apollo 1, Challenger, and Columbia, and the lessons learned from those missions. To highlight some of those lessons, coming out of the Columbia disaster was the standing up of our new governance system at NASA, which included the Health and Medical Tech Authority that you heard about from Dr. Polk yesterday. It was also the catalyst for the Bush vision for space exploration, and out of that came the mandate for a very applied human research program, which is the HRP that we have today. So it's very fitting that as we talk about protecting the crew health and performance of deep space, that remember the crew members that got us to this point today. So we can go to the next slide. Or I'm sorry, I have the clicker. So our vision that we set up a few years ago for the commercial human research program or research would be that every human that goes to low Earth orbit is offered a chance to participate in research that will further NASA's exploration goals. And I would say at this point it's just a vision. With our friends at Trish, we have actually made that a reality, that every mission that has flown, all the commercial missions that have gone to space, have been offered opportunities to participate in NASA-sponsored or Trish-sponsored research. The mission of HRP, it's a very applied research program, solely looking at reducing the human health and performance risks for exploration missions. You heard about this yesterday. If you look at the human health and performance risks for a lunar mission, as Dr. Polk mentioned, this isn't mean that it's a no-go for a lunar mission where you see some red, but this is what we use as a priority scheme to focus our research both for the moon and for Mars. I do want to clarify one thing though. HRP does not set these priorities. As I mentioned, we have a new governance model after the Columbia with the Health and Medical Tech Authority. So we really look to Dr. Polk and his HMTA to set these priorities. As a program director, it's my job to reduce all of these risks. So it would really kind of be a conflict of interest if I was grading my own work. So as Dr. Polk being our customer along with the crew office, they're the ones that set the colors for this, and we respond to those priorities with our research plans. And that might be something you consider as you stand up your own HSRB for HRP-C. So the way we reduce these risks is through work in the Earth on ground analogs such as bed rests, isolation confinement, radiation accelerators. Then where appropriate, we move work to the International Space Station. But now we have new commercial space that we're working with closely and using those opportunities. And we look forward to the commercial LEO destinations coming to take the place of the ISS in low Earth orbit. Then we'll move research to the lunar missions to prepare for Mars. And really, other than demonstrating our capabilities in those missions and showing and demonstrating them for a Mars mission, we're just trying to answer, is lunar gravity closer to 0G or 1G? So we can tune our models and better predict what we're going to need on a Mars mission. To go back to the tenets that Dr. Polk laid out yesterday, how do we better tune our crew health and performance system for mass, power, volume, and et cetera? We do have a lot of work. I should mention, that much like the HRP-C, we have a track when we do standard measures on all these platforms. We do hypothesis-driven research, and we have the infrastructure in place to support all these different opportunities. We do have a lot of work to do yet in low Earth orbit. We have countermeasure development. You can see a crew member, or this is a simulated crew member, that as soon as they come down from their long duration missions, we put them in EVA suits, an offloaded EVA suit, to demonstrate what capabilities they have so we can answer the question, when you get to Mars, how soon can the astronauts get out and perform EVA tasks? We're standing up our Cypher. We have our first 2 crew members on orbit right now. This is the most integrated and complex human life science experiment ever performed in low Earth orbit. We've flown about 650 people to low Earth orbit, but I can pretty much confidently say no 2 of those astronauts have ever had the same complement of research. So we don't know systematically how bone, muscle, psychology, all of those interact. So as we talk about personalized medicine today, this will help provide some of those data to help understand the full human body system. We do autonomous medical capabilities, understanding that as we move forward further and further, we'll need more autonomy and Earth-independent operations. And we've also stood up our own omics archive to start looking at that next generation of research. I'm not going to go through all of these, but one of the ways we reduce human health and performance risks is by delivering capabilities for Mars. And the reason I put this up here, and I can talk about any of your favorite one later with you if you're interested, but one of our approaches for commercial spaceflight is to work very closely with the providers, understand what their business models are, what their motivations are, so we can better align to see where there are collaborations. And there are a few of our commercial space providers that have the stated objective of going to Mars. So the Venn diagram between what our research program is and what their research program is pretty overlapping. So these are some of the things that we discuss with them and how that we work collaboratively together on commercial human research. As I've mentioned, it's more than just a vision we have. We've actually set the precedent along with the hard work from Trish, namely Emmanuel Urqueta, who's in the audience today, and Jimmy Wu. They really do a lot of this. But HRP is also working closely that if you're going to space, you'll be offered human research that better furthers our risk reduction goals for exploration missions. And I believe Dr. Fogarty will talk more about that. And then we look forward to the next generation of commercial spaceflight. So with the commercial LEO destination providers that we have agreements with, we've already started speaking with them. What are their research goals? They already have commercial human research programs at all of the different providers. So understanding what their goals are, where we can work together, understanding there's a lot of opportunities. It's not just going to be passengers, it's going to be people actually working on these space stations, and how can we align our goals so that we're furthering NASA's exploration risk reduction activities. I just want to give a plug for our investigator workshop. For those of you that aren't familiar with this, I'm biased, but I believe it is the world's premier human life science spaceflight workshop. It's free admission. It's in Galveston next month. So you can just Google HRP IWS 2024 and register for that. It's not just a report out. We actually have a focus on commercial space where we have a commercial panel, the providers there, along with our international partners as well. So just to summarize, our main focus at NASA HRP is to reduce risk for our deep space travelers. We work very closely with our commercial entities that are stood up, and we have programs in place to utilize those capabilities, and we look forward to those increasing that going forward. So with that, feel free to follow us on your favorite social media site, and I'm around. And again, feel free to reach out to me and figure out how we can collaborate going forward. So with that, thank you for your support today, and I'll turn it over to Dr. Fogarty.
Hi, good morning. Thank you, David. That was great, and you set the bar pretty high for brevity, which I'm not known for. So yes, Jen Fogarty from the Translational Research Institute for Space Health. I'm just about at my anniversary of 24 years in the space business. And the Day of Remembrance for me is very poignant because I was there at the landing site when Columbia 107 didn't return. I was part of a group doing research, living and working out at Kennedy Space Center. And a young postdoc was lucky enough to be a lab manager and running some work for Dr. Mike Delp. And it was a stunning revelation. Obviously, I knew about past experiences, witnessed Challenger on TV as a child, but there is nothing like that type of experience to really ingrain the altruism that goes into these efforts. And now we're expanding that to people who normally traditionally wouldn't get to fly. And to one of my colleagues, we've talked a lot about the risk, but we also have to discuss the beneficence, the benefits of doing this. And we had an ethics workshop last year where a significant part of the discussion was about the importance of the beneficence and talking to commercial space flyers.
It's been more extensive than what is done at the mic online for those who are familiar with the law. Because typically when we do
the beneficence of doing these things, and they are hard to predict. And I think as scientists, we get wrapped up in the business model a lot, like the ROI, immediate ROI. What is this going to give us back in the next 1 year, 2 year, 5 years? And as we experienced in the pandemic, it doesn't work like that. And when you're under pressure to deliver results and answers, and then you have to change, the information because you've learned more, the hazards of trying to overcome the original information you came, and then the distrust. So, a little intellectual honesty when you're talking about doing discovery, the importance is allowing yourself to learn. And when the discussion came up, from Mr. Bridenstine about informed consent. We do informed consent now, not just for the research, but the idea of flying people in space to the best of our abilities. We know our colleagues at the commercial space, companies, and the deal is we have to be honest with people. There's stuff we don't know. So that's the uninformed, informed consent. That happens in medicine today, but we do our very best, and we are obligated to continue to do the research to refine that information to, again, 6 months, 12 months, 5 years from now, give you a better perspective on what those risks are. And we also have the capability to be more precise. So what does TRISH do? TRISH is a complementary program or a cooperative agreement that's funded by NASA. So we have the same risk model, everything you saw, the infrastructure from the HSRB, those are our guiding tenets of what are the priorities, what are the high risks, and what do we focus on. But TRISH is the opportunity to do higher risk research, right? We can go out and kind of stretch the limits of what we believe will return an investment back. We want high throughput. We want to know real zeros, things that absolutely don't work, so we can move on, and we want real ones. But when I think about spaceflight, and going back to, just another disclosure, for 4 years I was the chief scientist for the NASA Human Research Program. So I kind of know them from the inside, and now I'm learning them from the outside. But I was also an ops person for 12 years and worked with medical operations. And it was like the concept of a con ops is essential. Where are we all trying to get to? What are we all trying to achieve? And how do we back ourselves out of that? And if your hair is on fire about everything all at the same time, it's really hard to manage what needs to come first. So you do the typical thing. Let's break it down. Let's decompose the problems. But at a very high level, when I got to step back as a scientist, I got to reflect and put these pieces of the puzzle that I receive all the time from our investigators and say, what is it telling me? And these are kind of how I break down my thought process. Like, how is the body adapting to these environments over time? And I also want to mention very quickly about intrinsic bias. Not only about who we interact with and how we think about our science, but you will see what you expect to see, right? Even in our own data. Sometimes we got to get someone else in a different perspective to help us really understand what the data is telling us, not what we want it to tell us. How is the adaptation and how will it change the probability of performance and health decrements? And these are hard questions, right? These are not trivial, and they require a lot of data. So I was very happy to see in the HRP-C report the concept of deep phenotyping and using molecular techniques to see deeper than we've ever seen before. But it's going to be a while before you can actually interpret the data with confidence. So you also have to patience is a virtue, and I have little to none of it, but we all as a group have to keep each other in check. And that's what the scientific discourse is about at meetings like this. Where are we in the state of knowledge? What are legitimate ways to extrapolate and interpret the data? And where do we have bigger questions? And maybe someone else has a different data set that we should all know about to help refine our interpretation. How do we monitor and manage health and performance of the crew non-invasively and unobtrusively? This was discussed yesterday quite a bit. We're all on the same page. We're working with technology companies and constantly pushing our requirements to help them understand that concept, that we cannot put people at risk by the monitoring, we cannot interfere with operations with the monitoring. How do we get there? Which is field testing it, which is why analogs are so great and why real life studies in different industries are so great. How do we meet the biological and physiological needs of the crew over the course of the whole mission? Super challenging, right? We're gonna take people from one gravity, whatever their current state of health is, we're putting them into microgravity, which is the complete absence of signal. You know, people go on and on about space radiation, and I'm not attempting to be willfully ignorant, but you will hear things, and I've read it recently, like, you know, a particle is gonna hit a cell and, and do this sort of damage. I mean, the vision it conjures up is really worrisome, but we tend to take for granted the fact that we have developed, and every cell of our body, every molecule, every atom is used to one G pulling on it. When you go to nothing, can you imagine the disruptive process? But it's hard to measure. But I feel like because people have lived and worked very successfully, we really take for granted how big of a hazard the lack of gravity is. And how do we provide agility, flexibility to address events that we were unable to predict? You know, there was a lot of stuff discussed yesterday, especially, and I was hoping Dr. Polk would be in the front because I was going to use him as example A, but he's not even in the room, so I get to do this even without him. So 3D printing, totally get it, understand how it can fit. I understand what a remarkable tool it is, but when you have to bring raw materials with you, when it talked about the pharmaceutical application, the logistics supply chain breaks down pretty quickly. So I'm going to talk a little bit at the end about synthetic biology, which is where you can capitalize on resources that you're going to have with you, and you can send up code, you can send up ways to manipulate DNA that can deliver you products that are probably way more efficient for our application in biology than 3D printing may ever be. It's not to say that it's an or question, right? We got to have solutions that fit the needs in the mission at the time you need them. So we talk about the spectrum of spaceflight going from commercial government sponsored at large facilities like the International Space Station all the way up to the right with Inspiration 4 free flyer, combinations of private astronauts going to the International Space Station and working on a facility and understanding what it's like to be there with an international crew, people who have trained for 10 years to be up there versus someone who was trained for 6 months. It's a very dynamic environment and clearly offering a lot more opportunity than we've ever had to understand humans in space. Remember, the Human Research Program doesn't say astronaut program. They're humans first, and that is the most fundamental thing people need to remember each time. We mentioned that they don't have there's no such thing as perfect health. There's a spectrum of health, and people make lots of choices and have genetic, vulnerabilities or robustness that allow us to understand what their baseline is. But these people are as robust as you can be and as fragile as you can be. It's quite the dichotomy in human biology. So expand. David mentioned this, and Dr. Urquette is up there. I'm almost like, I would have to have him stand at the mic. We're delivering a document so you can understand this in much greater detail. But this was the program put together, sponsored by HRP, to be of service to the commercial spaceflight program because we knew and understood that the diversity of people flying with commercial providers were an amazing resource to understand humans flying in space and how we could do it better. And we have always believed, whether it be HRP, Trish, Expand, and other, that there is always a spin back to Earth. This tells us huge amounts about human biology. Applying it, that's a little trickier and a lot more work, but we are always relevant to what's going on Earth. The Expand database consists of research, and you're gonna see some shadowing or some, I think, mirroring of what I saw in the tracks. I mean, this is just obviously scientists, thinking alike in terms of how we would approach a very complex problem and break it down into workable units. So David had a slide like this as well, we have multiple stakeholders feeding in there, and we'll show a little bit about the complexity of the legal documents that have to be in place to allow us to have this interaction. But Emmanuel, Jimmy, and Baylor College of Medicine Legal, as well as HRP, have worked really hard to understand how do we do this and make everybody feel confident that their data is secure and protected. That also means data from the company, because we needed vehicle data, which is metadata, to interpret the human data that we see when they get the exposures while they're in these vehicles. We have a lot of users on the back end, which meant in the middle, Expand had to have a capability, and we contracted with a company that specializes in clinical trials for NIH. And they were also a company who, I would say, the branding is strong for NASA, there is no doubt about it, and every interaction we have with them, they do go above and beyond. But they were also forced to change their model during COVID that benefits us, because they had to decentralize how they did data acquisition. People were not going into a clinical care facility to get their samples delivered, such as blood and urine, or having their testing. They had to start developing equipment and the capability to get data from people at home to continue clinical trials during COVID. And this company, TrialX, has been an amazing resource to us to understand what the FDA and gold standard practices are for data and medical acquisition, and being able to not only archive it, but make it distributable on the back end. You can shove a lot of electrons into a server and archive things. The real goal is to get it back out the other side and make it usable by other people to analyze. So Emmanuel and the group has also stood up a data privacy and release board, because we need control mechanisms. We need some people in the middle to be, determine what's appropriate in terms of questions coming in. Do we have the right data to actually answer the questions the people are asking? And how does it come out the backside? Because we still want to anonymize these people, protect their privacy, and also make sure that the science is credible. So we have things like research collaboration and data rights agreements and license agreements with the companies, so they understand how and why their data will be collected and used and what data we need from them. There's a lot of requirements. Speak again, you have to be clear about what you're trying to achieve with these archives and what your expectations are of providing analytic capability on the back end for the data that will be used. And then with the investigators themselves, it's important. I mean, these people are, we all have careers where someone else is measuring us and how productive we are, and that's called publications in the world of academia. And they get the first right to publication, and that's their data to work with. But they also know that by sharing their data, their ability to be successful also grows. But they get first rights, and then we figure out how to use it after, and they will always be engaged in other uses of their data, and they may actually have to be involved because they know their data best. So like the tracks that were presented yesterday for HRP-C, we also have the essentials, which is complementary to standard measures, which I knew a little bit about at HRP. And the idea of taking standard measures and making essential measures was streamlining it so it was more appropriate for commercial spaceflight. We had even more constraints in terms of how much access we got to the crew before the mission, how much crew time we have in the mission, what are the capabilities during the mission. So they really had to condense down what we needed to do. We had to do a down select process. And it'll continue to flux, as vehicles and crews get bigger, as commercial spaceflight missions get longer, we can add back content, but we want to keep that continuity of the science so there's always comparability between the people who fly. Benchmarking studies, that's when we could amp up how much, if we get more crew time, we can give you more work. And as was mentioned, these commercial flyers, they want to be of service, and they want to have the experience that's more in line with NASA astronauts, as mentioned to us all the time. Like, oh, we can give you some work. Like there's never a shortage of work to do. Does it fit in the mission? Is the hardware flight certifiable? All those hard questions have to be worked in the logistics of planning for any mission. And then the expeditionary, that's where really we're doing hypothesis-driven work. The tools are more complicated. The science is more complicated. So the requirements on the subjects are more. This is also on the back end, and I will say we've had a little complexity with this, which is when their mission is over, they're like, see ya. I want to go back to my regular life, and I'm with my family, and I can't come in for the blood draw, and we're like, time out. Like, well, we need this stuff. So now we've had to make accommodations, like we're getting blood drawn in other countries, we're getting it processed. Dr. Urqueta, I'm going to throw his name out there a million times today, can't say enough good things about the work he's done, but he's negotiated with academic and laboratory institutions all across the United States, in foreign countries, so that blood can get processed and they know what the protocols are, and it'll get stabilized and sent back to the Human Genome Center at Baylor College of Medicine, and we have a good chain of custody and we know their quality samples and they're all getting checked when they come back. So then again, that gives us a distributed resource where we don't say no. We don't have a loss of science in a subject, we're able to preserve it. But it's complex and you gotta be ready for that. So these are some of the topics, that we go over. I don't want to go into so much the details of how, because I'm out of time. And but I think you see a lot of parallels with what the HRP-C is talking about, because these are the issues. When it comes to human spaceflight, this is the stuff you're going to see, and it's on a spectrum, so it's complicated. But the more data that we get on people, the more likely we are to have a valid and confident interpretation. There is a biobank and an omics analytic capability. We only take the analysis so far, because as soon as we get out a certain analytic techniques, you're really talking about doing processing the samples in a way where you're going toward a targeted answering a question modality. And we want to make sure that we have sample left over to answer targeted questions. We're doing more of the untargeted work up front, so that the data is there at both the DNA and RNA level, but we don't go as far as, say, the proteome and metabolome. So other initiatives that complement expand. So the other part is working in commercial spaceflight. What we realized pretty quickly was we need vehicle agnostic capability. So when I worked at NASA, it was all about vehicle design requirements, and we were always behind the curve. Especially the medical side. So you ended up with a backpack or a Foot Locker size allocation, and they said, make sure you choose wisely what you choose to put in it, but it's finite. We're like, well, this isn't working out for us. Like, how do we get smarter about doing this? So I took that knowledge and experience and the pain that I felt working requirements across the table from engineers and said, how about, and also on Earth, I'm sure you've all experienced this, who actually has their medical record? Like it's everywhere all of the time, and God forbid when you travel, you just don't have it. So if you're conscious and you can give verbal history, that's great, but if you're rolling to an ER unconscious, and we got plenty of ER docs probably in the room, that they don't know what they don't know and they start from scratch. Why is that? Why do we not have access to our medical record, but I can file my taxes online? Why, we ask all these smart questions. Well, we said, given that, we went, and competed. We said what our requirements were, what our goals were, and we competed it. And we said we want to start to build a vehicle agnostic system, because we need a system that can go with the person to different vehicles that are owned by different providers that probably have different medical care groups. And we want to make sure that they are re-baselined every time, so that when they require medical care, we're not dealing with no information or the bad information or whatever happens to be. And if we think we can crack this nut for spaceflight because there's a forcing function, the spin back to Earth will be just amazing. But all the peripherals that were talked about, all that unobtrusive, non-invasive hardware, this is what it has to interface with. How do we get the data to a centralized location? And then how do we distribute the information some level back to the person so that they know they're good, or maybe they need to talk to the doctor, or maybe they need to exercise more or sleep more. We can give some feedback directly and be of value to the individual, but it's got to go to doctors, it's got to go to researchers, it's got to go to the database. So it also had to be distributed. So there was a lot of thought process about the end-to-end utility of a medical data architecture system that was vehicle agnostic and human-centric. I have to add that part. I mentioned synthetic biology, not in detail, but we have, and others, believe it is a heavy, heavy area of investment. But one of the most remarkable things prior to my joining of Trish, but I have just hung on to this product, which is Karen McDonald out at UCSD, is able to synthesize active pharmaceutical ingredient in the leaf of a plant within 18 hours. And right now, the rate limiting factor is extracting it out the back end, and of course you would say quality control and what is the concentration. But we're working with Karen and others to push it to the next step is, by the amount that you inject into the leaf and the DNA instructions that you give it, you may be just able to eat the leaf someday. You would give it as precise of instructions where the plant would be able to deliver you a composite resource that says, there is your antibiotic, there is your anti-inflammatory. And this way, we didn't have to pack the CVS, pharmacy. We were able to be responsive to on-demand need. So it's really groundbreaking. And you may not even have to use plants. People are talking about microbe and yeast and a variety of other resources in very small vials, and flip this stuff around. And then the last one, a little bit was mentioned about how to study humans, but not put the human at risk. So the development, and again, multi-agency investments in this, a lot of maturation, but tissues and organs on a chip. How much does it recapitulate human function? What is it legitimate to answer questions for? So our next step has been to fund work that takes these organs and tissues on a chip that have been shown to be valid and recapitulate function, and we want to automate them so we can send them up into space flight, say on a satellite, and they will also telemeter data back. So it's going to partner organs on a chip with lab on a chip concept, or non-wet lab chemistry analysis techniques that help us understand targeted biomarkers. But we call it Sentinel because the idea is to be able to send these out ahead of people and report back to us what people would be at risk for. And this is also representation of personalized in terms of we can take an individual's cells, and the goal for us in space biology and HRP is to have astronaut cells, private or government, flown with their chips, and then compare what happens to the intact human versus what's happening to the chip, and do our validation that way. And that is a goal for the use of the Artemis program for us. So, at the frontier of science, it can't be more exciting right now, and especially when we have jobs that allow us to apply it for such a lofty goal as human exploration of space. So I know we're all on the same page about that. So we look forward to the collaboration, both with IAASS and also, some of the new folks we're meeting from Oklahoma State and other universities. I was glad to hear the attendance that's online, because the more people that get to know about HRP, TRISH, and HRP-C, they will be able to raise their hand up and say, I'm the person you've been looking for. I have this technique. I have this data set. I'm not looking for a needle in a haystack anymore. We're going to use these tools as a magnet and draw the needle to us. So I'm going to leave you with that image, which I think is amazingly inspiring to think about where we are and the path we're on and what we're enabling today. Whoever she is, I look forward to celebrating the day they land and we get to be back on the moon. Thank you.
Now it's my pleasure to introduce astronaut who will be going to the moon. He's going to be flying around the moon and on Artemis 3. And how do we do this? Oh, please. You're over there hiding. So we're thinking of asking them questions, but would you like to start?
Good morning, and thanks for the invitation to be here. I was initially asked to start off with some remarks, and I couldn't convince Tom Cruise to come with me, so I said let's just do Q&A. But I would love to engage, just as a military officer and a pilot. Being in this environment, right, I'm not a researcher. I also tried to bring Kate Rubins with me, and Mike Barrett is getting ready to launch to the space station. So I tried to get you the people that you really want to hear from. But I also think listening to both sets of comments, something that I talk to our Artemis team a lot about is the fact that curation, this is lunar samples, so, physical sciences, but, the curation of the samples that we return in the Artemis, that begins on the surface. And so you're dealing with people like me, and this applies to our life sciences as well, our human research. You're going to have to train someone like me to be able to get you this data that you need, and then also to be able to implement the optimization. I like that word over risk reduction. That's important too, but when we're really doing well, it's not just feedback, it's feed forward, and we're making the next system safer and better, and so we're optimizing. And you're going to have to work with a lot of people like me. I love the diversity we have in the astronaut corps. And I'm one of the folks that's going to be at the table as we try to reduce the risk of some of these programs. So I don't have prepared remarks. I really thought we'd get the most out of this by a dialogue. And I believe if we're broadcasting online, questions online are okay too. But also, I thought I was going to be joined up here by some of the other folks who did speak this morning, so I hope the two of you are planning on coming back. All the questions that are science, I'll take maybe the easy math, but I'm going to point to them to answer the hard questions. So please, let's get to it. Let's start. So happy to answer questions or dialogue. And is somebody monitoring the online if we have questions? Okay. A lot of good familiar faces in the audience, like the one coming to the mic now. How you doing? Good to see you.
So we've had a lot of discussion yesterday and today about the science and what needs to happen for the science, and some of it eventually can sound like a wish list. Some of it may be possible and some of it may not be. But Victor, from your perspective as an operator and somebody who's been there and somebody who's going to the moon, I'd like to know a little bit about how you give feedback to the scientific community, whether you feel like that feedback gets heard, especially when you're doing experiments up on the ISS, and then the reality of trying to implement the science. There's, I think, a lot of aspirations about some of the things that we're trying to do that can conflict with the reality of the moving red line and the timelines and the performance capabilities that you have, both in the context of training, operations, and all the other things that kind of go into a successful mission. So can you talk about the difficulties of that stuff and how you put those together and where the limitations are?
Thank you, Eric. Good friend. The feedback piece, I would love, I don't have time to really get into all of the different types of feedback. But one of the important things I try to bring into every debrief or discussion with the science and medical folks is just the human aspect of it. And I know that's like the standard mark that astronauts are supposed to talk about. But it is interesting how, the space station has almost lulled us into a sort of complacency from a medical and a scientific standpoint. It's so big. We've got a pantry of all these great things. Our, blood withdrawal station is like always set up. And so the future, though, of deep space exploration is going to be much more volume, mass, and people constrained. The numbers of people we've put through the space station is amazing, but we're not going to have that for Artemis. And so just thinking about the quality and quantity of the science that we're going to get and who is going to do that science, I think it will enable us to make some better decisions up front. And I loved your presentation. I could have sat and just listened to you talk more. I actually would love to get your slides and talk to you about some of the things Trish is doing, because I think we could really learn from each other. And one area that I also try to give a lot of feedback on, because of not just privacy, but I think there's a cultural piece to this, is the importance of the psychological research and countermeasures. For a lot of reasons, we maybe don't have the discussions that we ought to have. I'll just say it like that. But that to me is an area that is sorely underutilized. And having the benefit of thinking about this one specific thing for 7 years, I was able to fly with some things in my toolkit, if you will, that I don't think you will get when you show up that morning and you know you're going to fly to space for lunch. And so, but we need to be ready for that and equip those people as well. So yeah, great question, Eric, and I would love to dig into that some more. If you have a more specific one, I can answer that too, but I try really hard to engage with our science and medical folks. I showed up to a sleep study. I'll give you a C. So I showed up to a sleep study, and I went through this whole thing, and then in the debrief, they were giving me the data and telling me what works for me. And so I said, okay, what medicines are you going to send with me on my mission? And they're like, well, that's for you and your doctor to decide. And I'm like, well, who are you then? and that was really early on, and I realized the line between clinical and research was not clear. And so in that conversation, I also found out that blood they withdrew on day one, like that's going into deep freeze just forever. And so I have a whole new perspective on how I interact with the science and medical folks, because they might think they're telling us what we need to know, but like these basic things like, is this just to keep me healthy, or is this a scientific investigation? That was not always clear, in my first few years doing this job. So would either of you like to respond as well?
I mean, that's amazing feedback, and I think the debriefs we need to learn from. And I know, both having worked on the ops side and then the research side, of trying to be clear with the crew, and then the pressures of how much time are you available? Is it hour 15 of an 8-hour day? When you get those debriefs, and we've kind of, the whole drinking from a fire hose thing, that just because you told someone doesn't mean they actually understood it and were able to ingest it and be meaningful to them. So I think we have to be a lot more careful with that. And your point is well taken about the cultural issues, particularly still with mental health issues. The research side has been frustrated forever about lack of access to operational data. And it often goes back to, for various reasons, including privacy, but other of why it's not made so accessible. And the psych stuff from the psych ops groups, it was, well, going back to your also point of the lack of clarity between what we're doing on you as a research subject and how does that interface with you and your current medical care versus that data is meant for the population, like the altruism to the future astronaut. And they don't need to be mutually exclusive, but we really probably have a challenge towing that line. But particularly on the psych ops side, it was trying to understand what data is extractable, because they want to maintain a relationship with you where you'll be honest and converse with them and actually tell them your real feelings and issues and what you struggled with, and maintaining the privacy versus, us knowing that you and others went through similar things, and that is a gap of knowledge in terms of us giving you something, a toolkit, to manage that. And we do agree with you that we don't really understand the idea of going 36 months, 54 months on these Mars type, the ability to extrapolate from a 6-month, 9-month, 12-month mission. You say, I am completely not confident that we can do that right now. So I think we got to find a way, and I think it will be some honest conversations between yourself, the astronaut office, the research side, and say, how do we navigate this? Because we all realize it's a serious gap, and we're kind of kidding ourselves that we can't have access to that data in an appropriate way.
You touched on something that Jim and I were talking about it this morning. It's something I talk a lot about with us technical folks, just communication, the power of communication, and context. I love the way NASA teaches things, is we have these long briefings and then we expect you to walk away from it and retain that, drinking from a fire hose. But it's amazing what, we'll give you a lecture on how to build this widget, and then, you'll study it for 6 months, and then they'll throw you in and now let you jiggle the levers on the flux capacitor, whatever. And I always tell people, if you could jiggle the levers first and go, why didn't that work? Then when you give me the lecture, I have context. Context is so important. And when we were discussing informed consent, I can tell you, I signed probably dozens of them without really understanding, because as a rookie getting ready for my first mission, I just don't know what I don't know. And now I look back on that and go, wow, I say context, I say the word context 30 times a day probably, because it's whether I'm talking about developing a new spacecraft, human-machine interface, or being ready for the psychology of a 500-day mission. We don't know. When I go to conferences and go, who wants to go to Mars? And everybody's hands go up really quickly, I'm like, then you really don't know what you're signing up for. And so context is something it's hard to think about. And now, when you have a professional astronaut corps that's getting a little bit of this, integrating the area under the curve, low magnitude but long duration, now you're talking about, like my buddy Alper that's up there from Turkey, very short duration and high magnitude. How do you build context in that environment? Such communication and relationships are one of the really important things we're going to have to think about, again, to optimize how we do exploration in the future.
The only thing I would add is, we've had the ISS now, and it's been an awesome place for our applied research program. But as we move to Artemis, we have to move our paradigm to an operational research program. No two missions are going to be the same. We can't do the same hypothesis-driven research. So I think the line has to change between op and research. The questions our scientists think we need to know from Mars have to be exactly the same that Dr. Polk thinks. So I think those lines should be blurring as we move forward.
Simon Everett's Blue Abyss, that feeds nicely into my question, actually. So, lunar mission, Vic, we know that Apollo was very operational with regards to what was going on there. There was some science done. How much science are you guys going to be doing? Is it really heavy on the operational side? And of that science complement, if you've got a feel for how it's coming together, how much of that's looking like it's life science and space medicine?
It's going to be very heavy on the developmental side, or what I think in the Apollo era what we would have called engineering, because we have to make sure that this platform is safe for humans to fly, and that is our main mission. That's our primary objective. But we have gone through lunar fundamentals. Our biggest scientific contribution is going to be the foundation for the crew that goes to the surface and is able to continue the lunar exploration that we have started with Apollo and continue with Lunar Reconnaissance Orbiter and all the other programs. So how much science are we going to do? I mean, I think the best data you're going to get back is the crew's comments on what it was like to leave Earth. Humans haven't done that, the low Earth orbit in so long. That the crew comments in flight testing, in testing airplanes, we do handling qualities evaluations. And we have these scales, if any of you are familiar with Cooper-Harper ratings or Bedford workload ratings, it's a number. The output is a number. But if you read the report, what Bedford, Cooper and Harper and Bedford will tell you is the real important data is the pilot comments. And so I think the comments from the crew are some of our most important scientific data. The psychology and what it was like to be there. The observations, human eyeballs are going to see the far side of the moon. And depending on when we launch, it could be well lit. And our scientists tell us we might actually be able to put eyes on something that's never been imaged because of the lighting conditions we wanted in the equatorial region for the Apollo missions. If looking at the moon from the Earth, what would be your left side, on the far side, it has not generally been seen by human eyes. And they say, if you see it, you get to name it. So that was pretty motivating. So we've got 4 windows, and you can guarantee there will be 4 astronauts sitting in those windows when we go by. But we'll only be, 5,000 to 8,000 miles away, so no big deal. But, crew observations like we do from the space station, but really our contribution is going to be setting the conditions for the surface missions to continue what they're doing. Gosh, I would love to dig in on that some more too. But and then obviously we flew they called them Phantoms, and we had Commander Munikin Campos there to understand what this would do to human tissues, and we built one to look like the stature of a woman. And so we're actually going to take a woman. We're going to take a 6'5" Canadian, and you're going to take 2, Mark 10 or Mark 1, 5'10", size 10 shoe guys on the mission. So we're going to get a good smattering of physiology and the effects of deep space radiation on 4 people of varying, physical composition. So that's probably the most important things you're going to get out of this mission.
So one of the areas I thought was interesting, because this was coming up, we were asked to plan for Artemis when I was chief scientist, and people were like, well, what kind of science do you want to do? And I was like, the mission is the experiment, right? The outcomes and the performance of the people on the mission, why would I contrive an experiment? But are we allowed to measure you? Like, that was going back to like crossing that line and negotiating this way of saying, I'm not going to add mass, power, volume, time constraints. You're already expected to perform and do things. We should be able to understand what were the expectations of how you would perform versus how you really performed, and why we're measuring, say, the physiology, molecular changes, which would come from the other sources of, biomass we would take from you, would say we need to map that to whether you actually performed as expected or not, and then start to understand the why. And how could we have supported you better? Was it a design issue, or was it a cognitive issue? Is it a little bit of both? And if we don't start that approach, I always feel like we're always getting in our own way by making contrived things. And one of the example was, an experiment called Robot with the arm. And we would have to measure people based on a training regime when they're really being trained on the arm. And it became counterproductive at one point. It was very I was like, so why are we, they already are asked to perform, but we couldn't cross over to that line. And, there was this perceived threat of the occupational longevity or performance metrics if we went ahead and measured you for your real performance. But I think as people in this field, commercial, government, have to start to talk about that is still the most logical way to go doing about this. But how do we make sure the data isn't misused? Because the fault isn't on you if you weren't able to perform well. We just had to either adjust our expectations and allow automation to come in and help you, or design the tasks differently, or design the hardware differently is probably a more logical outcome. Or on the biology side, how do we support you better? Are there preventive measures we could take, the way we buff you up, just like any one of us who are looking to live a better life, Well, anyway, but that crosses into that territory of where it's a kind of a no-go zone right now, and I think we have to open that up because of the leanness and the constraints on these future missions.
Dwight Holland, thanks for the Trish talk. That was really cool. I love those slides. And I wanted to tag a little bit off what you just said about context. I had another remark, but once you started talking about that, I thought I'm going to jump on that real quick. My advisor for my PhD training in human factors and systems integration was Walt Werwolly. He was the graduate student that was Cooper and Harper's graduate student at the Cornell Research Lab. Then he developed the modified Cooper-Harper scale, and I was one of the research pilots when I was really young in the field. It was just one of the subject pilots. I didn't do it intellectually. Then I jumped into the field. But here's what's really cool. In his comments about human systems integration, he was an astronaut finalist candidate of the XS-11 class back in the 60s. He said exactly what you said. He said it 30 years ago, and he really impressed that on me, is that you can do great human factors in the lab, theoretically good human factors, but until you put the context of the operational environment around it, like we see in Antarctica, like you've seen in flight test and you've seen in space, it's not as meaningful. And I think that's where the minefield is. Because when you look at past accidents in aviation and systems, 80 to 90% have a definite or probable cause of human systems integration issues when you do realist. Now I said definite or probable, not exclusively human factors, because it's always a system. So when we think about human systems integration, it is, the integration part is the human, the system, and that implies context, right? It doesn't just imply human factors. And I saw so many things in the Antarctic and in the flight test world when I was doing stuff, and you saw this in space, where human systems integration, the integration part, wasn't good. And I worry just a little bit after talking with folks, and this isn't like I'm fearful because we're not doing the best we can. I just worry that sometimes when we have like a lunar lander program and we've got requirements, and then the operators are given general requirements, and then you drive down and they get to figure it out, that the people actually doing the interfaces in either the glove boxes on orbit for commercial space or whatever, or the lunar lander interfaces, they're avionics engineers and folks, and they don't understand sometimes the context. And that's so important where astronauts and flight test people like you come in, the people that have actually been there and done that, to give input. And I guess my question, having said that, my question back to you is, do you feel like right now the astronaut corps and the operators and the people that are actually going to be using this stuff are getting enough input at those levels of design? Because that's critical for safety down the road and efficiency. That's kind of my question.
Oh, My inner test pilot wants to break out and, not, oh man, no, to answer your question, no, I don't. We're small. There are only 50 of us right now. Actually, we're south of 50. The astronaut candidates graduate in March. We need them. There are not enough of us. The astronaut corps used to be almost 150 people. We were flying much more often. We had much greater involvement, and so much more overlap of the programs. We're so small now that I don't think we're providing that input because there are just so few of us active. And a lot of ways I could go with. You touched on so many things important to me, and also this time of year. This is the remembrance time, you know, AS-204, Apollo 1's fire, the STS-51L, and STS-107. We always stop and pause and talk about that and all the other things that have gone wrong this time of year. And something that I know we're here to talk about HRP for our civilian research, but put this wherever it can reside for you, because I think it's something for all of us to be honest with ourselves and think about. I read all these reports. I read the Columbia Accident Investigation Board report, executive summary, the most, and it talks about, you know, every mission is developmental. Prove it's safe instead of having to prove it's unsafe. That switch is huge. It can have such a profound impact on how you evaluate systems in your risk matrix. But I look at all of those things, the organizational changes and the effect it has on safety. But something that I've just come to realize and appreciate is I read all those things and I go, am I informed? Okay, yes, I'm aware of these things, from the attention to detail required for the Apollo 1 fire through organizational and management and engineering debate and dialogue and leadership up through Columbia. But am I better than they were? And the fighter pilot in me wants to say yes. But the engineer in me is like, no. And I'm not a scientist, but I pretend to be one on the space station. And that scientist goes, no, I actually have data that says you're not. And actually, by thinking you are, you're more dangerous. And so what can I do? I look at all those reports and I go, I'm not able to avoid what they stumbled into trying to do their best every day. I'm actually just as likely to stumble into that, doing what I think is the best. So not only do I not have the input, I think sometimes we forget the context that those folks that, you know, led up to those decisions that resulted in tragedy, they were doing their best with what they had. And so I take that to me right now and I say, I'm already doing something wrong. I just need to figure out what it is. That reading those reports makes me humble. It makes me go, I'm already screwing it up. I just have to find it. And so I'm not waiting for a screw up so that I can, you know, tamp that down. And so I think that's a mindset we all should just, you know, giving ourselves a little bit of grace. It also helps you to be a little more forgiving of yourself. But the most important thing is it helps you to be a little more forgiving of those that you work with. And so, like I said, I know that is a little bit of a departure from the direction we were going, but I just think that's a sentiment that I can't share enough, because I don't get into all of the rooms that I think we need to be in as we're developing landers, as we're developing suits. I don't talk to the suit teams enough, and that's a place where, boy, you want to see the intersection of a human and a machine making the spacesuit work the way it should. I want to talk to all of those teams. And so, no, I don't think we have the reach, but it's a numbers. I think a part of it is just we're so small nowadays. And I think that the input that we have, not only there are too few of us, the opportunities to go to space are also limited, and so we're flying less than we used to. And so we have less timely feedback, which is a great way to build context. What I thought I cared about before I launched and what I was thinking about on May 2nd, 2021 when I landed in the Gulf of Mexico, very different. And I couldn't wait to get back and talk to the young astronauts that hadn't flown in space. And so our mission in the astronaut office is to train and fly for the benefit of humankind, period, and to provide crew perspective and leadership for all aspects of human space exploration. That second part is my life's work, or at least a big part of my life's work right now. And I think building the context to do that effectively is a lot harder said than done.
Yeah.
Sorry for the long answer, but that's...
And as we train commercial astronauts to do these science projects in space, we're going to have to train them with that context in mind so they're safe and they can avoid pitfalls or react in emergency appropriately.
So much. And you're also going to, so training to fly in space is at least two parts. And I'm sitting here looking directly at Alicia Robinson, who ran this for us, but you're doing two things. You're learning the system.
We have a couple of online questions, so I'd
Okay,
like to get those out.
Then I'll share, and the system's learning you. I'll end with that. You're learning the system, and the system is learning you. These commercial astronauts, we're going to have to figure out how we integrate that second part, the us learning you, because human spaceflight is built on one thing, if nothing else, trust.
Okay, let me go ahead and just pull out one that we have here from Daniel Culp. What is the Artemis program's view on the importance of in situ resource utilization of lunar resources such as water ice?
I mean, what is the program's view on it? Vital. It's a core. I mean, the first time we land on the moon, we're trying to land on the South Pole. And if you understand the engineering and scientific risk that goes along with that, I mean, this is a Gordian problem, really complicated. The orbit you have to get into near rectilinear halo orbit so you can get access to the South Pole, and then the low sun angles. The sun doesn't, traditionally rise and set. It just kind of goes around the horizon at a low angle, so the lighting, long shadows, hard to land, not the beautifully well-lit equator like we did in Apollo. So the program thinks it's a really big deal to get to a place where we can find water ice because of the potential volatiles, the potential things that may be in that ice, but also the fact that we can refine, a potential rocket fuel from that. So in situ resource utilization is so important that I think we're making some engineering and operational risk trades that maybe we should also open that up and have that discussion. We probably want to land on the equator before we go to the South Pole, but to make sure that the engineering is safe before we focus purely on the science. But it is very important to answer that question.
Tina gave me permission to ask a question real quick. First of all, this panel is amazing. To have the HRP team here and the Trish team and one of our Artemis astronauts, thank you so much for coming to this event. What I heard from Vic, we need more missions, we need more astronauts, we need more flights. All of these things are critically important. Of course, that gives us more data and really more knowledge, more information, more experience that we can apply to this whole human-machine interface that, of course, has been articulated as so important. One of the areas where this conference is important is that we're expanding now into these commercial human spaceflight opportunities. And I loved what Jen had about the EXPAND program, so important to this conversation. Question for you, Jen, and Trish in general, how hard is it to get commercial spaceflight participants to give Trish the feedback that's necessary to have bigger sample sizes and better data? That's one question. Another question is, that EXPAND program, how is that funded? And is it adequately funded? Is that something that Congress needs to contemplate? And then I think let's just start with those two questions. I know we're getting short on time, and I'll leave it at that. The
Sure.
final question, simple one: how can a university like Oklahoma State University be helpful in this process, especially when you think about the EXPAND program? I'll leave it there.
Yes, on the technical side, I think we're always open to feedback. I would have to lean on Emmanuel a little bit. The structure is because we're working with our commercial partners, they're really organizing the complement and our ability to interact with the flyers. And so I think we could probably be more deliberate about, there are surveys involved, but specific surveys of saying how did they experience the science, what did they agree with, disagree with, how did they experience it, more contextual. Is probably something we would have to be more deliberate about to make sure we're eliciting that feedback, and we build the time in that they have to provide it, and maybe chasing them down a little bit afterward. And we do a lot of virtually now, so there's no excuse we can't get to anybody almost anywhere in the universe at this point with some sort of comm delay. The funding generously comes from the NASA Human Research Program. We are fully supported by the federal dollars, and we had to go back and make sure that HRP was understood, how this fit into their charter, and we're in total agreement that this is appropriate in terms of knowledge on humans, helps us all grow. Well, data on humans help us grow that knowledge base, right? You got to transfer data into knowledge at some point. That's a process too, and a debate. And then how far can we extend it? I will say it's a shoestring budget. It is a challenge. They have an overwhelming number of risks and priorities that we constantly are renegotiating and a lot of things fall below the red line, but David has been clear that the infrastructure built for this is important, and we need, essentially to use that responsibly. So we continue to work that. We make sure that the other use of our budget is to fund science, and I mentioned the other initiatives, but these are not mutually exclusive. So we've kind of been able to parlay the science and say the medical data architecture to be applicable to expand, and the expand work goes back and forth. So we're able to populate the science, the funding for the science through the entire Trish budget, but the infrastructure has to be recognized and be in our budget line, because it's not trivial to make sure we have the infrastructure to go execute with all the different providers, present and future. We're working with all the ones who currently even aren't flying people, because they need infrastructure to allow science to occur. And for some of them, that's not a priority in front of them. So you kind of have to keep on encouraging the development of that capability in the developmental companies. To your last question, of course, Oklahoma State University can be of service to expand. We're just opening these conversations and helping them understand what we're trying to achieve, and they're helping me understand what their capabilities are, and that's how we begin a collaboration and a partnership, because there's no reason for us to invent capabilities at another, at Trish or Baylor or wherever, if they exist. I just have to know about it. So I think that conversation has just started. Obviously with OAIRE and the work they do here with aviation research and the data collection that goes on, the human factors concept, the human-centered design, it is all right on the mark. So I see that there's a ton of potential. Now we're just going to describe the requirements and how we're going to move forward with the expand program, and what is our growth going to look like over the next couple years. I think when you talk about what Congress can do is really support the human research program at NASA, because that supports Trish and expand. And there's a lot of work to be done, and we can be very responsive to the growing needs of the community that's going, and we have always recognized the lack of diversity. One of the areas I'll be working on in 2024 is a female health initiative. That is continually an area of lack of data, and we, going back on uninformed consent, for a lot of the women, it is a real challenge to be able to describe to them what in particular are the risks for them in the future. So it is work that needs to be done, but right now with the finite resources, we make hard decisions about what actually can be manifested and become a payload and become a practical science that delivers data, but we always have plans for more. And I think it has been an underfunded area for a significant amount of time.
Thank you. I'd like to thank David, Jen, and Victor. This is a fantastic panel. Okay. So yesterday we talked about track 1, which has to do with comprehensive measures. Comprehensive being broad versus standard measures. There's a difference between the two. Track 2, on the other hand, is more of what most of us are familiar with, which is hypothesis-driven research. And we're going to be hearing from, I don't know if I can say her name, Funmilola Oluwafemi, from the Nigerian Space Agency. And she has written a fantastic article about isolation and confinement, and that's how I got to know her. And we are having a little bit of a internet connection, so what I'm going to do is ask Sherry to come forward. Are you mic'd, Sherry? We need to mic Sherry. Yeah. And Sherry works at Bowling Green State University, and she also works a lot with Astro Access. And she's going to talk to us about making space accessible and safe for individuals with disabilities. Yeah, I will. And can we get her slides up, please?
Oh, good, the mic is happening. It's such a tiny, whoa, sorry. It's such a tiny little mic, too. Are we good? Okay. And that is fine. Feel free to just, I will tell you when to advance the slides, but if I get wrong, feel free to flick back and forth. It's totally my fault that there aren't big, fancy, glowing Roman numerals on the top of these, so I can say slide 6, but I can't do that. So I think we're good. Okay, thank you so much. I'm so glad to be here. This is such a fascinating couple of days. I've learned so many things, and I've taken so many notes. We're doing such good work here, and I have faith that there's a whole lot of more good work to come. And I'd like to add an essential piece to the discussion underway that I hope will turn out to be useful. And the idea here is that what I'm about to say is not just useful for the subset of people that we have designated as people with disabilities, but it will turn out to be a set of research hypotheses and practices that will be useful and make things better for everyone. We know that space is a disabling environment. Either it will disable you slowly over time through one of the many mechanisms we've heard about, or maybe space will disable you through some kind of sudden accident. So whether we send disabled people to space or not, disabled people will be there. And it occurred to me as I was listening to the presentations yesterday that if 1 in 4 folks on Earth has some kind of disability, it's possible that number could increase in space. It could be something like more like 1 in 3, especially in some DRMs. And I'm just super interested in what the social consequence of that might be. We need an anthropologist up there immediately to check that out when it starts to happen. Next slide, please. So if we want to keep people safe as we go to space, keep everybody safe, we have basically 2 choices. We can screen them out, or we can accompany them as they go to space and provide them with accurate, informed consent. And I'm really glad that we're all on the same page that what we want to do is accompany people on their various journeys to the stars or partway to the stars, instead of telling people that they can't go. The part that we're missing, though, is a systematic, hypothesis-driven research program that's asking questions about what disabled people will really need to be either productive, trusted crew members or safe, happy tourists. Sorry, my thing's okay. So, whether you're medically safe or not is only one of the primary questions we have to ask. So say, for example, that I have a classroom. I'm a college professor. I have a classroom. Everyone has told me that it's medically safe and it's all fine. No one's going to be injured by being in my classroom. I welcome people in. I find that although it's medically safe, there's no room for my wheelchair students to park their wheelchairs, no chairs for them they're safe for them to transfer into. There's no captioning on the videos that I'm showing, so my deaf students don't know what's going on. And I haven't clearly told anybody where the exits are, so my blind students aren't actually safe in this environment. Okay, there we go. Was it going to be less? Oh, there we go. Less weird, echoey, buzzy thing. Thank you so much. Okay, so what I've done is in my hypothetical classroom situation is I've granted entry, but I haven't done anything about access. So the medical aspect of what we need to do is incredibly important. It's essential, but it's not quite sufficient. Hit my next slide, please. The principle of universal design basically teaches us that changes that we make in the world around us, nominally made for the benefit of disabled people, make things safer, more comfortable, and more convenient for everyone. The classical example of this is the curb cut, and so my apologies if you've heard the curb cut story 95,000 times, but that is the classical example of access. So if a wheelchair is going down a sidewalk, a good thing that they need is to be able to descend to street level without going over a big bump, without going over the curb, and so we designed curb cuts to allow people to descend gracefully and safely to street level and to rise again after they cross the street. It turned out that everybody actually liked these. It was good for people who had strollers. It was good for people with minor knee injuries. It was good for people with those wheelie bags that we all have now. And it turned out to be safer for everyone as well. So I know there's a lot of medical folks in the room, and some of you have no doubt treated people who have fallen down a step or off a curb or down maybe several steps, but I'm guessing that way fewer of you have treated someone from falling through a curb cut. It's just a safer way to get around. We didn't automatically make these curb cuts perfect, though. It took some design, it took some research, it took some time. So we had to decide where to put them. Do we line them up with a crosswalk or do we offset them? We had to decide what angle of descent and rise is necessary for various kinds of wheelchairs. That was a long, complicated investigation. And eventually we had to figure out that we needed those little dots, those little raised bumps on the curb, so that everybody knew that the curb cut was coming and that it was a crosswalk. So the question that we have to ask now is, what are our space curb cuts? What is it that we need to do? The next slide, please. Our goal here is to widen the aperture. We want to get more people closer to the stars. There always may be some groups for whom travel into space is unwise. Perhaps people who are medically fragile, people who could not survive the trauma of a launch, and perhaps people with communicable illnesses, not a good time to go to space. So we're just trying to get everybody closer and do what we can do to widen the aperture of access. The next slide, please. So whether you have a medical condition is one question, and we're doing a great job with that. Whether you have a disability is based on your environment. So if we go back to my lecture hall at my university, if I provide only print copies of my textbook and only print handouts, and I do a lot of gesturing when I lecture and say, well, that is, of course, the right answer, but that, don't ever do that, then my blind students are effectively disabled in that environment. But if there's a sudden change in the room, maybe a sudden change in illumination, perhaps it becomes painfully bright, or perhaps the room is filled with smoke, some other off-nominal classroom situation, the blind person in that classroom will have more freedom of movement and will be safer and make a more graceful exit than the rest of my class. So we've basically switched the disability context in that classroom. And that's what we have to think about in terms of access. How do we take people where they're at and give them access to the environment that they need access to? Next slide, please. There is some urgency to this situation. Well-researched design takes time. And we are right now in the process of building things. We are building habitats. We are building vessels. And we ideally want to avoid retrofitting. So the research has to happen now. And there is some ongoing research, perhaps not as much as everyone would like there to be, but there is some. One of my hats that I'm wearing is a representative from ASTRO-ACCESS, which is an organization interested in disability access to space. So one of the places that ASTRO-ACCESS has done a lot of our hypothesis-driven research is on zero-G Peric flights, our old friend the Vomit Comet. We have had the opportunity to have disabled people aboard perhaps 6 of those flights. Flight ops in ASTRO-ACCESS is disability-led. This is essential. So you can treat people with heart disease and you can be a cardiologist, right, without having heart disease yourself. That's perfectly fine. But you cannot effectively design for disability if the program is not disability-led. We need the embodied knowledge of that disabled community at a minimum, right? At a minimum, the thing we can do is we can stop super bad designs from getting started, stop super bad ideas from happening. I have a really fun list of things that able-bodied people have suggested that disabled people need that never go anywhere. Some of them are super amusing. I won't go into them here though. But they're bad ideas, and we're able to stop those. Sometimes, next slide please. Sometimes we already know what is necessary. Sometimes a space habitat is just, in fact, a room. It is a really fancy, expensive room, and you shouldn't go outside, but it is, some of them are just rooms, partly, right? And we know how to make rooms accessible. I participated in an analog mission earlier this year, and honestly, a lot of what we did was cleaning up and making coffee and writing reports and doing research that we had brought ourselves to do. So we know how to do a lot of things that we're already going to be doing in space. So some analogous established practices are a good idea, like the Braille warning sign. Braille is time-tested, 200 years, worked great. Had some minor refinements along the way, but that still works in space. I have a couple pictures for you from our zero-G flight showing the kind of research that we are doing, and it's not great research because we're doing it, it's great research because it's hypothesis-driven, and we would really like to be only one of many groups doing this research. Hit the next slide for me, please. This is a pic of a NASA employee who flies with AstroAccess. She is looking with her hands at a tactile image on the wall. This is a tactile warning sign. We discovered a couple things through the implementation of this program. One of the things is that where you're going to put the sign is complicated. So on Earth, we know where to put signs because we know that people are going to be oriented with their feet down. We know for a print sign kind of how big to make it. We know how people are going to be oriented. For a Braille sign, we're hoping that they're designed such that the people reading them will be feet on the ground, hands up in front of them, so we know how high off the floor to put it. That's not useful in zero gravity. So the first thing we have to do is think about where to put these signs and how people are going to find them. So instead of one random sign placed in some spot that we hope is useful, we might consider iterating these signs, making more of them, and fixing them to a handrail, perhaps, or some that everyone will be using anyway for stabilization and translation through the space. So that might be one thing that we learned. The other thing was that we can increase the information density on a sign. So the graphic that this flyer is consulting right now contains not only information about which way gravity is going to be when it comes back, which we thought was essential for the parabolic flight, but also information about the direction and relative distance of the nearest exit, and also the nearest emergency equipment. So she's participating in our first study, studying the effectiveness of these tactile graphics. And the cool thing about them, I think, is that if you have these things, sighted or blind, right? And if you come across one of these, especially in an environment where vision is occluded by dust or debris or smoke or the lights are out or whatever, you will have more information faster than you would have if you are kind of looking around. Oh, where is the exit? Let me reacquaint myself. Oh, where is the fire extinguisher? Let me reacquaint myself with the room. All that information is right under her hand when she's touching that graphic. Wouldn't it be cool if in your airplane seat as you're flying, instead of saying, look around for the exit, you know where the exit is just by touching the arm of your seat. All that information could be right there. Next slide, please. Sometimes we need extended practices where space introduces a known complication or complexity. Can you get my next slide, please? This is a picture of a CEO of a space company who also flies with AstroAccess, and he is doing some seat docking. One of the things that we wanted to investigate was the question of whether disabled people could get their bodies into the launch seat and fasten that 5-point harness in a limited amount of time like you have to do in a suborbital flight. It's clearly a safety concern. If you can't get your own body safe in there, or you can't devise a system for someone to assist you, that could result in severe injury, right? So we wanted him to get into this seat, and we were doing this with blind and wheelchair users on this particular flight. We wanted him to get in his seat and buckle his harness. We found out that, yep, the blind people and the wheelchair users on board our flight can, in fact, get their bodies correctly positioned on the seat and get that harness fastened. We did find, though, that fastening the harness, I mean, if any of you have done one of those 5-point harnesses, it's not an easy thing. I can also tell you from bitter personal experience that if you grab the strap in zero gravity and pull it toward you, you will be whacked on the side of the head by that buckle. It was fine, everybody's okay, but can't we do a modification so that that harness is easier for people with hand differences to latch? A benefit to everybody, right? If we can make a harness that will be provide access to disabled people, but also easier for everybody to latch. My next slide, please. So there's some instances where we need new innovation, where something clearly new has to happen, a problem that we have not encountered on Earth that we need to innovate for. Get the next slide. So we know that we don't need a wheelchair in zero gravity. That would be ridiculous and probably dangerous and bizarre in any number of ways. But what do you need if you have no control over your lower limbs? So your legs still have mass, but you can't control them. They can impart spin to your body without you intending that to happen. There's some interesting video of a guy with lower limb paralysis on a zero-G flight, and his legs sort of get out of control, and he's just engaging in a little bit of spin. It's all about Isaac Newton with your legs if you don't control them, right? So what can you do? One of the suggestions that we came up with in consultation with our wheelchair users is some kind of leg tether. This might be in the form of a flight suit modification. So this is a science journalist who flies with us, and he's got his legs fastened together at the knees. And is that the best place to fasten it? We just genuinely don't know. There are a lot of hypotheses about what would work best to control your lower limbs if you can't control them autonomically. How do we introduce something that will be useful to you in that environment? The knee tether worked reasonably well, but it was the first thing that we tried, so there's probably lots better we can do. Next slide, please. This is a pic of 2 aerospace graduate students who fly with us. Both of these folks are deaf, working on intelligibility of American Sign Language in zero gravity. We have a paper that is in production. We're still analyzing the data from this flight about some of the grammatical intricacies that occur. Nothing serious, but super interesting, especially if you're a linguist, right? Some of the interesting grammatical intricacies that you might be aware of if you are ASL user in zero gravity. We're working with linguists at Gallaudet to finish analyzing that data and get it out. So one of these 2 people is upside down. Nobody maybe knows which one, right? And maybe it doesn't matter. But then they're signing to each other and they're understanding each other well. The other thing that you can see in this picture is there's a little light behind them. It's a little green light, which means that they are in a microgravity environment. So if you've been on the Vomit Comet, by the way, none of the disabled people threw up, but a couple of our allies did. So yes, we were all deeply amused by that, and I don't want to be smug, but I am. Exactly, sure I do. And we know, and we expected some of this because of the contributions to space science from Gallaudet students in the early 1960s, where a group of them whose deafness was caused by an inner ear difference, which meant a middle ear difference, which meant that they were immune to space sickness. So they did they helped a lot with some experiments in the early years of NASA. So anyway, what these folks are doing is looking for that little green light. The coach is about to yell "feet down" coming out, and all the hearing people will hear that, or most of us anyway, and we'll try to get it oriented so that we land safely. But if you don't hear that cry, we also trigger a visual component, a visual light that will let them know that that call has been made. And we heard from multiple people on the flight that those lights were actually super useful. Everybody really liked them. Next slide, please. This is a SpaceX employee taking on and off her prosthetic foot. So you can and you definitely should ask the question, is this safe? A better question to ask is, how can this be awesome? So if you can remove your foot when you're not even using your foot in microgravity, what could you put on instead? What can we make? What can we build? What would she really like to have? How can we change what is arguably a deficit on Earth to a benefit in zero gravity. And so we're looking at prosthetic designs for people with limb differences in space, not treating that as a problem, but treating it as a really interesting opportunity. And my last slide for me, please. So I think I'm so grateful to be here because I feel strongly that we're all on the same page, that this is what a space crew should look like, or can look like. It's a multi-ethnic crew, multiple, with different gender identities. Lots of us are disabled in this pic, and many of us are not. This is either Flight 1 or Flight 2. If you could zoom in on my face, you could tell by how scared I look if it was Flight 1 or Flight 2. But we can make it be like this. But to do that, we have to establish disability-led research programs to ask the right access questions, and we have to have a system for sharing those results. So we are doing exciting work this week, and I have great hopes of the potential that of the things that we're doing. But we don't want only to clear the way for disabled people to enter space. What we want to do is give them full access once they're all there. And thank you so much. I'm super happy to take questions. Oh, yes. I mean, if we have time for questions, which I get.
We do have time for one question if anybody has one. Thank you, Sherry. Yeah? All right. We do.
John Kennett here from PML. We developed the exercise countermeasures, and we've been working with an amputee. We've been working with an amputee on board the zero-G flights. You make such a great point about such what might seem simple things, but just simply which way up when 1G starts to arrive again, when you're on that flight on the Vomit Comet. I think there's so much that the spaceflight community can learn from the work you're doing, and I'm curious to how much that is actually flowing back in to NASA and to ESA with the work that you're doing at this moment in time.
It's a super good question. No one is doing this work full time. We are all volunteers, which is suboptimal in a number of ways. So it is slow. I think one of the things that we need to do as soon as we can is establish some kind of center, and so that some of us can be doing this work with more of our time instead of between grading papers. So I think we're working on it. We attend conferences. We're publishing as we are able, and that's one of the reasons that I'm worried about. I've never felt weird about knowing things before. I've never felt uncomfortable about having knowledge, but I worry a little bit that we know these things and we don't have a quick, efficient way of sharing that knowledge quite yet. So the answer is, I don't know, maybe?
Thanks very much.
Thank you.
Thank you, Sherry.
Okay, thank you so much.
Okay, next we're going to hear about isolation, confinement, and distance from Earth from Dr. Funmilola Oluwafemi.
Good day. I'm Funmilola Oluwafemi. I work with the Nigerian Space Agency, and in this workshop, I'm making a presentation on the topics isolation, confinement, and distance from the head. By way of introduction, there are several categories of risk that have been deduced for manned mission to space in relation to health and safety of space travelers, and these include gravity transition, isolation/confinement, hostile or closed environment, space radiation, and distance from the head. These are the 5 major categories of risk for manned space mission. And hence, this presentation is on the discussion of the challenges and countermeasures to the isolation, confinement, and distance from the head for civilian space travelers. When two or more people are crammed into a small space, of course, there will be behavioral issues, especially if it's going to take a long period of time. So many issues will be generating because of the confinement or isolation of them in a restricted area, especially if it's a long distance. For example, the distance from the Earth to Mars is going to take about 3 years. And this is a long period to confine some set of people, on this journey. I was discussing with somebody, and she said, "Wow, this is going to take 3 of my birthdays." That means she's going to celebrate her birthday 3 times on the split flight before getting to the destination. So this is a very long time for this, for the proposed long-term mission. And even if it's a short-term mission, to be confined with 2 or more people, so many issues are going to come up. You are going to know the person's behavior the more, and others. So what are the challenges that arises from the isolation, confinement, and distance from the head? I categorize the challenges into 2. And the first is the psychology. The challenges that are classified under psychology, and the effects on behavior and emotion of space travelers, which may lead to mental health challenges. So, of course, the isolation and confinement and the long distance is going to affect the behavior and emotion of the civilian travelers, space flight travelers, and it may lead to mental health challenges. And the second point under this grouping is that it's going to affect the psychosocial. It is going to have psychosocial effects or challenges that is going to be seen. So therefore, there are so many psychosocial factors or issues that I have listed here. And the first is cultural issues. And this deals with the background of the people that will be in the space flight together. They may actually be from different cultural background. Hence, what is called good to one of them may be termed as bad to the other. This is because of the background and the mindset, that they are bringing into this travel. And the second is interpersonal stresses. That are some things that personally, one of them may say, this is okay, and the other will say, this is not okay. In fact, this is part of it. So that is expected to happen as well. Loneliness is expected because of the long time. There are some things that they do on Earth. There are some particular habits. What they do, they may not be able to do them on the space flight, and therefore it makes them to be lonely. Then there was going to be limited social contact. So many people, they like to be on the social media, but this is going to be restricted during this space flight. The next point is lack of support from heads due to communication delays. The ground station and communication to them is going to be delayed because of the distance, and this may actually affect the psychology some of them. They will not also have access, they may not also have access to their preferred food. For example, someone from a particular cultural background may prefer spicy food, while the other may prefer crunchy food. So therefore, they may not totally have access to the kind of food that they want, or to the kind of taste that they want it to be. The next point is sleep loss. Because of the environmental factor, the microgravity, and other factors, therefore, there will be several times that there is going to be sleep loss. They will not just be able to catch the sleep. The sleep will not just come. The body wants the sleep, but they can't just catch the sleep due to the effects of the space environment. All this is going to cause depression on the civilians. Yeah, sometimes they're going to feel depressed. And there has been proposed a space psychiatry. So therefore, it is needed to be to be looked into very well. There is need to prepare more. That what if something like space madness happens? Although in some of the space agencies, advanced space agencies, space flight, it has been said that this is already prepared for, but for the civilian space flights as well, it should be prepared for as well. And all these affecting the psychology may lead to suicidal and homicidal intent. The civilian may want to, kill him or herself, or even kill somebody else. So please, let's prepare concerning all these challenges. The next group of challenges, they are classified under insufficient spaceflight hygiene. And the internal environment of a spacecraft will be contaminated. And where does this contamination come from? The contamination is most of the time is not from the head, but it is from the byproduct from space travelers' food, the water, the air, the interior surfaces, and the scientific investigations that include animals and organisms. So therefore, making the spacecrafts to harbor microorganisms like bacteria, fungi, and even protozoa. So, and this can cause some certain diseases. So this should be put into consideration. And hence, personal hygiene of space travelers is quite important, as this is risk in relation to human factor. So what are the countermeasures for these grouped challenges? So the countermeasures on the psychological challenges, I have them listed. The first is the use of microenvironment. And what are microenvironments? This is making the environment of the spacecraft to look as natural as possible. So having a full sensory experience through depth, touch, smell, and even taste, just making it real as possible. And the inside of the spacecraft should be beautiful and modern. So this is going to enhance positive psychology. Pre-flight screening of the civilians candidates for verbal content analysis and any mental health challenge is quite important. So this is going to screen the civilian candidate, to select a right. And another point is access to good desired food. For example, using food printer. As I mentioned before, one of the civilians may prefer spicy food and the other may prefer a crunchy food. And hence, food printer is going to assist in this instance, because they may add the spice as much as is needed. And access to entertainment is another important point. When there is entertainment, most of the time it makes most people, happier and healthier, and then affecting their psychology positively. And there should be private sleeping chambers for each person. The second grouping of the countermeasure is on the spaceflight hygiene for civilians, and the following are recommended for the civilians candidates: pre-flight vaccinations, pre-travel infection control education that includes hand hygiene and health etiquettes. Space habitats and environment should be equipped with HEPA filters for better air filtration. There should be antimicrobial coatings on surfaces. There should be frequent sampling of the space cabin air. Water storage and distribution system should be manufactured using non-corrosive material that has limited organic carbon to minimize biofilm formation. There should be coating surfaces with the spacecraft. Within the spacecraft should be made of a non-leaching, non-porous antimicrobial material. There should be prevention of humidity against uncontrolled microbial growth, routine housekeeping and monitoring of surfaces, water, and food, etc. And also, there should be access to equipment needed to detect microbial pathogens causing infections. And this is going to be a therapeutic intervention and mitigation. And the major third countermeasure is there should be synergy between the space safety community for civilians and the designers and operators of spacecrafts. In conclusion, space flight hygiene and taking the preventive measures against the negative psychological effects of isolation, confinement, and distance from Earth is key by the civilian candidates. Also, the space safety community for civilians must not only provide valid requirements for certain suggestions, but must work very closely with the designers and operators of the spacecraft developed and tested, participating in any necessary compromises. Mission designers are well aware of the challenges of providing a safe, extremely reliable, and habitable environment. Thank you for your attention. These are the references that were just.
It may be possible to ask her questions later during the discussion, but she does have a shaky internet connection. Right now, we're going to take a break, and we'll get started back again at 10:50, and we'll hear Simon Evans from Blue Abyss tell us about some of the work that he did while he's been on the planning committee.
but freaking cool. Yeah, I would get burned. Talk about a virtual spacewalk. Yeah, and actually, that's one of the our hand on the shoulder. Make sure. One of those on the bottom. Whoa. Virtual spacewalk. Yeah. Thoughts?
draft at the moment. We're not suggesting that this is the answer. There's a body of work that would be required that if such a tool were to be adopted, to fill it in appropriately and properly. But just looking at the microgravity element and expanding that out a little bit, you can see that there are, oops, I've got to go back again. I need a pointer. You can see that the grey column there are the phenomena, and the top one there is fluid equilibration. So what effects might we expect from, Tina's going to give me a pointer. Lovely, thank you, Tina. Got it. What effects might we see from fluid equilibration, blood pressure equilibration, in the longer term, orthostatic intolerance, hypervolemia, and so they can go on. So that there's a number of different effects that we would see linked to fluid equilibration. And the same with the other elements, cessation, alteration of G receptor stimulation, and then what are the effects of that? So here we've got section A, the many and variable effects. Now, let's go on to here. Section B, looking at the health conditions and disabilities. So here we've got two sets, as you can see, health conditions at the top, disabilities at the bottom, and we've got categories of health conditions. We could list what are all the health conditions we're expecting our spaceflight participants to fly with. They're going to be hundreds and hundreds and hundreds. I'm sure that we all understand that. So what we thought is it might be possible to use such a tool where these conditions are put into categories. And one of our number has produced a number of categories there. Will this work? I think by populating and using the tool, we'll see whether it works. And similarly with disabilities, there could be hundreds of disabilities, or should we have categories? And we've put categories in here. It's a little bit more tricky, actually, with the categories. I sat down with a disabilities network led by King's College London, and we found it was quite tricky to categorize the disabilities, but still, that's for someone to look at if this work is to be pursued. And so, health conditions, the different categories to the right are the impacts. So those effects that we were just looking at, for a given health condition, there would be a number of those effects which would impact that condition. And so what can happen with a tool like this is those different effects can then be linked to that health condition, so that we can look at the health condition and go, oh, okay, 1, 2, 3, 5, 6, 7, 8 effects we're expecting to impact this condition. And what are those impacts? That's over to the right. So impacted in what manner? A brief statement of what that impact looks like. And similarly with disabilities. The categories, what are those many effects that we would have listed in section A? Of those many effects, what are those that affect this disability? And then what is the impact? So if we just home in on the health conditions and look at the top there, the first category is cardiovascular. So I've just thrown in there to the right the impact, the effects that were in the previous sections. These were linked simply by linking cells, equals, and then the cell number. So slow, difficult to access expert advice is an effect of distance, for instance. That could impact cardiovascular condition. Restrictions on medication availability, that would could impact a cardiovascular condition, and so on. So I need 3 hands. The impacts are the effects are what effects would impact the condition, and then to the right you might remember it was impacted how. So for instance, with regards to slow, difficult access to expert advice, so in an emergency, advice and guidance would be could be slow to be received. For restrictions on medical availability, possibly insufficient medication, e.g. beta blockers, we're looking at cardiovascular, aren't we, anticoagulants. So the impact, or a brief statement of what that impact might look like, would be there. So that's the health conditions and disabilities section, and then below that, what do we do about that? What can we do about that? And where are there gaps? And this is one of the important outputs of such a tool. So it's the countermeasures section. So there, that's divided into 2, and it's linked then. So countermeasures, those various health categories and disability categories are in these two sections. And what we have then as columns are examples of a training program or a medication or some sort of preparation, some form of mitigation that we know of that would then alleviate that impact that we're looking at. Where we don't know of a mitigation, we can put in I've put in a yellow box which shows here is a gap. This is the gap that our research program would want to try and fill. So for a given condition, as I said, a series of potential countermeasures, and there may be a dozen different mitigations that could be used to solve the issue for one particular or to mitigate against one health condition being negatively impacted. So there'll be a series, one would hope, of mitigations here, and the same for in the disability section. So just zooming in, then we're still using that same example we looked at before. I'm just going to throw that in. It might actually, and this occurred to me earlier today, it might actually that there is a partial mitigation. There's something that could be used, but is it ideal? So maybe rather than simple, yes, it's fixed, or no, it's not, there's a continuum. And so I've put in orange there. I'll talk through that in a second. So going back to our example, cardiovascular as a category, slow, difficult to access expert advice, which might mean that guidance would be slow in an emergency, would be slow to be provided. One mitigation would be to have an on-orbit medic, and it's something, of course, the MedOps community is very aware of, and that is simply one mitigation. With regards to restrictions on medication availability, if there's insufficient meds up there, well, maybe the SFP, the spaceflight participant, needs to launch with his or her medication and enough for the duration of the time they're in space, plus some buffer probably. So it's another mitigation. So these mitigations are in here in relation to the impacts that we saw in the previous section, and where we might have something that's partially mitigated, increased risk of thrombosis, so prophylactics, anticoagulants, but do we want every spaceflight participant to be taking those? It's probably not the optimal solution. I think there's work to be done there. So that shows that there's work to be done, and here, yellow, we may well have a gap. So the tool, very quickly then in summary, three sections for each DRM. The top is the effects. We look at a health condition or a disability or ability, if you might say, and we link those effects that we think would have an impact on that condition, and then we will be able to have a statement that outlines what that impact is for each of those effects, and the same with the disability section. And what we do then is we link what countermeasures, what mitigations that we know exist to these impacts, and we are able to do that in as much detail as we can do for both health conditions and disabilities. And as I mentioned, where there is no mitigation, no solution, then we've got a gap for our research teams to be able to focus on. So it would take a fair bit of work to populate something like that. So there's certainly a body of work that needs to be done. And we must remember that with regards to all of that, excuse me, that's one DRM, and there will be a number of DRMs. So some of the DRMs are going to be very similar, so there will be a great deal that will be common between DRMs, but certainly still there's a body of work for each of the DRMs. But the concept allows the interrelationship between the effects, the condition, and the mitigations to be shown and to be covered for whatever DRMs are decided in the end to be adopted by the program. And what I hope that in conclusion then is, so HRP-C aims, and I'm sure will to a large degree, help unravel the intricate relationships between the space environment factors and the physiological well-being of spaceflight participants, and enable more effective and improved countermeasures and mitigations to be produced. It'll allow the cross-border activity, the international collaboration that we're seeking to facilitate, and it will, of course, advance our ability to safeguard human health. The platform Excel, as I mentioned, it is purely for our ease of use for us to be able to show you what we had in mind. Maybe a DAG might work, maybe some sort of heat map, I don't know. So I think different platforms could be reviewed to see which would be most optimal for something like this. And as I mentioned, there is a program of work required, so we would need to agree that that's to be pursued if it's felt that the benefit is sufficient to conduct the work. And once completed, it would require management. I think it would then be a tool that the international research teams could view and work from, but it would need management, and that dynamic framework, I think, would make for a supported HRP-C as it moves forward. So I think that's it. That is indeed it. So, Tina, thank you. Thank you.
We're now ready for the discussion for track 2, and Mark Schellhammer is going to lead this discussion. We'll hear again from Mark later. He's from Johns Hopkins.
Thank you. Okay, so I'm going to ask my panelists to come up on the stage. So Sherry, Simon, Michael, whom I've prevailed upon to join this since he invented track 2, essentially. And I will start by giving some of the ground rules, which I'm going to take from Simon's ground rules from yesterday, which are that we're looking for comments, remarks, suggestions from people in the audience, including online. Not speeches, not grandiose ideas, not complete changes in direction. We have a report. We distributed the report. We know that you didn't read the report, but there is a report, and you've heard a lot about what's in the report, the contents of our deliberations and putting together the general plan for an HRP-C. What we're really looking for from you at this point is whether or not we're on the right track. Are there things that we're missing? Are there things that you think we should put into an HRP-C that you have not heard yet, or maybe that you've overheard and are not really necessary? So feedback on whether we're taking the right approach. Help us put together the HRP-C. Okay, I'm going to toss out a starter question to get the discussion going, but first, I'm going to prevail one more time on my good friend Eric Antonsen to come down and say a few words, because he had a few things to say about Simon's presentation, which just ended. So I think while that's still fresh on our minds, we'll let Eric say something about that.
So Simon, so what you have been wrestling with is something that I and Jen Fogarty and many others have been wrestling with for many years in the research administration aspects of both HRP and the Human System Risk Board. And part of the reason why we struggled with it so much is, one, because it was an under-recognized portion of what is needed for research. The organization of putting all those things together and making sure that you have that top level, both mapping and acknowledgement of where the gaps in either knowledge or capabilities are. So back in 2008, Jen Fogarty and Jeff Davis at NASA started doing things called RMATs, which was some of the early work in starting to capture this as a research administration tool. And then a number of other advances were made over the years within the NASA system. But for the most part, it was not a funded effort often, because it's not recognized as part of the research, right? And so, first of all, what you did was amazing, coming from somebody who has struggled with these things. Second of all, there are a number of things that have been built out within the HSRB that have tried to tackle the same problem that are probably some things that can help you take that to the next step so you can learn from the errors that we've made. I'll be talking a little bit later about DAGs and stuff like that because we eventually moved to graphical databases and away from relational databases because of the complexity of all the things that you're talking about. So I'll be dipping into those a little bit later, but huge kudos to you, and please, this is one of those things where if you don't actually, as part of a research program, fund the development of the management tools for this, then it's really easy to lose track of all these complicated things. So great job.
Yeah, wonderful, thank you. And that's the key, isn't it? Management tools or management, because we're going to have, all being well, if this moves forward as we hope it will do, we're going to have many research teams, many nations involved, many individuals involved, and we want to all sing from the same hymn sheet.
And take advantage of the advances in computer technology and relational management and stuff that are already happening in other parts of the world.
Right.
So staying at the front of that can really help.
Yeah, thank you, wonderful.
Yeah, I think there's another general principle there, which is when available, there's no need to reinvent the wheel. So there are things that NASA has already done there that are very relevant to what we're trying to do with an HRP-C. We should feel free to steal everything we can from the pre-existing HRP. It's your tax dollars at work. Okay, so with that, I'm going to throw out a question first for the panel, and then but you can comment on other aspects of what you've heard today too. But the question I'm going to pose is, what does what we're calling a track 2 focused hypothesis-driven research program look like? So let me give you a little context. You've heard that there are X number of different medical conditions out there, people with a wide range of disabilities who are going to want to fly into space. And the job of the HRP-C is going to be to enable everyone who wants to fly into space, just like that's the job of the NASA HRP. But we know if someone shows up at one of the commercial space providers, flight operators, with $100 million in his or her pocket and has 5 medical conditions that the HRP-C has not addressed, that person is going to fly. What do we do about a situation like that? What does it mean to propose a hypothesis-driven, targeted, directed research program when the targets are almost too numerous to name? What does that program look like? Now, I know my panelists have some comments on that because I've seeded the question with some of them. Whoever wants to start.
Well, one thing I would say immediately is, in advance, okay, they're flying already. These high net worths are flying already. But as soon as the HRP-C program can get going, we need to be able to start prioritizing what are we expecting those conditions to be, so that we have within the program a set of priorities to enable us, hopefully, to be in advance of the next high net worth individual who turns up and said, hey, I need these 3 conditions looked after. And we go, yeah, we know that. We've had that in our mind, and we've started the research programs to pursue those solutions.
So you can do some of that just by prevalence of the conditions in the population, and that probably will take care of a large number of the problems, but not all of them, right? It's that one that just kind of comes out of nowhere, and we're just not ready to fly that. Under conventional circumstances, you'd say you're not ready to fly that person, but you're going to fly that person. Sherry?
So I might start one step backward. From where we're at right now, which is clearly making a separation between health condition and disability, because those have different, those need addressed in different ways. So if you have a health condition, something like your heart problem or your cholesterol or your blood pressure, whatever you've got, that's a medical concern that is particular, is always going to be particular to the individual. So then, which is different than a disability, which is I don't have access to some environmental factor or some function aboard your spacecraft that I'm going to need. So keeping those things separate is going to be super important just from an organizational standpoint and help you figure out what you actually need to do. The second, I think, in advance is figuring out what your priorities are going to be. So we can and we should do the matrix of however by however many where you lay out each possible thing you could face and each aspect of your flight, and just filling in all those squares. That's a Herculean effort. That's going to be a lot. So one of the ways to cut the corner on some of that necessary research and get it started is you figure out what your priorities are. My first priority is to go through my spacecraft and make sure all the safety functions are accessible to everyone. So I eliminate things that I know are a problem for the first pass because I'm just interested in safety. So maybe then the second pass is everything that everyone else finds difficult to do already. So controls that are always hard to operate, doors that are always hard to open, all that kind of stuff that's already irritating, we could address that. And so I might start with those two, and then I might go to next things that have to be done frequently, so that I'm not looking at a flat data set, I'm looking at a data set that's already sort of usefully prioritized. And so when you come upon an individual that presents with whatever they present with, you're not always doing a bespoke accommodation and a bespoke medical intervention. You've already looked at the most common things, like we've already said. You've already looked at the most common things that you're going to have happen and the most common functions aboard your vessel and aboard your habitat, so that you have not only a place to start, but a way of advising your client, passenger, whatever we call those, because they don't know space and they don't know what it is they're going to need. There has to be a meeting together of sort of people who know access and disability, people who know medicine, and people who know space. You need all those three factors of people in the room, so that you are not, so that you have all your data in hand. And having done that a couple times, then you won't be trapped in this, we're doing bespoke accommodations all the time.
So this might be a little bit of a posing a question to the group as my answer to your question, Mark. I think there's maybe 4 elements to think about, and it's probably going to come down to what is the HSRB or a designee of the HSRB, describe. But I would say there's what are the space-focused biomedical risks would be one category, I think, to open a discussion on. Number 2 would be what are the opportunistic events like the one you described. Of now you've got an individual who's going to fly into space. That's more opportunistic if it's, let's say, Parkinson's disease, as someone recently did fly. Do we want to then run through the IRB a Parkinson's disease-focused investigation so that on top of, and this is how Track 1 and Track 2 were designed in parallel. Track 1 would, of course, be collecting all kinds of background comprehensive measures. And now if this individual was to fly with Parkinson's disease, now we can do gait analysis and we can do very specific Parkinson's-focused investigations as the hypothesis-driven portion of that. And then are there other, rather than diseases, so we could go back to what was mentioned, what are the most common diseases in the population? Should we be studying those in particular, let's say type 2 diabetes and the various other comorbid effects and polypharmacy that goes with that. But then there's a 4th question or a 4th tier, I think, and that would be, well, what kind of systems might we want to investigate? So rather than a disease per se, should we be looking at the cardiovascular response, right? The endothelial response, clotting behavior in space in a general way. So I'm going to kind of throw that out as a question to the group. There were 4 tracks that I mentioned, or 4 components that might be worth considering as we construct hypothesis-driven research. But what do we think about those 4 ideas? Are there other ideas that you would add on to those? But then in the course of prioritizing, how would an HSRB go about evaluating something like that sort of proposal? Do those 4 make sense? Do they not? But how would we construct research for each of those? And I'll just say, I think on the one hand, we have the opportunity to be very opportunistic, just as you mentioned, because when a certain condition, a person with a certain condition flies, then we have the ability to study that in great depth and get information we never would have had before. I think one of the beauties of having an IRB that's strictly focused on civilian space travelers is that it could look at that case rapidly, evaluate it with some sophistication and expertise, and then make decisions about how would we go about then approving a kind of hypothesis-driven research on that kind of an individual? So rather than that being an answer per se, I really am curious to hear, you know, what those in the group think about viewing it from that vantage point. It only is one vantage point, but I'm curious to hear what others have to think about that.
Yeah, you've described, I agree with you in principle, but you've described a very broad research program, a very expensive, potentially, research program. And clearly you can try to prioritize what the major medical issues might be, the major disabilities, different tracks, and then start doing research on those. But how do you systematically address opportunistic research? That's kind of an issue, right? Because somebody shows up with condition X that you've not seen before and you didn't expect to see it. You need to put something in place.
Can I answer that in this exemplary way? One example of that would be, what if we did targeted pharmacogenomics in everyone, and we decided that from now on, this was going to be a platform of study where in each of the missions, and this is granted different than the comprehensive measures, but if we were to say we're going to do pharmacogenomic profiling on everyone who goes into space, these are all targeted measures. Now we know the drug profiles that have gene-drug interactions, and then we have a option, which is always the tricky ethical question. So are we then just going to follow those people with whom or on whom we have pharmacogenomic data, or are we actually going to use that to tailor their drug therapeutics so that everybody is getting personalized and customized drug interventions, even though it's going to be wildly heterogeneous? And are we going to test a pharmacogenomic program in that way, not just at the observational level, but at the interventional level? And that's, again, another ethical question, an IRB question, and an HSRB question, and a community, you know, for discussion.
Yeah, okay. So we will open it up if people want to come down to the microphone and ask questions. Otherwise, I can go on pontificating for the rest of the hour. I don't think you want that.
Well, I think we talked a little bit last night about the challenge in front of us. We want to cast a broad enough net where we can find out what we don't know, because we don't know all the answers, and so we have to have information to allow us to define what are the important parameters to measure and to track and to monitor. But at the same time, we're not a group with infinite resources, right? So we need to prioritize our resources on measuring things that we think will have an impact. And so I think that's going to be the tough challenge going forward, is to balance the fact that we can't do everything, but we need to make sure we capture enough information to allow us to define what are the important measures that predict health impact. So how do we manage this balance? And maybe the panel could comment on that.
Well, I think I just asked you that question, Jeff, so I'm going to wait for your answer first.
Yeah, well,
We need another workshop.
yeah. Well, and I think that having tools like what Jennifer Fogarty talked about, you know, lab on a chip, you know, having a large number of omic platform data sets that allow us to look at multiple parameters with less resources are going to be a key to that. And I think maybe, you know, Michael or Simon, you can comment on trying to get the most bang for the buck when we do make measurements. You know, the traditional things we talked about yesterday in the kind of the physiologic realm, we know certain things that have been important, but there may be other physiologic measures that we have yet to define their importance. And so we don't want to throw those out prematurely.
I think we need to engage with industry, not the space-related partners and usual suspects that we deal with, but outside of our field. We all know just how fast and how wide technology is spreading nowadays, so that there's bound to be some new technology and new capabilities in another field that we might be able to apply to what we want to do here, which will allow us, as you were saying, Jeff, to achieve a great deal more quickly than we would normally be able to do. And I don't know what those new technologies are, but they're out there.
Right, we're going to have to leverage the new technologies as they evolve and apply them and be nimble so we can utilize those as they come to the forefront.
But beyond that, it's that means to find them. I don't know whether many people here remember the platform Jeff Davis, when he was director of HRP, produced. It was a fantastic platform, not suggesting that's what we establish, but it was a means to enable individuals and research teams and organizations outside of our fields to understand what our needs were and to suggest solutions.
Yeah, and that's where this Track 2, Track 1 partnership comes to play, and bring those industries that are developing new technologies and new means to measure and bring them in and allow them to participate and synergize with, the kind of core measures that we're doing and to help us to define what we don't know yet and what we need to know.
So I'm going to ask you a question, Jeff, from one of your areas of expertise. So we've talked a lot about kidney stones in space, and let's just pick that one as something that hasn't happened in space with U.S. astronauts at the moment. It's happened after they've gotten back.
Mm-hmm.
But we'll just pick that as something that it's not necessarily at the top of the biomedical risk category, but it's a high probability in the population. So if we just picked something like that, how would you envision approaching something like that from a risk management standpoint, since it may be more prevalent in the population than astronauts? And you can tell me if you think that's the case. Would that be something we'd study deliberately, look at examining the risk factors, genetics, dietary impact, take a kind of a comprehensive approach to making sure that didn't happen in space to the best of our ability?
It's a great example. I mean, because typically professional astronauts are pre-selected to be non-stone formers, so they don't have this genetic predisposition as we know a large segment of the population do. That will not be true for spaceflight participants. So they will not be excluded from participating through the preventive medicine model like professional astronauts are. And we do know that there are a large number of factors that contribute from an environmental standpoint that might increase the risk in spaceflight for stone formation. And some of those are microgravity related and the liberation of calcium and phosphate from the bone and excretion in the urine. Some of those are dietarily related, and we talked about that yesterday with acidification and driving towards a pH and a potential solubility product that will favor the formation of calcium oxalate, for example, as opposed to calcium phosphate, which tends to occur in a more alkaline environment. So the calcium oxalate stones are driven by this acidification, and so there may be some dietary impacts and countermeasures like citrate, which complexes the calcium and reduces that solubility product, driving towards stone crystallization. So I think that we should definitely do a metabolic evaluation of these individuals before flight to look at their risk and maybe introduce potential countermeasures or dietary interventions, or certainly a hydration protocol. All of these things could be part of our mantra with HRP-C to help reduce the risk for these participants that we know are not going to be sub-selected to be non-stone formers.
So part of the mitigation there would be recognizing that it's a risk. It's still unknown as to how prevalent or how significant it would be in terms of the spaceflight context, but then doing everything you can, which basically, in this case, is an extension of terrestrial medical care, but just paying extra special attention to it. It's not exactly a research endeavor in the classic sense, but it is a countermeasure. It is a solution to the problem.
It's a combination of clinical research along with clinical care that we want to do, and we would use the two together to help provide a risk reduction technique for these individuals.
Yeah.
So then we're talking about a whole suite of prophylaxis, right? There's all of these earth-based countermeasures, where we could do these pre-mission analytics, understand particular kinds of risk, do as much as we can pre-mission as possible, understanding the mission dynamics going to change all of that. So that becomes, you know, not in-flight directed, but it's pre-flight directed.
And just like I would say the radiation issue, I mean, we know that there are certain risks for radiation exposure that are terrestrial. Those exposures go up in space, just like the microgravity in space increases the risk for the kidney stone. The radiation exposure in space flight is higher than terrestrial, at least from a background standpoint. And so we can use the data that we acquire from those that are participating in space flight, undergoing these higher risk environments, to help us understand the problems terrestrially and develop better strategies for mitigation in the terrestrial arena. Because there are going to be people in the terrestrial realm that will be at higher exposure, somewhat like spaceflight participants, from either the kidney stone situation because of their work in arid, hot environments, or because they work as radiation workers in nuclear reactors or in the military, or they're even involved with diagnostic radiation or radiotherapy. So all these people could be at risk and might benefit from the type of work that you're going to do in HRP-C to characterize the risk profile.
Yeah, can I just add one last thought? And I wanted to, Melchior, you mentioned something yesterday that I wanted to kind of jump onto, and then let's maybe talk to Chris. But you raised the question of cognitive decline in space, and so one of the things we've been looking at is the question of APOE2 genotypes and APOE4 genotypes, and I'll just quickly characterize those. So if you look at the APOE4 genotypes have a much greater risk of developing Alzheimer's disease and early on than the APOE2. So the question would be, well, if they have exposures in space, is that risk similar, different, or accelerated? And so one of the questions is, do we have any terrestrial evidence for one versus the other? So in the chemotherapy literature, we know that chemotherapy can induce pretty significant cognitive changes. So there have been several studies that have looked at the cognitive risks of chemotherapy in APOE2 versus APOE4 genotypes, and it is considerably different, and it's worse in the APOE4 genotype. So that's one fingerprint that says, all right, there's potentially increased risk there. Then we go to radiation exposures, so whole cranial radiation, et cetera. Definitely an increased risk to cognitive decline. Unfortunately, as far as we've been able to tell right now, there is no APOE4 APOE2 genotyping with regard to cranial radiation to be able to answer that question. So it remains an open question, an unanswered question, but it's probably the kind of question that an HRP-C might want to start asking is there a difference in the impact on cognition in space if you're APOE2 versus 4 or one of the intermediate genotypes? Because that leads to the subsequent question then, if that is the case, what about the informed consent related to that? But I think secondarily, and as importantly, are there countermeasures? If you have an APOE4, can we develop countermeasures that would mitigate that risk of an APOE4 genotype to some extent? And that's a much longer discussion, but it's sort of an opening way to think about this and the kinds of questions that we might want to ask about civilians going into space. You know, especially in a certain age group with an APOE4. You know, if you're 60, that might be one consideration, but if you're 25, does that accelerate it or is it immaterial? And those are some unknowns that we have right now.
So a lot of this comes down to the fact that until you fly the first person or the first set of people with a particular condition, you don't know. You will never be able to mitigate completely to the extent that we would like the risk before you actually fly somebody with that condition.
And we're quite blind
So they become
to that.
research subjects whether they want to be or not.
Yeah, and we're blind to that particular question at the moment. As far as I know, if somebody's done it in space and it's part of the medical record that we don't know about, that's a separate discussion. But as far as I know, it's not been looked at in space in a systematic way. But anyway, yeah.
Yeah, okay. Be sure to introduce yourself before you speak, Dr. Chris Mason.
Yes, Chris Mason, Weill Cornell Medicine. I really like the panel, and actually that leads into the question I had, which is, should HRP-C have a version of the longitudinal health assessment that's being done for the NASA astronauts? And it's come up a little bit in discussion, but I want to get the panel's thoughts on ways to implement that would look at some of these long-term risks, and also which will change, of course, over time. The pharmacogenomics databases will get bigger, the variant annotation databases will improve over time. So almost the idea of giving anyone who flies, kind of an annual report, an update on their genome, on their profile, if they consent for it, of course, but a way to view them as lifelong sort of partners in learning about long-term risk.
It's a great idea. I think a lot of spaceflight participants would be proud to be on such a database. I would.
Yeah. So far, same experience, yeah.
Yeah. Of course, consent would be required, and some would choose not to, but what a great idea. And it would really help HRP-C in the longer term.
On the other hand, we did hear from Dr. Fogarty that some of commercial spaceflight participants are not professional astronauts, and when they land, they are under no obligation to continue to participate in post-flight testing, and some of them choose to engage to different extents.
Yes, and
so is it, and my understanding is even professional astronauts, the NASA Astronaut Corps, they are provided with the opportunity to come and get an annual physical, and many of them do not take advantage of that.
Yes, and it's for the commercial crews, at least for Inspiration 4 and some other missions so far. Yeah, there's variable, basically ability to get all the samples you want for every study, because some are harder to get, some are easier. Blood so far is easier. Stool so far is the hardest, I'd say, in terms of compliance. People just don't like to send you stool, even though it's very informative. But in any case, it depends on the assay type and the sample type, definitely.
Yeah, but it is a great idea. It does start clearly impinging on the legal area of liability, and so maybe people don't want to know what the long-term consequences are.
I'll just add one thing. So, and this is a little bit jumping professions, I suppose. So I'm on the NFL Players Association Scientific Advisory Board and also the Health and Safety Committee. There was a longitudinal program, the NFL Players Health Study, that was implemented quite a few years ago now. And granted, they're part of a league and that's part of a union, so to speak. But the data that has come out of that has been astonishing, honestly. And so granted, those are careers that are longer. They didn't just fly into space once, for example. So I know they're quite different, but I just wanted to say that has been instituted elsewhere. And in that environment, the data that's come out of that has been really quite extraordinary with some really interesting surprises.
If such a longitudinal spaceflight participant study was introduced, and we've got our spaceflight participants ticking that in the box pre-mission, it's one extra little bit of leverage for them to actually do the post-mission related analysis.
Hi, thank you. Dan Clever I'm Professor of Strength and Conditioning at St Mary's University, but I'm currently on secondment to Physical Mind London working on exercise countermeasures. Is that better? Yeah, it is. Yeah. So, Michael, I did read the report. It sounds like I was in the minority, but so I have a very specific comment on the report, but something that I think is very important, and that by following that line of sort of thinking leads to a hypothesis, and a hypothesis that has very general import, and that thus has the potential to be very useful terrestrially. So the specific thing that I didn't like in the report, and that I'll briefly paraphrase, was in the musculoskeletal section. It says, during spaceflight, we're no longer required to work against 1G, and this causes bone and muscle to atrophy. That's not quite right. The stimulus to adaptation is the forces that are experienced by bone and muscle. That's going to be the predominant reason why we have deconditioning, is the absence of the force. And that is a consequence of there not being gravity, but it's not the lack of gravity itself that causes it. And you can see that in the data. So we know on ISS there is gravity. And equally, when we look at the deconditioning data, we see that there's not very much deconditioning of the upper limb because that's still got the same, a reasonably similar environment. Where there is deconditioning is in the lower limb and in the spine because they're not being pulled against a surface, and that surface providing the ground reaction forces, which are the stimulus to adaptation. And the reason why that's important is, okay, if we're thinking about why do people decondition, what we need to be thinking about is what are the forces that are experienced by that system. It's not simply there's an absence of G, it's that there's an absence of force. And I don't think that that's something that we engage with well. And there's very profound questions here about the mechanobiology of adaptation that if we're going to do countermeasures really, really well, we need to engage with. But when we engage with those questions, that gives us information about mechanobiology that, yeah, is pure basic science and that can then help our interventions terrestrially. So it's a question that's not important particularly, or not as important terrestrially because the presence of G and the presence of a surface that we're being pulled against does give our musculoskeletal system this loading. But it's a question that becomes very, very important in microgravity, but that in solving that question in microgravity, it can give us insight that can have profound import for our interventions terrestrially. So it's quite a specific question, but it is focused on track 2. So
thank you. That's good because it's very relevant potentially to the design of countermeasures for everyone in space. If you understand the fundamental forces that you're talking about, we speak loosely about a zero gravity environment, a microgravity environment, and if you're going to do translational work and try to translate what you're finding in space to terrestrial medicine, and the opposite direction, you really need to understand those forces. Again, as Jennifer Fogarty said, every cell, every atom in the body is subject to the fact that you've changed the gravity environment. So you can't avoid thinking about that. To touch on another thing that you talked about, a real difference is, in my day job, I do vestibular research. So you cannot put a reaction force on the otolith organs like you can apply to other parts of the body, the musculoskeletal system, for example. That's why we don't have a good way to mimic either before flying the zero-G experience on the vestibular system or vice versa, any gravity extent on the otoliths except for applying artificial gravity. We don't have it. So there is a fundamental difference, and it has to do with the ability to apply the reaction force. So point well taken.
Thank you.
Thank you.
And before you go on to your other point, I just want to say, so that critical distinction, that nuance, please feel free to write that in a language that you're comfortable with, that you think is professionally defensible, because now the one thing I want to say about that document, there was a lot of eyes on that document, was recognize that it had to be limited in order to achieve a certain length. So yes, it will be deficient because of its natural status of having to be limited, but at the same time, we really also want this input to say, well, yeah, but this is too critical to not say it this way or to not include that. So feel quite free to say this one rises to that level that I think is critical to be nuanced, refined, or inserted if it's been omitted. So yeah, absolutely, that feedback is really welcome.
Thank you.
Schneider, NASA. I'm actually coming up to talk about some things that y'all already have mentioned. So the first one is that related to the two hypothesis-driven research, and the specific one of what happens if somebody pays $100 million and they have an unknown or an unusual thing. Well, terrestrial, we have a process that's called research of n equals 1, in which you do start with a hypothesis, and you could have a series of these particular research studies to be able to do piecemeal what you'd like to get And when you finally get enough N, then you'll really have the numbers to say statistically this is significant. But this is the way I think that you need to look at this, as opposed to talk about only looking at the monitoring aspect and say, what do we see about this unusual particular.
If it's unusual, how long is it going to take you to get what you consider to be a sufficient N?
Well, let's say.
How long is a person willing to wait?
So let's say that it has to do with other parameters that you're looking at as well. So as you're looking, you're going to tease out these particular things. So you may never get a particular thing, but if it happens to be something that is more common, then you will get the answer. I mean, it's sort of like terrestrially, we do this basically in cancer patients with N of 1 for treatments. And so if you have an N of 5 because it's a very rare cancer, you don't really ever get a good enough answer to say this is now going to be the treatment of choice. But you do get some information that will be helpful. And once again, this aspect is looking at hypothesis driven. And so that's what I'm saying. This is a way to at least approach that. Hopefully that will get us the information.
So can I address just one? You raised, so I want to address that point and then another one we talked about earlier. So in that scenario, let's go back to the Parkinson's, individual with Parkinson's disease that decides to fly into space. So one of the crucial things for the untargeted analytics and the targeted really is longitudinal serial measures, and a lot of them. And for example, we would typically do 3 to 6 pre-mission omics sampling and 3 to 6 post, or even more than that, and as many in mission as possible. But even on the targeted basis, so you could imagine somebody with Parkinson's who's maybe their clinical management hasn't used, let's say, a gait right device or something where they're going to monitor gait carefully, quantitatively over time. But there we might say, okay, in this individual, we'd like to get 20 measures of the gait right analysis before you fly, and we'd like to get 20 after you fly. So we've got a good serial baseline, a serial endpoint on a particular measure of motor function and gait and balance. And then we'd have that fully quantifiable metric to compare before and after. And that's how I see some of the hypothesis-driven work being done, then, to really tailor with enough measures so we're not just capturing 1 or 2 baselines, 1 or 2 endpoints, and we're not really confident about what spaceflight did to influence that. Anyway, what are your thoughts on that, Victor?
So I'm not going to go that, but I'm going to go to the next one that Chris brought up. And y'all's basic answer was looking at tourists and saying whether or not you should give them. But I'm looking at this is that there's going to be real workers that will be going up and down many times and will be servicing the tourists. And those are the people that what Chris's idea is excellent, is to be able to not only monitor them, but to give them feedback in terms of their potential health risk as well as what they're doing okay and how that's.
Not just hospitality workers, but people doing other types of work that's going to become more and more dominant.
Professional commercial astronauts.
Yes.
Can I ask a question? Sorry, where's Becky Blue? I'm going to put Becky on the spot, or anybody who's on the Spark committee. There she is. So one of the things that's happening right now, and Becky and I have had some great conversations lately, I think Emmanuel's on Spark and several other people, but this is about how the FAA might be engaged in recommendations, regulation, what have you. But what I'm going to pose as a question is, is there a way in the structure of what FAA is looking to do to create an incentive? So now I'm not saying regulate it, but to create an incentive whereby if you did participate in an ongoing longitudinal study, that somehow FAA incentivizes that. Obviously, Melker, you're going to have an opinion on this, but if FAA incentivizes that participation in some way, either through the individual worker, through the carrier, flight provider, what have you, but is there a mechanism where we can encourage through incentives that ongoing participation where we can continue to learn more about those individuals.
Without it being coercion, because it's a research study.
And that's always a fuzzy line, right?
Yes.
Every IRB has their own fuzzy number
Right.
for what's coercion.
Which is why we
or not.
should have our own.
There you go.
But let's let Victor get to his.
Yeah,
his
my third
final-
point, then I'll sit down so y'all can talk. So the third is in terms of hypothesis-driven. I think Sherry's talk this morning was excellent in terms of looking at the accommodations that are needed in a hypothesis-driven way. So first of all humans need accommodations for spaceflight because of the differences. And then you get into those people who need other additional accommodations because of one factor or another. And all these things, as Sherry and others have pointed out, is much more cost-effective if you can do it before you've bent metal and you have to change things. But currently, as we're starting out, we have these structures for each of the private companies, but they're going to be modifying, just like planes had modified over the years. And this gives a hypothesis-driven opportunity for doing such things as Sherry has suggested. Thank you.
Yeah, if we can provide them hard evidence that it's in their best interest to do it ahead of time, then everybody is better off.
Right, retrofitting is expensive and a waste of resources and takes you away from things that you could be doing. It takes more time also, so absolutely.
Hi, Bill Queel from Hopkins. I really appreciate the conversation or this notion of how the environment affects this emergence of, say, a disease phenotype or a medical condition, let alone how the environment, whether that leads to a disability, because in some environments those conditions can be assets. So I think that's really important to keep in mind. And then from a countermeasure standpoint, there are environmental countermeasures you can put in place. So, and I do this in clinical practice a lot, right? With my individual patients, I try to help them create the right environment that they can thrive and minimize the risk of some kind of emergent disease like diabetes or heart disease. Where I run into a little bit of trouble, and I'm curious how this will be dealt with operationally in spaceflight, is a lot of these conditions are common to multiple people. So for example, if I have a couple and I have a couple in mind, she sleeps better when the temperature is warm, he sleeps better when the temperature in the room is cool. So short of compartmentalization of some type, how do you deal with that there are certain common environmental conditions that are good for one person, not good for another? Is just an optimization issue for the system as a whole, or how do you even think about that?
I could start that. I think in general what that means is we haven't looked deeply enough into what each person actually needs and how they get it. So there's always competing accommodation needs. Right? Somebody wants a curb cut for their wheelchair, someone else wants more of a queue about when they get down to the street. So that doesn't mean the curb cut is a bad idea. It means that we haven't thought carefully enough about how we're going to construct that. So competing access needs are common. And I think, and it's just a opportunity to look more carefully at what it is each person actually needs and how they can get it. And maybe there are probably multiple solutions to all those situations, which isn't really an answer to your question, but it's an approach to an answer to your question.
That's great, thank you.
I like that question and the discussion because it's getting what Bill and I talk about extensively, which is that it's a systems approach. So if you're talking about accommodating the individual, that means potentially designing the vehicle, the spacecraft, the operation, the entire mission to accommodate the individual, and vice versa. The individual has to also accommodate restraints based on the engineering, but you should look at them as a combined system and not just try to figure out how to make it acceptable for the human at the very end.
Hi, this is Rob Lautsnyder from University of Michigan. I really appreciate this panel. I have actually two separate comments or additions. I was listening to Victor talk about the N of 1, and you and I actually were talking about that just before this. And so this is something of a research design thing that requires lots of frequent measures during whatever the exposure is. But I also want to remind us that, these one-off private citizens who are flying with unique health conditions don't have to fit into what we all want as researchers, our gold standard RCT design, right? There are other experimental designs where we can extract useful knowledge. It might just be a case study for now with lots of frequent measures that maybe eventually, looking at what might be an exponential growth of people flying, maybe eventually we will get a handful of them and be able to make more general statements. But there's nothing wrong with a case study for today and data banked for tomorrow. But that lends me to my other question, though. I hear a lot of really optimistic, well, maybe we can follow these people for a long time if we have to find some incentives to get them back. But I also heard yesterday, sort of surprising to me, about how many non-professional people are flying now and how this growth is just going to explode and we're going to get lots and lots of people, which as a statistician, seeing N grow is so exciting. But then when I think about the business model of how are we going to pay these people or fund these people or incentivize these people as the number explodes and we want to follow them longitudinally for a really long time. I know we're not all business people, but at the end of the day, when we submit our grants, we got to have budgets, and we got to think about this stuff too. So it's more of a comment. I don't expect an answer, but HRP-C needs to think about, gosh, if we're really going to try to be that optimistic in our long-term data collection of these people, like a lifetime surveillance of astronaut health type model, NASA has that long-going budget and that commitment to that astronaut's entire life. But I don't think we have that capacity. I mean, think of even insurance. Yeah. So
if I could just make a quick, not profound or anything like that, but I was at chairing a metabolomics society meeting a couple of years ago, and one of the guys from NIH came up, and we were talking about dried blood spot analysis, right? Simplifying the collection of blood samples in the field. And so he walked up and he goes, I got 50,000 people in my study. He goes, can anybody tell me a simpler method of collecting blood in the field from my 50,000 pediatric patients who he's following from birth until age 18? And that's what you're talking about. You're talking about a problem of scale, like a problem of success, and then once we've crafted something that's objectively intended to learn more, what if it scales beyond our reach? And if we had that problem, that would be extraordinary. But I agree, we're not prepared for a scaling event really just yet. Either not financially at all, but operationally, organizationally. And so, yeah, how do we build that scaling concept into the development of an HRP? Anyway, those are great points, Rob. Thanks.
Technology is going to have to come in to help us so that we can have more and more variables measured at cheaper and cheaper cost up to a point where it can't, in which case there's the balance, the resource cost balance. That's a higher end than we've been used to, but not as high as we want, and that's often the case, isn't it?
So I don't want to address your second point, but I want to talk about your first point just a little bit, and then we'll turn it over to George for I think is what's going to be the last question, unless there's one online. The first, but you and I have talked extensively about the different statistical approaches and the N of 1 studies, clinical observation studies, case studies, all those kinds of things. So applied properly, that does make as solid a scientific case as you can, given the material you have to work with. But it doesn't run the risk. It actually instantiates the situation that you're going to be then flying with people whose risk you have mitigated to different levels. And that's a potential ethical problem, because there are people you could say, you have this medical condition A, and okay, there's enough people who have that and enough people in the population, so we have centrifuge studies and we have parabolic flight studies and we have this and we have that, and we feel pretty good about this. We have this, and we've only seen 2 of these things in our lifetimes. We're going to, I don't know what we're going to do. We're going to measure you. Okay. But you're putting those kind of people on somewhat equal footing because you've agreed to fly them both. So not that it can't be done, but there's a huge continuum there. And then you're going to have people coming in and saying, well, what about this guy? You didn't know anything about that medical condition, and they flew. Why can't you fly me with my medical condition that you also know nothing about? Slippery slope argument.
And I'll just add one quick one-sentence point. And how are we going to confound our own research by optimizing, personalizing, stratifying the intervention so that they go into space in an optimal state to as best as the clinicians understand it? But now we've modified our own ability to answer the research
By
question.
definition, doing something that no one else is going to be doing. And but it's the only acceptable approach. Okay. Oh, I thought you were going to answer that.
Let's get a committee.
Hello, I'm George Pantelis from the University of Louisville. I've dealt with IRBs as a PI in many different situations. I always tend to submit the most challenging protocols and have interesting interactions. And that brings up the thought for our discussion of what's the composition of your IRB and what's going to be the way that IRB is going to operate in two things. Sherry has mentioned to us several times today, as did Victor, understanding the research within the environment and context that it's going to happen needs to be an important consideration in the risk to the test subject besides just what you're doing to the test subject. And so have you considered in the composition of your IRB having representatives from the different spaceflight providers, because each of their spacecrafts is a little bit different. And that may influence the risk assessment of doing a particular procedure as a part of your proposed research protocol.
So let me address that. I see Tina was checking the schedule undoubtedly to see if there's somebody talking about the IRB later today.
Okay.
And there isn't. But the track 3, which is in the afternoon, discussion is generally about the organization and components of the HRP-C. So I will suggest that we defer that and make it somebody else's problem than mine.
So that's going to be the same answer to my second point.
Oh,
yeah.
Okay, good.
So I'll make it easy for you, Mark.
Yeah.
And that is, what is going to be the type of interaction between the investigator and the IRB? I've experienced very contrary and confrontational IRBs. I've experienced collaborative IRBs, which means that they are true to their regulatory responsibilities, and yet because this is such a unique position, people on that IRB might be able to make very helpful questions to take a concerning way that they've proposed to do their thing into an acceptable way, an acceptable risk for the test subject.
So can I take a
Don't
quick
answer
stab
that
at that?
question. No, you have to wait until the afternoon to answer that.
Yeah, okay. See,
That's
I told you.
Sorry, it's somebody else's problem.
See, that's why he's a senior to me. I'm
That's
just
right.
the
Yeah,
guy,
hardly.
the wingman.
But the clock on the computer says that we're out of time, and we're standing between people and lunch. So thanks to the panelists, thanks to the audience.
We will be starting after lunch promptly at 1.
Contributing to basic sciences. Are we ensuring safety? What is really the final goal of the research?
Every eye condition and every, all of that. Everything in the process. If we talk about functional disease instead of and like
Yeah, okay, there we go. Hello, friends. Those of you who are still outside, if you could start to mosey your way in here, we'll get started. And where is our control? Okay, great. Do you need to advance that, or can I do it from here? So, thanks everybody for these great day and a half now. I can't believe we're already winding into the finish line, but this has been so great to have everybody together. Appreciate all your input. I want to say again that if you have recommendations and suggestions, either from the discussion or from the document that you've read, please feel free to share those. We really want that to help make the program better in the end. One of the things that I wanted to do this afternoon, or that we wanted to do, is basically itemize track 3 and break each of those components down into their constituent parts, give a little bit of detail on each one of those. And what I was initially going to do is maybe give a bit of an introduction, but you've all seen this now, you understand the principles of what track 3 is really about, operations and programs. You could call it offices too, if you like. The ones in red there are really some of the ones that we will have special topics on or special individual discussions about today. And what I'm going to do is just stop my introduction here, because you guys all know what we're trying to accomplish in this section. But what I do want to say is I'm going to introduce Dr. Rick Kingston from the University of Minnesota to talk about the Adverse Event Management Program, which we really call the Space Health Program. But in the past several meetings that we've had where we've discussed this, and one of the recent ones was at the we introduced the HRP-C to the Spark Committee and talked about it. This particular subject generated a lot of dialogue, a lot of back and forth. Several of the flight providers had people in that meeting that had a lot of questions. And so what I chose to do is to give Rick a little more time, because that seemed to be a topic of a lot of interest for flight providers and clinicians. We won't really do a question and answer period, but it'll give him some time to explain more about what he does, incredible experience in the adverse event management universe, one of the biggest companies in the United States in terms of handling adverse events for Fortune 550 companies, et cetera. So I'm going to let him introduce what he says and what he does, but Dr. Rick Kingston from the University of Minnesota.
Okay, well, first of all, I just truly very appreciative of the opportunity to visit with you folks today. And I remember when Michael first called me and was kind of explaining what they wanted to do and what you're trying to accomplish with your health monitoring system. I was thinking about it in the context of what we do as a practice, and I'll talk about that a little bit. But it became evident to me that you have a product, and really what you're going to be talking about, what I'm going to talk about, is product stewardship. You hear me all right? Okay. So with that, just a little bit about our practice. First of all, we're an organization that's licensed by 3 different licensing boards. So we're licensed by the boards of medicine, pharmacy, and veterinary medicine. It's the only triple licensed medical practice that has physicians and pharmacists on the human side with veterinarians in the same medical practice, which is pretty unusual. And you can imagine that our morbidity mortality conferences, where we have all of them together, is pretty interesting as well. It's been incredible in terms of what we learn from our veterinary colleagues, and also what our veterinary colleagues learn from us. And as I'll mention in a second, we have one of only 2 animal poison control centers in the country. And the number one thing that pets get into, I don't know if you would realize this, but the number one thing that we get calls about in our pet poison helpline are human pharmaceuticals. And it's usually pets, getting into the bottle, they chew it up and everything else. So we learn a lot about what happens, and we use some of that information in terms of how we look at drugs in the human space as well. One thing that's very important to us is that we have a professional academic affiliations. We have a formal affiliation agreement with the University of Minnesota. I'm also an academic at the University of Mississippi in the National Center for Natural Product Research, which is an FDA-funded center of excellence dealing with botanicals. And also, dealing a lot with the safety of botanicals as we use them in the marketplace. The other thing is that, just to put some context in some of my remarks, we have over 300 corporate clients, some of the largest companies in the Fortune 500 arena, where we manage their adverse events. And any allegation of an adverse event involving any of their products comes directly into our medical call center. And we manage whether they come in by phone or whatever. Sometimes it'd be emails. There's all different forms of communication that we deal with. But we manage their entire adverse event reporting system. They have regulatory reporting for some products and not regulatory reporting on others, but we handle everything as part of their product stewardship. The other thing I think is important about this, and I'll mention, is that these companies, they look at product stewardship in a very holistic way. And I remember when we first got started in putting the product stewardship programs in place, the Household and Commercial Products Association is probably the highest profile. They represent all of the Fortune 500 companies and smaller companies as well in the consumer packaged goods arena. So we end up with these 300 corporate clients. We handle everything from toothpaste and personal care to pesticides, to drugs, dietary supplements, medical cannabis, the entire category. So we get to see all kinds of things coming in from all these different markets. And it really helps because a lot of times when you're talking to your colleagues in these companies, they're very siloed in terms of the way that they look at their particular industry or their particular company. And so what we can do is sometimes bring in a broader perspective in terms of product safety and how we monitor for product safety and how we deal with that. The other thing is, again, we have the expertise in human and veterinary toxicology and post-market surveillance epidemiology. So not only do we collect the data, but we analyze the data and give the companies information back in real time in terms of what might be happening with a particular product or an issue. We also provide regulatory support for adverse event reporting compliance in virtually all the regulatory agencies that have mandatory reporting of adverse events by corporate clients. And I always, when I talk about that, I always want to make sure people realize there's a big difference between mandatory reporting of adverse events as opposed to post-market surveillance. Those are two separate things. The product stewardship side is very important for these companies because they really need to know what's happening with their products, how consumers are using them, how they're being affected, and what they can do to improve the safety of those particular products when they're in the hands of the consumers so that they reach their maximum benefits without unintended consequence. And if they have unintended consequence, how do they deal with that? We also, I think, we're very proud of the fact that we've got a long-standing experience in this area, 40 years experience. I started off as the director of the Minnesota Regional Poison Control System. So I was the director of the center for a five-state region at the time. Learned a lot in being in the public poison center arena in terms of how you collect data. And I was on the design team that designed the current data collection tools that are used in the public poison centers today. And as I mentioned, multiple market experience in clinical risk assessment, and we perform health hazard evaluations to aid in determining the need for safety interventions, which could include recalls. So a lot of times when we get situations that come in, if it's a serious event and we think that there is a direct relationship between the use of the product and the event that's being reported, we may start taking a look at whether or not a recall is warranted. And recalls are incredibly expensive. You know, if you're a Fortune 500 company and you've got millions of units out in the marketplace, you have to be really careful, make sure that you get it right when you have some type of an issue. So we help them sort that out from a product safety perspective. The other thing we pride ourselves on is that we have a history of collaboration with U.S. and Canadian regulatory agencies on post-market surveillance science, policy, and regulatory implementation. So we've had the opportunity to help shape some of the adverse event reporting programs that the various agencies have put in place for various regulated products. So again, we get to just see a lot of different things in different markets, and I think it's helped us be a better practice and help our clients and our customers and their customers make sure that there are products in the marketplace and that that they are safe for use. When we first started the product stewardship program at the Household and Commercial Products Association, where I've been a product stewardship trainer for I think like the last 30 years, we have a program when new companies come on board or when new staff come in the science realm for these companies, they go through a product stewardship training. And when we first put the program together, there was a lot of concern about sharing of information back and forth and, the proprietary nature of that and so forth. And ultimately where we netted out and where the companies came from is that their view is that they need to collaborate on safety and compete on performance. And that was their guiding, rule in terms of how they would set up their post-market surveillance and their product stewardship. And this is the definition that we used in that. It's a company's responsibility to manage their operations and products, to minimize any negative impacts on their employees, the communities they operate, the environment, and customers who use their product. In my view, spaceflight is a product. You've got this experience, essentially, that you need to manage, and you've got a lot of different, interests in your community. I think what's so exciting about it is that you're all coming together and you understand that if something happens to one company and you have a major incident that has, heaven forbid, fatalities involved, it has an impact on every one of your colleagues and every other company. So it's in your best interest to collaborate on the safety side of it so you don't have those kinds of things. The other thing is that you want to make sure that you have a system in place to monitor for the unintended types of scenarios. And in that context, why is a post-market surveillance critical is that, and I think Victor probably summarized it best this morning, he says what he's most worried about is what he doesn't know. And one thing that I've learned in just being in the group over the last day, you know a hell of a lot about spaceflight and the conditions that it produces in humans and how they adapt to it, some of the adverse effects, and you're managing those on a day-to-day basis and doing a great job of it. When the former administrator talked about the fact that NASA's been around 60-something years, they were expecting that there was going to be a number of individuals having to be taken out of space because of medical conditions, and to date they haven't seen that. That's fantastic. But the challenge is as you start transitioning to have commercial space flight with consumers that have all kinds of things that come in and influence the safety of space flight, those are the types of things that you have to be concerned about, is what you don't know. And in that regard, you need to be prepared to discover the unexpected. And I'm always reminded of this particular article and what happened with the NIH. Many of you probably are familiar with it, with the Feeler ride, where they were actually giving this particular drug to patients in treatment of hepatitis B. And the animal study, actually the dog studies, looked pretty promising, so they got the go-ahead. They started putting patients in it, and then initially they started to see patients that had discontinued the drug actually start developing some significant neurologic signs and symptoms. And they just thought, well, this doesn't seem to be associated with what we would expect with this particular drug, so they kept enrolling patients, and then all of a sudden there was a delayed effect and people started dying with fulminant hepatic injury. And they were very forthright. They said, we simply missed the early signals. And that's the thing that you need to be keeping in mind, is what you're looking at here is the art and science of signal detection. And so when you establish a program and when you're thinking about how you put it together for your folks in your industry, you're going to have to design a database to manage the collected reports. And every company that I've worked with, they collect different types of information that's germane to their particular industry. But you have to have a data collection system and a database to manage that so you can mine the information that comes out. You have to design an intake system and policies and procedures to triage reports to appropriate designated staff department. There's going to be different ways that people might report adverse effects associated with their experience in space. You need to think about what is the best way to reach those people and make sure that they communicate back with you if something unusual is encountered, whether it's during space flight or after space flight. You have to train all company employees regarding adverse event reports so that your crew knows how to, and the folks that are administering the program know how to communicate with the civilians that are going to be in space flight. That's going to be important. You also have to have a system to manage and document all incoming incident reports from all methods of communication. So it may not be a single method. You may have multiple ways that people can contact you and your program and your surveillance effort to share information about what their experience has been. then you have to ensure, and this is a really important one, that all serious adverse event reports are evaluated in real time. It's great when you have the opportunity to collect data over a period of time and then analyze it later on, but you need to be able to also look for the serious types of events that you just didn't expect and be able to do something with that data in real time instead of waiting until you get enough information to start taking a look at it in aggregate. So it has to be a real-time type of system. And then transition from simply receiving reports of adverse events to establishing best practice post-market, in-market surveillance processes. And that includes the trend analysis, benchmarking, and signal detection. And that's going to be probably one of the most vital parts of the program that you put in place, is to make sure you use that data and do something with it. Because from a litigation perspective, as we heard yesterday, that's what the market is going to be expecting of you. And that when you have a robust post-market surveillance system in place, it has a tremendous impact on the perceived safety, and it also helps you confirm safety. So if you have a system that's so robust that more likely than not, if somebody was to experience something unusual, you want to have a system that's sensitive. It may not be specific, but it has to be sensitive to pick up those particular events as they occur. So when you think about what's an adverse event, you know, when the FDA gives their definition, it's pretty broad. Say any, an adverse event means any health-related event associated with the use of a product that's adverse. That's pretty broad. But that's what the agencies are expecting, is that you're monitoring for everything that comes in that has a health-related allegation, in many cases, of an adverse effect. So as I mentioned earlier, it's the art, the signal, or the science of signal detection. And in that regard, identifying potential product defects or safety issues resulting in adverse events that may require action or mitigation up to and including major program changes. And I add the program changes because you as a group and your consortium can make those kinds of determinations, and to the benefit of each company and also the companies as a collective. So just to give you an example, so if I'm looking at companies, say it's a dietary supplement and a OTC drug company, or maybe it's medical cannabis, for example, there's three things when I talk to the senior executives within the company. My first question that I'm going to ask them is that, what's the benchmarked and expected incident rate for any given product's adverse event reports? And are there systems in place to monitor significant deviations for minor, moderate, or major severity outcomes? You already know a lot about human conditions and the effects of space flight, but the question is going to be, how do you benchmark that, and how do you compare what your expected rates are, and also how do you monitor for deviations in what you might normally expect? I remember a few years back we had a case that came in where we had a company who were monitoring adverse events, and they had a supplement product that they were putting niacinamide in, and we all of a sudden started getting this rash of significant adverse effects, guys showing up in the emergency department, major flushing, which you would see with niacin, for example, and something just didn't add up. And so when I took a look at the reports, decided to call the director of quality at the company, and I said, Tom, I think that there's something going on here. And he says, no, we see this all the time. People complain about flushing. I said, no, this is different. He said, okay, well, I'll check it out just to make sure and look at our batch record. So 2 hours later, I get a call, and he says, you're not going to believe this. So the guy that was mixing that day, instead of taking niacinamide, he put pure niacin in super high concentrations. And so almost everybody that was getting that particular batch all of a sudden was getting severe reactions that they ended up in the emergency room. But they were able, because of the way that they tracked their sales, they were able to recall all of that product, get it out of the marketplace, and institute that within 24 hours. So the FDA, they would oftentimes use that as an example of what companies should be doing in terms of monitoring for adverse events. But again, it's thinking about context of what's happening when you get a report that comes in. So the other is the observed incident rate a true reflection of expected consumer reactions when using a given product, or are these reports simply background noise? The reason why this is going to be important for you is that as you start to offer in-flight, space flight services to the commercial market and to consumers and civilians, there's going to be a lot of background noise. Every surveillance system that I've put in place, if it's sensitive enough, you get background noise, meaning that there are other things that are happening that don't have anything to do with the product, but they basically are a concomitant type of event. And so being able to sort out the background noise from an emerging signal is something that's going to be very important. Then the last one is the product actually causing customers to have adverse effects, and how serious are they? Can they be mitigated? And if not, do they represent an acceptable or unacceptable risk? It's kind of funny, when I talk to people about, product safety and safety in general, if I ask for a definition of safety, I've got 100 people here, I'll get 100 different answers of the definition of safety, because it's a relative term. Safe as compared to what? You think about every cancer drug that we give, they're all identified as safe and effective, and safe for the intended use in that particular circumstance. So there are going to be certain things that, when you get indemnified for somebody, coming on your flight, that you can, talk about things that, might be an issue, but, indemnify that you want to make sure that you know what the expected types of things are going to be, and you share that information, and then you have a process in place to collect things that you wouldn't normally expect to see. So these are the things that I usually ask the company, and I oftentimes also take a look. I have 10 things that I ask them to look at. And the reason I do this, because after testifying in a lot of product liability cases, I know what the attorneys are going to ask when I get on the stand. And so, first of all, do you normalize your incident rates? It's one thing if you have one serious event in 100 bottles or 500 bottles, and it's a much different thing when you have one allegation of a serious event with 2 million servings. Big difference in those two scenarios. And that helps you kind of zero in on what's unique about the one case that you've got with the incident rate where it comes out of 100 or 500 bottles and so forth. Do you have a process to determine acceptable ranges and actionable variations? So if you've got a lot of data that you've already collected, you know how the space flight is going to affect astronauts, the crews, and the folks that are flying in the civilian ranks. But when you start seeing things that are maybe outside of what your acceptable range might be, have you set an acceptable range that are what we would refer to as acceptable adverse effects? So have you identified the accepted ranges and the actionable variations? And then next, determining expected events based on the toxicology and product design. At least in my market, what we're taking a look at is how is that product designed? What is the toxicology of the ingredients? And we also recognize when they do their placement studies, they don't study 1,000 people. They study maybe 60 or 70. But really, what happens is when that product gets into the marketplace, it's your post-market surveillance system, which is the safety net, because that's what your market population is. That's how many people are going to be using it. You're talking about thousands of people potentially. Then determining, identifying predictable events and their expected incident rates. As I mentioned, you've already got a lot of that information now. Have you benchmarked these predictable events and how frequently they occur? Because your consumers, your civilians are going to know what their odds are. What's the risk that you're trying to characterize for them? And then incident integrity scoring. This is something that we take very seriously. It's considered that most consumer healthcare product events are spontaneously reported by consumers versus clinical trial generated. When you get into that position where you're carrying a lot of civilians, you're going to get reports from civilians. And so you have to have some way to take a look at the individual reports and put some context around them and characterize what the risk is associated with that, and think about all the other things that could potentially cause the effect that the person's reporting. And we actually published our methodology in regulatory pharmacology and toxicology in 2021 in terms of the way that we assign the integrity scores for our individual cases. Then identifying the background noise or events occurring simultaneously but unrelated to product use. And again, you're going to have a lot of background noise. That's the nature of monitoring these types of things and having a sensitive surveillance system. And then identifying trends in low-scoring, unexpected events and considering potential relationships to product issues, in other words, sentinel events. In order for you to get the sentinel events, you have to get all the background noise that comes along with it. But it's actually going through those reports, figuring out how to stratify them into meaningful buckets so that you can look at the possibility of an emerging safety signal. Then we've got, for suspected sentinel events or deviations in expected incident rates, do the individual incidents represent, and I came up with just a smorgasbord of different things that we've dealt with over the years, because a lot of times when you talk to the company, they call up they've got an event, and they'll tell you, well, you know, our product doesn't do that. Well, yeah, it probably doesn't do that when it's properly manufactured, but what happens if you have a manufacturing breach? What happens if there is a contamination, pathogens or adulterant, either before leaving the plant or after leaving the plant? You know, like with Tylenol and cyanide, after leaving the plant in Chicago. Then direct but predictable or previously recognized adverse effects based on the inherent toxicology, pharmacology of the product or an ingredient, and essentially is it dose-dependent or not dose-dependent or idiosyncratic. Then we've got direct but previously unrecognized adverse effects of the product or an ingredient, and that be idiosyncratic. It's unpredictable in occurrence, but predictably occurring at a low incident rate within the population. And then secondly, long-term effects secondary to chronicity of use. So you're thinking about those types of things as being important. Got it. And then last, or a couple more for suspected sentinel events or deviations in expected incidence rates. Do they represent interactions with other things that they might come in contact with in the marketplace? And you can see some of here, including gene expression, which also is something that you've identified as a potential issue. And then last, not least, are the reported effects in any given category preventable? Can the reported effects in any given category be prevented, managed, and or mitigated? And this is where you can reduce your liability simply through disclosure, education, reformulation. Look at all these different factors to help you figure out how you can mitigate it with the customers that you have and the other stakeholders. So lastly, and I'm not going to go into this, we use a weight of evidence model. We look at whether or not there are events that are coming in. We looked at the standard factors of association, which includes expectedness, temporality, biologic plausibility, de-challenge, re-challenge, and confounding factors. And I've got a number of different ways that we look at that, but we oftentimes look at multiple streams of data. It's not just what we collect from the consumers that are reporting, but there are other systems that are basically collecting similar types of complaints that we might find as being important as well. So with that, key takeaways. Best practice post-market surveillance is designed to support innovation, ensure sustainability, enhance consumer safety and loyalty, assisting company and brand protection and stakeholder communications, and then implementing a robust post-market surveillance system is really the cornerstone of good product stewardship. I think you're in a unique position because you're right now looking at what your product stewardship experience is going to be, and this is going to be an important part of it. So I will end there. I hope I didn't go too far.
Thank you, Rick. Is this mic on? Or here, I'll just that one. Thank you. Great. So I'd like to introduce Dr. Chris Mason of Weill Cornell Medicine, who's going to speak to us about the human specimen biorepository. So, Chris, there he is. You want that? Thank you.
Thank you very much. All right, I'll bring up slides. Well, first, thanks to the organizers. Thanks to the invitation to come here and seeing a lot of old friends, meeting a lot of new friends. Okay, there we go. Let's go back. Okay, great. So I'm going to walk you through and try and keep it to, let's see the timer. You can start the timer. Keep it in a short vignette of some work that we've done, kind of the history of some work that's been done in my lab at Cornell, and also kind of how we got to where we are. More recent work with the Inspiration 4 mission and some upcoming work with related missions, and then some of the data sets and protocols. And I was going to do a real-time live demo, but instead I have screenshots. But I'm happy to walk people through a demo of some of the platforms and ways to access some of the data that's been consented for some of the more recent missions. So first I start with kind of how I got to where I am, just being a dorky geneticist getting involved in spaceflight, was we were selected as one of the teams to start to look at the twin study when Scott Kelly went up into space. And this was really our first foray into getting multi-omic medicine with, in this case, a twin astronaut. And of course, Mark would always say he's the handsome one with the mustache, but really they look very similar. But really, you know, this is my first experience working on a mission, and really great support from NASA and from the crews to help enable a lot of the cutting-edge science at the time, and also a lot of follow-up work, which I'll show you. But so one of the big questions, and since it's been published a few years ago, I'll kind of give you the quick highlight and then jump into some of the related follow-up work. But one of the questions we had for the study is we have, I think, for most of the things we discussed over the past 48 hours and what I think HRP-C will do ideally for the future is what changes in flight and how does it manifest across many modalities of biology? Do we see, of course, metabolites, genes change, we see changes in pharmacokinetics. But what we did in this paper is trying to look for things that move together in concert. And so in blue was the flight subject and in green was the ground control. and trying to see, does something not change at all? Is it flat? Does it go up? Does it go down? How fast does it recover? And I'll come back to these themes again and again. But one of the things that was surprising is, a lot of things went up, but the thing that was surprising that went up the most was that telomeres actually got longer in space, which was the opposite of what we expected. So this is work that Susan Bailey did, and then at the first meeting, nobody believed her, so then we validated it in my lab, and then we thought, well, how is it possible that normally telomeres shrink as you get age, the caps on the end of your chromosomes, but here they actually got longer. And so they wanted to follow it up with a number of ways to characterize with more modern methods these sort of sequencing approaches. So one of them was to see, of course, many things go up and come down back to baseline, but then we used what are called long-read sequences where you can get a single molecule of DNA or even RNA and sequence across really the entire genome and get base level resolution. So you can see each one of these fragments is a single molecule of DNA mapping down to the genome, and you can get exact fragments, and you can see where there are mutations, are there changes in telomere length, you can get epigenetic information, all this through the sequencing methods. And we did confirm and published a year later that indeed in flight Scott's telomeres got longer, but also you can see at the very bottom there are some more short fragments as well. So it seemed it was more of a complex story, but we did confirm it with this more recent method. And so this came out, but then we did additional follow-up work with collaborating groups, including Susan Bailey, to see, well, how common does this occur? And actually we saw in 11 other astronauts, it also showed up. So I'll come back to this a bit at the end, but it seems like it's a fairly consistent feature of spaceflight. And actually some of these metrics are now part of the CIPHER study as well at NASA. So that was intriguing, but I think the thing that was most striking to me and inspired some other papers was what changed the most dramatically upon landing, because Scott had really, he wrote a book about this. I actually wish that all of the subject of any of my studies wrote a book about their experience, because we could start to look for, he had a really harsh landing, so we could look for cytokines, for example, that spiked to the largest degree on the day that he got back to Earth. And you can see this is the timeline before, during, and after the mission, and these spikes are sometimes hundreds of percent or thousands of percent increase, particularly IL-1RA, or interleukin receptor antagonist 1. And you can see IL-10, IL-6, you can see C-reactive protein. Here's some of the known markers. In fact, we're starting to call in the lab IL-6 is the return to gravity marker, because we see it in actually so far in almost every study like telomeres. And so we're starting to see some signatures like these. But to get to some of the points that came up yesterday is like we see this in one subject, but how does this compare to others? So some of our first papers to start to put this into context relative to other crews was a year later, where we could see, and here you can see, for example, the flight subjects got in blue, and across 29 other astronauts, these are box plots that show for shorter missions, say less than 6 months in pink, versus his mission. And you can see in some cases, it's a lot of variability. You can't see all the details in the back, but what you can see is there's a lot of noise. And the main point you should take away from this is that every astronaut is a unique snowflake, or you could say is a unique version of something you'd cook up in the kitchen. Everyone is very distinct in their response to space, and this came up also with some of the exercise plots yesterday. But I think what's amazing is even if the marker that's the highest, IL-1RA, he's the highest that's ever been observed for any astronaut so far to date. But in other metrics for cytokines, these stress markers in the body, he was cool as a cucumber. Nothing really changed. And so even though he's up there for a year, by other metrics, was the most calm landscape of cytokines. So everyone, not surprisingly, after everyone here in this room listening the past few days, has a unique profile in spaceflight, and we see this for sure with some of these data. But clearly we need more data. This is, I like to joke sometimes the twin study was amazing, it was wonderful, it was collaborative, but it was one of the lowest powered studies in human history, right? It was, technically it's the lowest powered study, we have 1 and 1. But what we lost, I think in numbers, we made up for in number of assays, number of analytes, number of time points, and sort of the breadth of the study. But we need more data. Actually, we had a real unique opportunity when Inspiration 4 mission was announced, and we'd been chatting previously with Jean Mateus before the announcement that something was coming, and then when it was announced, it was a really unique opportunity to take some of these more modern methods and some of these same questions to an all-civilian crew, and then also worked a great collaboration with Trish, which I'll highlight in a second. But this was a chance to take an all-civilian crew, and so we activated an IRB that was, kind of we're calling this broad multi-omics protocol, clinical assays as well. And it includes, this is a slide that was quickly showed yesterday, but there's every modality of biology we measured before for the twin study, but as well as more modern methods. This includes cell-free nucleic acids, some of the metabolomics and proteins that you can see in blood, stool, urine profiles. I mentioned earlier, stool is so far the least compliant sampling of anything we get. Even when we got some of the samples back from the ISS for the twin study, we had blood tubes there at JSC, and there were stool samples, and postdocs were terrified of the stool samples, but were fine to go grab the blood samples. So I feel like you have to recognize all these analytes have real value in the body. But in this case, we collect everything we can, essentially, from these crews, as well as some additional analytes that have never been done before, in particular skin biopsies, as well as some other cognitive metrics and other environmental sampling, which I'll show you. So this is a kind of a chance to try this really broad study and expand in the omics direction. So one thing that did come up, and this is now going to be published hopefully in about 6 or 7 weeks, is that telomeres did indeed get longer, and even just 3 days in flight. And you can see the error bars on this are big, so it was only statistically significant for one of the crew members. But on average, the trend was maintained is that even if you're in space for just 3 days, that's enough to induce a telomere lengthening phenotype, which was interesting to see that it was so responsive. Some other highlights to show you is actually, and this is actually some work directly funded also with Trish, is the first flight of the Apple Watch, as well as the first flight of the Butterfly IQ device. So in-flight ultrasound measurements, you can see of the bladder, of the interior jugular vein. The eye, you can see, was not as successful of a scan, at least. Again, this paper is in press, so it'll be coming out hopefully in about 6 weeks. And it's really exciting because it showed that you can bring some of these more modern diagnostic methods, or at least medical tools, into flight. And the crew, in this case, again, a civilian crew, that one was through lottery, one was announced, one was a billionaire, one was a cancer survivor, people that really just kind of came together quickly, could get briefed, trained, and get ready to actually go up into space and do science that had never been done before, and was really, I think, advancing the field very quickly. So it was great to see this, and again, this will be coming out soon. Some other highlights from this Inspiration 4 mission included the largest, to my knowledge, largest ever astronaut microbiome study. So we did basically 8 time points, 10 parts of the body, 2 or 3 assays per site, as well as the capsule before, during, and after the space flight, to see essentially where do microbes go, where do they change. One of my favorite studies in the microbiome space is Jessica Green did a study once looking at roller derby players. And so if you look at roller derby before and after they actually have a game, their skin bumps into each other. So their skin microbiome gets more similar after playing roller derby. And so if any of you play basketball, if any of you really play any sport, if any of you are in a crowded elevator, your microbiome may exchange with your neighbors more than you might want to know about. But it does happen. In this case, we wanted to see, well, in a capsule for 3 days, probably it's a very tight and confined space, how will this intersect with some of their blood work, their immune system? How will this, could we quantify and characterize the movement of microbes and sort of their overall dynamics? And indeed, we could, and again, this paper is also now in press, so you could see here some of the dynamics. So this is what's called a Circos plot, where each one of the thicknesses represents a species that's present within a person or moving between people. So this kind of shows you that we're all microbial jungle, and this is a continual diurnal movement of microbes between all of us. But in the case of the crew, you can see here the density. You can see the capsule up on the right of the Dragon capsule. You can see actually some people had more transfer to or from the capsule. Most of the transfers, though, were within a person. If you look at the specific SNPs of a species, you can see whether it moved within or between people. But some people did absorb more from the environment than others. So this is an interesting dynamic to visualize what happens in a space capsule. Same thing happens in space station, which we've also published. So that was one highlight. And if you want to see this particular species, you can see that within astronaut on the left, most things were within a person, but some species move between astronauts and even between the capsule and the astronauts during the mission, and it's highlighted in brown in flight. So it's interesting to see these dynamics, which are always occurring, but we can now actually quantify them much more precisely. Some other work that we did that's also coming out with this large package of papers is spatial transcriptomics. So you can take, we took before and after skin flight, biopsy the skin to see what happens actually at the surface of the skin. Do we see changes that are subdermal? Do we see any changes in the vasculature? There's a 3 millimeter skin biopsy. In this case, we assayed 18,000 genes, and this is one of the images from the paper. But we could actually see in some cases the melanocytes were disrupted, and even some of the macrophages started to move towards the surface of the skin, which has not been seen before. So there's another kind of a new feature from this expanded study. And a few other closing vignettes from the study is we're able to use single cell sequencing for the first time for this crew, and for one of the first data sets of its kind for single cell sequencing. So it means each kind of cell in the immune system, we could ask, which one is the most perturbed by spaceflight? All cells, of course, the whole body is affected by spaceflight, but if you look cell by cell, in the case for monocytes, dendritic cells, T cells, B cells, we could go a cell-by-cell examination of which were the most perturbed. And actually, the monocyte cell population, you can see sort of this block of gray is how many genes changed, and then the colored one is how many are unique to that cell type. That, many genes change in all of our cells all the time, but in particular, we could see that there was a distinct change there for the monocytes. They were the most stressed of any cell population. One other thing we did that was also new for this study was cell-free RNA sequencing. In this case, you take all the RNA that's floating in your blood, and if you sequence it as a window into which cells have recently died or are lysed or undergoing stress, And you can see you can see progenitor cells, monocytes, you can see platelets, but one thing that was really interesting from the study is also the hematopoietic stem cell population was enriched the day of landing and then after flight a little bit and then slowly tapered down. So we can see a bit of a stem cell activation, we think, post-flight, which also is a new feature from this study. So the last thing I'll highlight from this sort of package of papers is to comment more on the coefficient of variation, the variability between crew members, which has come up again and again in this meeting, and I think will come up again and again through all the different spaceflight participants and astronauts, is that if you look at different modalities of biology, you can see the coefficient of variation, how much variability between the crew members. It depends where you look. Is it proteomics or metabolomics? The metabolites and gene expression changes are by far the most responsive, but most of them also return back to baseline relatively quickly. But this shows us that each layer of biology probably has a distinct error profile or response to spaceflight. So this is actually, what's exciting is actually this is coming out in probably about 6 weeks. There'll be a large package of papers, and 24 of them were also used a lot of the data from the Inspiration 4 mission for follow-up work and validation studies. And then it actually is a lot of data, so the amount of sequence data, even though it was only about 1,200 samples that were processed, the amount of data generated is actually going to be about a 10-fold increase in the amount of human spaceflight data once it's released in about 6 weeks. And then it's also really exciting because I think as a concept, which come up in these last couple of days, is could this be something like a UK biobank as a model where you can look at data, you can look at samples, and this is indeed what we're planning on leveraging. So there is a bank that's been set up at Cornell, so this includes some coordination with Trish with some of the same aliquots there as well as here, and a lot of NASA astronauts, there's some SpaceX, some Axiom, and some Saudi astronauts, some international cohorts. This is a couple of screenshots. I want to close in the last few minutes with some screenshots of the data page and the resources that you can access in a few weeks. So one is these specimens. You can request very particular specimens depending on their aliquot type. We're all using some of the OMOP data standards which are used for a lot of things like the UK Biobank, so annotating samples based on other methods that people have used in the field. And then also taking lessons from other data cohorts and biobanks, things like the All of Us program, where Cornell is one of the recruitment sites for the US effort, like the UK Biobank, basically. And so there's also other cohorts you can see here, like phenome groups, pheno.ai. One quick note, I'm a member of the All of Us program, so my genome's been sequenced, and I can log in and see what it looks like. This is what my profile looks like. You can see here, Christopher, here's your DNA results. It's funny though, sometimes it thinks I do not like cilantro. I love cilantro, so it's not perfect, right? So every database it has its imperfections, but this is a learning experience because I think as if I can log in and say, no, I really do like cilantro, and it will change eventually. But this is data access is key, and so in the closing sort of couple minutes, some previews of what's going to be there. So a lot of the data that's going to become public is also accessible in the NASA Gene Lab portal. So this is some of the human specimens, the immune profiling you can see here. And there's also a data portal, so you can click and basically for any given gene, you can make volcano plots, you can sort between different cell types, look between different missions, and also look between some of the JAXA data, some of the NASA Twins data, and some other data sets, all in sort of one data portal that you can play with the data and follow up with questions or hypotheses in your own data. And there's also a cell browser. This is kind of a screenshot of the cell browser, so you can play with some of the single cell data. And there's a microbiome sort of browser. So by virus, bacteria, or fungi, you can track where they've moved between the different crew members in the mission. And then for the last future-looking ideas is actually more protocols being, more data is coming in from these missions, which we've heard about already the last couple of days. We are working on protocols for actually in-flight library prep and sequencing. So this is with the Mark 1C device, which is kind of a follow-up to work we did with Kate Rubins. We did this in 2016, and with Sarah Castor-Wallace to actually show that you could actually sequence in-flight, and so the library prep there is also ongoing to make it so you do it in-flight. We're including pharmacogenomics as part of the output as well for the crew members, and I'm adding that to the outputs. And then on a philosophical note to close, looking far ahead, keeping it 15 minutes, there's other ways you could do even epigenetic modifications of cells, so you could turn genes on or turn genes off if you think there's something that's at risk, some of the synthetic biology kind of applications and engineered biology. I think a model for HRP-C, and I want to bring it to everyone's brain, if you haven't already thought of this, is the Framingham Heart Study. It was a 3-generation and ongoing study that really set the bar for the field, and I think has been an immense resource for medicine and science, really for our country as well as the world. And I think this is a really good model, something to think about. So when we have future missions or other ideas, if we think of even something like a Krakow flyby, where in 18 months you could go visit 3 planets, first proposed in 1956, this could really be, when all this data that would come from a mission like this is something we'd want to all have access to and be able to leverage. And with that, in closing, I want to thank, first I want to think as a model. I think what we could all be like is maybe like the Avengers, potentially. Avengers Assemble, this could be all of us potentially. I don't know who wants to be the Hulk here, but this could be a model for all of HRP-C or Voltron. I know Jen was talking to Jen Fogarty about this. This is, if anyone remembers Voltron, does anyone remember Voltron? Okay, this could be a model potentially as well. Anyway, and also, and then closing, the last philosophical note is I think this is the most persistent and urgent question is, what are we doing for others, is what King said. And I think especially for people that we may never meet in grad students that will be born 10 years from now and what the field will benefit from when we look 50, 60, 70 years from now. So with that, I want to thank everyone in the lab that makes this work possible and is wonderful and inspiring. And of course, funding from NASA, coordination a lot with Ajay Mateus, Marissa Rosenberg from SpaceX, a lot of collaborators at Trish and other colleagues, and thanks for colleagues here in the room as well as Soveris and Michael. Thank you very much.
All right, thank you, Chris.
That's 16 minutes, okay.
So I'd like to bring up again Dr. Mark Schellheimer of Johns Hopkins. Mark is going to actually talk about the Human Systems Risk Board for Civilians. Yeah, thanks.
Okay, so right before lunch in the session that I was moderating, I threw out the question, partly as a lead up to this, but I didn't give you this particular answer. The question was how you organize, promote, start, design a research program based on medical conditions, disabilities, things that you may not know what you're going to be faced with. When you're, and also a lot of people potentially coming with their favorite issue that they would like to be addressed through research. So one of the answers, not the complete answer by any means, and this is going to raise more questions, as many questions at least as it raises solutions to that question, but one of the approaches is the equivalent of a human system risk board, HSRB, for civilian spaceflight, and this is stolen directly from the NASA JSC version of the HSRB. You've heard reference to that a couple of times. You've also heard reference in some of the talks to risks of different colors, green, yellow, red, in the NASA system. This is one of the boards that feeds into that delineation of which risk gets which color, which is actually not a gimmick. It's a very rigorous process, and I'll describe some of that and how it might be relevant to the civilian and commercial HRP situation. So the problem is, how do you identify and prioritize the major risks to human health and performance in an operational setting? And this is a key point in an operational setting. This is, we're proposing in the HRP-C just what the NASA HRP is, an applied research program, not a science program per se. Of course, you have to do science because that's research, but it really is applied research with the goal of maintaining people's health and performance, whatever performance might mean to a given individual in space. And this is relevant because this would, what I'm saying now, would enter into the deliberations of an HSRB. That is the role of the person who's flying. It may very well be that the role of the person who's flying, that person's performance, is to look out the window and enjoy the flight. That's valid. You have to address their medical conditions, if they have any, to a given extent that might be completely different from someone whose job is to go up and build a habitat on the moon or build a space station in orbit. So completely different things. So that's the operational setting part of this. So this is a description of the NASA HSRB. Now, I'm a little skating a little bit on thin ice here because there are people in this room who are dramatically and intimately familiar with the HSRB at NASA. One, at least, sitting up in the corner of the room, Eric, ran it for a while. Dave Bauman sits on the HSRB and attends it regularly. So presumably, if I say something egregiously wrong, you'll hear from them before I'm done here. But I think I have the basics right. When I spent some time at NASA about 10 years ago or so, and I would attend meetings of the HSRB as well. So this draws from that and also from some published literature. This is, by the way, all public information. None of this is a secret. So you can look up the guidelines, basically the operating rules for the NASA HSRB. The HSRB, this is the NASA version now, manages the process by which scientific evidence is utilized to establish and reassess, the reassessment is important, the postures of the various risks to the human system during all of the various types of existing or anticipated crewed missions. Okay, so some key points there, right? Postures, risk posture, they talk about risk posture a lot. The various risks, which means presumably you've identified the various risks. Well, that's part of the role of the HSRB. For the human system, during all of the various types of existing or anticipated crewed missions. In the commercial world, that would also mean the roles of the different individuals. That's kind of the different kinds of missions. So going further, identify and track the major risks to human health and performance in space, basically rewording the same thing. How do you identify the potential risks? A number of lines of evidence. Previous flight experience, that's the gold standard. If you've seen it in space before or it's caused a problem, then you know it's a space flight issue. Once you've factored out, parsed out what would be a bad situation on the terrestrial situations as well. Information provided by flight surgeons, what are they seeing that they can tell the research community, inform the research community? They have a seat on the board. Fundamental considerations of physiology. What are things that you might not have seen, but evidence leads you to expect you might see something. Kidney stones has not yet been a serious problem in the American program. Some evidence of increased prevalence after flight, but common sense and a good knowledge of physiology tells you that this may be a consideration, partly because of the environment. Each risk is assigned an L/C rating. I'll talk about that a little bit later. L/C, likelihood and consequence. Risk custodians, there's actually groups called risk custodians. There's a group of them assigned to each one of the identified risks. They update the risk ratings when they go to the board to have the risk ratings updated periodically. Not all risks, this is important, not all risks are allocated for research. The job of the HSRB is not to dictate that HRP perform research. The job is to delineate the risks and prioritize them. HRP's job is to pick up some of them and do research when necessary, but some risks do not need research to be mitigated. They can be mitigated through operational measures, or, dare I say, selecting who can fly. Nobody wants to get into that, and that's not where we should go either. But there are other ways of mitigating risks than just allocating research to them. And you can see some general idea of the membership. It's rather broad. Human Health and Performance Directorate, Human Research Program, it's an astronaut representative, flight surgeons, etc. So this is the basic idea of an L/C, likelihood and consequence. It's rated on a 5-by-5 scale. The NASA version has very strict, very rigorous definitions of all the numbers on the scale, but you can just imagine consequence of 5 means someone is likely to die from this. Likelihood of 5 means, I believe in the NASA version, it's a greater than 1% chance of occurring. And then it works downward from there. So obviously the idea of a research program would be to prioritize things that are rated red, turn them yellow if you can through countermeasures or mitigations of various kinds, and then turn them eventually green. Now, just for your reference, this is a little bit blurry on purpose because I don't want you to get involved too much in the details of this, which are not that important for this particular application. But this is the job of the Human Research Program. This is called the Path to Risk Reduction or Integrated Path to Risk Reduction. This is a listing of all of the risks that the Human Research Program is tasked with or has agreed to mitigate through research, and they're listed down the left-hand column, and it's a timeline over just about the course, the lifetime of ISS, and you can see that not all risks are created equal. Some of them, there's an anticipation through successful research that they will be mitigated, turned green, in time to do the next big thing, go to the moon, make a decision about going to Mars, whatever it might be. Okay, I think I'm going to skip that one. That's just a process slide. Okay, so how would we transfer this over to an HSRB civilian or commercial equivalent as a standing body that would play a large role in prioritizing and organizing the research or other mitigations that should be carried out? So the goal would be to provide a standardized, rigorous, and transparent is important here, the deliberations, some of which can take place in privacy because of medical privacy, but the actual mechanism, the way that the board goes about its business should absolutely be transparent. So everyone knows that they're being treated fairly if their favorite risk is under consideration. So standardized, rigorous, transparent mechanism for identifying, categorizing, and prioritizing risks. Risks here might include those tracked by NASA. You just saw them on the path to risk reduction. Some of the NASA risks, of course, might not be applicable to civilian spaceflight, and there are other ones that might not be applicable to NASA that will have to be added. In particular, a much broader set of pre-existing medical conditions, presumably, physical disabilities, presumably. Determination of new risks would be the first order of business, I would say, I would propose, in standing up an HRP-C with an HSRB, commercial version, civilian version. And in this case, and this is different from the NASA version, I would think that the HSRB in this case, the civilian case, would in fact essentially dictate the research agenda. That's because the HSRB here would be part of the HRP-C. The NASA HSRB, Human System Risk Board, is not a part of HRP, and vice versa. They are related. They're part of the overall Human Health and Performance Directorate. But HRP is not subservient to the HSRB. In this case, the HSRB would be part of HRP-C. So this would be my proposal for the set of critical tasks for an HSRB. Identify the major risks for civilian spaceflight participants as a function of the mission, the role of the particular individual, tourist, researcher, worker of some sort, and their health status. Prioritize the severity of each of those risks, likelihood and consequence. Probably have to redefine the L/C scale for this particular situation, this particular use. Delineate the status of each risk. May require research, might just need tracking and monitoring. In other words, insufficient information. Let's do some rigorous tracking and dictating or recommending the extent of that tracking and monitoring, including other things. Adopt a process whereby proposed risks are brought to the board for consideration. You don't want to open the door so wide that everyone who has a pet project comes to you and thinks that they need research money to pursue that particular thing, but you do want to open it wide enough that when people start to see suggestions of an issue, that they can bring it to the board for consideration. And the board could say, no, I'm not convinced. You need to go back and either find something else to work on or bring us better evidence. Provide for a continuous review of all the risks. The HSRB at NASA, I believe, tries to go through all of their 15 to 20 risks each year, more or less. Arrange for the dissemination of board findings and research monitoring results. So again, transparency. The idea is to get this out there. And then you can see my idea of what the membership should be. Leadership of the HRP-C, from the commercial flight providers, flight surgeons as appropriate, and a representative from the spaceflight participant, the flyer community. And I will stop. I will just give one advertisement because the next talk is going to be talking about directed acyclic graphs, which is one of the approaches that has recently been adopted by the NASA HSRB for putting everyone on the same page. So if you come in and talk about mitigation procedures, if you talk about the path from a spaceflight hazard like altered gravity through to making a claim that you have the potential to lose crew life or mission goals, you can track that through a causal chain that everyone has agreed to. Now, in the NASA case, there's a limited number of these directed acyclic rafts. In the civilian commercial case, there could be a very large number depending on how you parse out the different risks that you decide to take on. With that, I will stop. Thank you.
Thank you, Dr. Schellhammer. So next I'd like to introduce Dr. Eric Antonsen to speak about AI modeling and prediction.
All right. Thank you very much for the invitation to speak here. I appreciate it. This green, is that it? Oh, it's not me yet.
Now you are.
Okay, it's not me, it's you. I appreciate the opportunity to speak here. I ran the risk board for a number of years and rewrote a lot of the policies there because we struggled with these same questions that HRP-C is going to be struggling with. And as we learn how to do things better, we want to make sure that we have pathways and procedures that allow us to ingest new ways of doing business, new opportunities to use computer software, all that sort of stuff. And so when we think about AI, it's reasonable to ask, especially as we're in the middle of a rapid expansion of AI capability that is very public right now, how is that going to relate to the capabilities for spaceflight that we're concerned about? And when I look at the Moon to Mars objectives that are really focused on the human and biological sciences goals that NASA has as it starts looking forward, what the thing that strikes me is that these are all data management challenges. I mean, these are about information. And as a practicing physician, I work 14 shifts a month in a level 1 trauma center. To me, medicine is about how we gather data, how we interpret it, and how we decide what to do with it. And just because we're doing it in our head does not mean that's the best way to do it. And medicine is going to change because of all these changes that we're seeing very rapidly. And so when we think about where are we going in our horizon, I made this slide in 2018 and it's gotten a lot of mileage, right? When we're thinking about where we're going and with a commercial company that is talking about going to Mars, understanding those challenges, understanding those risks, informed consent, and how to approach what we prioritize are major challenges because it's going to get harder the farther we go. So the big thing that I really struggle with is the change in real-time communications because so much of what we do right now in terms of identifying, diagnosing problems, resolving problems is really managed on the ground in mission control. And so there's a bunch of different things that become much harder for us to do operationally that we have to help fill in the gaps with. So we use modeling a lot at NASA. We use it in a lot of places outside of NASA. For example, a few of these things, the NASA Space Radiation Cancer Model, that's some data from there that we published out in Zita Volinia's report, Safe Expeditions, that tells you, hey, how likely are people to get additional risk of dying from cancer for these spaceflight exposures that you're getting from what we know about the radiation environment. And that's what that is. That comes from a model that got transitioned to operations in 2012. Usually what you see is this information in, oh, somebody got a bunch of sieverts or gray. When you actually try to convert it to the clinical world, I think it makes it more interpretable. But there's a bunch of models that we use, and these are all examples, if I use medical terminology, of prognosis, right? We're trying to figure out what's gonna happen, because then we can reason through what we should do, right? Well, this is an example of some information from the integrated medical model. We made a bunch of assumptions, all of which were very rosy, by the way, and then we looked and mapped out, hey, what's the difference as we start going further and further along in length of exposure to the spaceflight environment. So that's kind of like when you get out to that right side, that 730-day and that 1195-day, those are the lengths of Mars missions. And Crew Health Index here is a way of assessing quality time lost. And at the top of that is 100%. You got a fully functional astronaut, and the bottom is 0%. And those two lines diverging, that's the difference between having a medical system that is adequately matched to the things that happen in order to treat them, or completely inadequately matched. And the difference between them really is about the knob that we turn on how we design the medical system, how well we match it to the problems that are going to come. So these things, the ways that we've used these in the past are trying to get us in the ballpark, right? In the ballpark of what is it likely to be like with a bunch of assumptions and caveats, right? And I don't have time to go through all those. But here's the thing, we can calculate all this stuff out and we can look and we can give you numbers for how likely do we, are we to wish we had evacuation if we had it on a Mars mission? How likely is somebody to die just from the medical stuff, not from the vehicle exploding, right? And when we look at some of the Mars missions, we get pretty concerning numbers up there. 1 in 90 is the same amount of risk that astronauts take roughly when they get on the space shuttle and they go up, and that's how much risk they have of dying from some vehicle failure. So now on a Mars mission, we're likely to lose somebody due to medical conditions alone at that roughly that same rate. But here's the challenge, right? Our data ends. And this is why we function in this probabilistic domain, because once we go beyond that 365-day mark, we don't have any experience here. Now we're extrapolating incidences and we're making a whole bunch of assumptions and we're relying on the methodologies that we have for probabilistic analysis. So what happens when we get beyond the data, right? Our predictions get worse. We have to realize that we haven't fully characterized a lot of things, the hazards, the human response to spaceflight. Even though we've been flying for a long time, as people mentioned, there's less than 700 people who have ever flown. So this is part of why resilience is so important, because we're going to be experiencing new things in these missions coming up. And you'll see my favorite definition of system resilience there below. The ability of a system to continue to, one, operate under adverse conditions or stress, even if in a degraded or debilitated state, right? While maintaining essential operational capabilities, and 2, to recover an effective operational posture in a time frame consistent with mission needs. So how do we do that? And how does this relate to AI/ML? Well, right now, we are using these things for prediction of what could go wrong. What we're not using it for is a number of other potential capabilities that are sort of on the horizon, and it's going to be up to us to figure out when they are mature enough to start pulling them in to things that we are trying to do. For example, clinical decision support, diagnosis, dynamic risk modeling, management of in-flight mission issues, right? And there's my thing, right? The loss of real-time communications. When we lose that, it's reasonable to ask if eventually this type of mission is going to depend on these capabilities. And I'm going to tell you why I think that. Usually when we're looking at all of the risk stuff and the human research program stuff, we're thinking about the people having pressure from the outside pushing on them and causing all these problems, right? This is the environmental challenges of spaceflight. But we forget that humans bring safety, that humans actually make things work. And when we've been running the ISS over the last 20 years, there's not a lot of advertisement about how much they've actually kept that thing functioning and running, not just the astronauts on the vehicle, but also mission control. And so humans have this that they are going to contribute to any Mars mission eventually, right? They're going to be the ones doing knowledge integration, causal diagnostics, anomaly response, time to criticality, right? All of these things are very human processing jobs of the information that right now is overwhelming. And what do I mean by overwhelming? Well, when we talk about performance, and we got a great comment yesterday about, hey, what are we actually preparing for? The cognitive function and performance needs to be good enough to make sure that they can respond to the things that go wrong in the time frame that it's going to go wrong in. So what's going to kill these crew? This is 20 years of information on the ISS, an analysis that was done looking at the anomalies, right? Anomaly is something happened, and we don't know if it was bad or not. And when you filter all those for the things that required urgent diagnosis because they were probably likely to kill the crew if they did not have an appropriate intervention and response within an hour, you get what's in the red bars. So about 1.7 times per year over 20 years. But if you're in the first 6 years of the ISS program, in the burn-in phase of the bathtub curve, you're closer to 3 to 4 times a year. So a 3-year Mars mission, just by this milestone, might have potentially 12 of these events where the crew have to actually respond to what's going on. And what happens when you don't have that real-time support? Well, you lose all this. So how do you take the function and the capability of mission control and stuff it into the brains of 4 people? You do not. It is impossible. And this is where AI/ML is likely to come in, not necessarily as generalized intelligence, but as intelligence augmentation, most likely. So when we talk about performance, right, they got to do this job. That task performance over there is really the thing we're worried about. We put them into spaceflight where it's orange over there. Some of the risks, things might happen. Their health contributes to their overall readiness, but they're not alone, right? They also have other crew that can help, that define a team. And then there's also how did you design the system? For a long time, when we have focused on risks, we've focused on this little area, the health of individuals and their readiness. But it's really a function of also sometimes people step in and do the job when somebody else can't. And then, even if you have a 100% functional crew, if you didn't bring all the spares, that treadmill probably isn't getting fixed, right? So it's not always about, are the humans the only part of this? If I take you into one of the DAGs, the behavioral and cognitive function DAG, and I say, hey, let's talk about that cognitive function, right? What is it that causes that cognitive function to decrease? Because that's really one of the big predecessors to individual readiness. And you can look around, and this is somewhat complicated, but really at a level that you could spend some time with it and interpret it, right? And you can go look at those other risks, those other things that we're looking at, and know intuitively that a bunch of those things are going to affect your ability to think and to function and to be prepared to do the job, right? So what happens if we map all that stuff out into one of these? Well, then you get something that looks like this. And we're not really capable of interpreting that with our eyes, and we need different ways of calculating and approaching these things that actually come from network science and other places. So this is where we learn from a lot of what's going on in other domains about how to use knowledge graphs, databases, and those sort of things in a much more productive way to approach risk. So those DAGs that you saw, that last one, that was really, that's all of them were approved by the HSRB after about 200 scientists argued about them for a couple of years. And they get updated. So back, again, what happens beyond the data? If you want to inform a giant graph like that with information at all the levels that people are talking about, then you need to be able to start doing the discovery science today in humans in spaceflight. And by discovery science, I mean measuring all the things, right? So there is going to be a limitation on that. That's going to be a balance, right? But understanding the science, the human and biological science, is how you inform effective countermeasures development. And we have ways to approach these complex systems now. We have ways that we didn't have before. So we use graph databases for a variety of reasons, right? Yesterday, JD got up here and said, good luck organizing the data, right? And I understand because I've seen the problems inside of NASA with data. But NASA is not a Google. NASA is not an Apple. NASA is not one of these tech companies that has already handled and created these types of things in the past. These solutions are out there, and graph databases are one of the things that you're struggling with in Excel is like, once you put all that stuff in, you got to make all the relationships. This is why we go to graph databases, right, to simplify that. So the AI in general, the applications, right, where are we in healthcare? Well, we did some things that were about rule-based learning, and we got to deep learning, and now we're in foundational models and generative AI, and there's a whole bunch of different things that starts to open the door for us on, including being able to assess what are the operational requirements if you want to do a precision space health system. And I can't really get a whole lot into this, but you can see that we published this in Nature Machine Intelligence. The thing that I want you to look at is adaptation. Dynamic learning methods agnostic to out-of-distribution data. What that means is if you train data sets on people on Earth and then continue to feed those data sets with stuff from space, in theory, you can actually create data analytic algorithms and AI approaches that can learn from that and modify, in a way that is consistent with the rules of physics, physiology. We're not there yet, right? That's what that news story from just a week ago says. We're really not there yet, but believe me, it's coming, right? We're learning. So a big part of this is, one, integrating software with onboard hardware for data collection, analysis, all these sort of things. For LSAH and terrestrial databases, making sure that the data management is fair, findable, accessible, interoperable, and reusable. We don't have to climb up the entire AI ladder to general AI. Intelligence augmentation takes us a huge distance for enabling a small group of 4 people to start to do the things that they were earlier supported by all those people in mission control. And we already have a lot of examples of places where we are leveraging terrestrial AI ML development in very specific ways in the healthcare sector that apply directly to some of our problems in spaceflight. The clinical decision support, handheld ultrasound pocket probes, like that's already happening. We've seen that. That's flown on SpaceX, using voice analysis and stuff to make things non-invasive. I mean, there's a whole bunch of different ways that we are creatively going to be able to address this problem. I'm going to skip that. There are a bunch of opportunities, but we also have to keep in mind reality. People, the astronauts, have not done massive amount of blood analysis in orbit. They just tested HemaQ up there. They flew to ISTAT a long time ago. They had some difficulties with comparison with controls on those, but most of the blood is brought back. If you're going to do an HRP-C, and especially leveraging commercial entities, doing something like self-driving labs is a reasonable thing, because if we don't do the science, we can't actually create the precision health systems that we need. And so this is critically linked for a Mars mission to the science that we do now in commercial spaceflight and to the moon. Populating and creating those databases and capabilities is critically important. And then just a real quick note on a couple other things, right? Digital twins, synthetic data, these are things that can potentially enable folks to start moving out of the domain of having to worry about PII, and especially federated learning. That's something that's happening at healthcare centers across the US right now, and when you do that, you start to bypass the concerns about PII. And finally, edge computing. If you really want to do this on a spacecraft, you have to be able to do this processing, bypassing the bandwidth limitations and stuff like that. So, all that said, these things are revolutions that are happening together. They are going to complement and inform each other. And I think one of our biggest challenges is that we oftentimes look at what we can do out of the knothole of what we are trained in and what we are good at right now. And if there's anything that to me is screaming for, hey, let's keep growing and keep learning, it is figuring out how to leverage these potentially massive capabilities to enable things we've never been able to do before, like a first human Mars mission. So please make sure not to forget to iterate and put those capabilities into your budget. All right, I'll stop there.
Thank you, sir. Thank you.
Yeah, great. Thank you, Eric.
Yeah.
And thanks to everybody who just presented here. These are just fantastic discussions. So one of the things I wanted to discuss now is precision medicine, and I won't get into the terminology because I know we moved from the term personalized medicine to precision. I wanted to start with a definition here briefly, essentially the science and practice of providing methods of treatment prevention tailored to the individual. In practice, it's generally been their molecular characteristics, so very much precision medicine and cancer and other fields have been focused on the molecular, but we also want to include these other phenotypes. In our case, it must be aligned to the operating environment, so we need to know more about the operating environment conditions than most people practicing precision medicine. But then the concept of stratification and personalization, and I know that's a little bit contradictory when we say precision medicine is about individuals, but we will find indications where an entire crew may share a need for the similar countermeasure because they have a similar genotype, et cetera, a phenotype of some kind, and then there's true individualization or personalization. But one of the things I want to say that it's an assumption, and I hope we can all agree on that, Eric alluded to it, many of the others have alluded to it here, and that is that there are many aggregating factors that converge together to influence the phenotype. So we're really talking about incremental gains and losses, and the types of things that we're going to look at as terms of interventions. If they're modifying the phenotype in small percentage ways, that can aggregate over several different types of measures or interventions. And so what we're really trying to do is avoid the scaling of loss of efficiency and improve the scaling of gain of efficiency, and often that involves molecular networks and physiologic processes. So the way that I'm going to approach this is not in terms of a concept or what would a program of precision medicine look like, but what I really want to do is use some case illustrations, because we could really say that some of the things I'll talk about now are the low-hanging fruit of precision medicine. These would be the kinds of things we could do today, but I want to illustrate specific cases so that we can get a better sense of these are. So I want to talk about drug-gene interactions with a specific example, drug-drug interactions, which is part of the low-hanging fruit, nutrition and metabolism, and then I want to finish up with our translation concept of the finding of the NASA twin study of percreosol and how we can think about how one might translate from that high-dimensional data in a small N of 2 cohort to a countermeasure or to a novel hypothesis. So I'm going to go fast because we want to stay on time here, but these are really straightforward principles that I want to illustrate. So the first one is codeine and tramadol. Some of you may know this well. We use a paradigm here of these 5 different categories where we essentially say if we want to use precision medicine in the area of drug prescribing, there's really 5 sectors that we'd want to focus in on, and one of those would be drug-gene interactions, drug-food interactions, drug-drug, drug-herb, and drug-nutrient. And those all can have a very pronounced impact on whether the drug is efficacious or whether the drug has adverse events. And one of the key things about these drug interactions is they're very often repeatable and predictable. And so that's one of the key things to take into the clinical therapeutics environment, is that repeatability and predictability. So we'll start here with the drug-gene interaction. And so just very quickly, you probably remember, if you do, the biotransformation process, but phase 1 is characterized by many things, but cytochrome P450, which is a term you'll hear if you're not familiar with it. And then phase 2 is conjugation, where there's a binding reaction to make the drug soluble for excretion. So we're going to talk a little bit about phase 1 here. So in phase 1, for the precision medicine side of pharmacogenomics, or drug-gene interactions, we'll talk about cytochrome P450 and each of the different isozymes. Phase 2 consists of a number of other enzymes as well that are obviously regulated by gene variants, and then the enzymes carry out their function either efficiently or not. And so some of them have conjugation nutrients, but I wanted to speak specifically about codeine then. So we're looking at the use of codeine and its conversion by a cytochrome P450 2D6, a very common enzyme. And codeine works, obviously, by the conversion to morphine. So we're really looking at to what extent is codeine converted to morphine, wherein it would have its clinical therapeutic effects. So let's look at the poor metabolizer. So that is the phenotype of the genotype related to 2D6. So the poor metabolizer converts about 10% of the codeine to morphine. Then we have the ultra-rapid metabolizer at the other end of the spectrum, which converts about 40 to 50% of codeine to morphine. Well, we would say that the poor metabolizer shouldn't use codeine because it doesn't work, and this is actually part of the Pharmacogenomics Consortium recommendations, as well as the US FDA, is that it doesn't work in poor metabolizers, therefore it shouldn't be used. So we could take that off of a mission drug list. The ultra-rapid metabolizers create too much morphine, and you can see from the symptoms here, those of you who've utilized prescribed morphine, those are not symptoms that you would want in a spaceflight operational environment. And so we would not want to use codeine in the ultra-rapid metabolizer, so we would take that out of the mission drug list. So the interesting thing is there's several other drugs like this that are metabolized by 2D6. One of those is tramadol, which you're all familiar with. The consortium does not say remove tramadol, but it does say reduce the dosage by 30% or more, so that's a little bit variable. But this immediately you can see, if we understand the genotype, we can look at drug-gene interactions and immediately start to think about it in terms of what drugs, and this is going to be a little bit hard to see because of the lighting here, but basically it's showing the frequency in a large cohort of pharmacogenomic evaluations. So the penetrance is sometimes as high as 90% if you look at different populations. And in some cases, you see here 30% and 26% carried 2 or 3 gene variants that would have influenced drug prescribing. And so this is from the standpoint of, and we'll just skip this here as well. So one of the ways that we've envisioned pharmacogenomics in spaceflight is that you can do a pharmacogenomic profile on every individual. So this represents one of the cohorts of ours where we've done a full pharmacogenomics profiling targeted using a company called OneOme. And what you can see at the top here is the cytochrome P450, 1A2, that's the one that metabolizes caffeine and other things. And then we go along the top here, and so essentially the subjects are in the row vectors, and we give a red, green, or yellow to whether they're a rapid metabolizer or slow or intermediate or normal. And what we can see here already, if this was an envisioned crew, that we already have a place to look in terms of a reference point for where different individuals fall. And I'm going to draw just attention here quickly to the 2C19, and then we'll go next, because this would be an example then, if that is a altered metabolizer of 2C19, this would be an example of what a report would look like in terms of these drugs should not be used in that genotype for these reasons. And so we would immediately, as we're developing a mission drug list, start to understand that certain medications would be preferred for that astronaut. Other individuals would be on the forbidden list. And some of them you just have to modify dose, and some you have to find a different drug. But this is now starting to become a guide for us, and this would be something that could be envisioned part of a research project for the HRP-C, but also part of a practice environment eventually. Now again, the HRP-C is not prescribing, but the HRP-C is doing research and perhaps giving recommendations. So this would be a mock-up or workflow that we've worked up for pharmacogenomic testing, and this is in a chapter we published, which I can share with you, and maybe, Jamie, we can send that out in the group list, but we've got a whole workflow for how you would do this with astronauts. So then let's go to drug-drug interactions, and we'll go quickly through here. I'm going to speak to zolpidem, Ambien, because it's one of the most oft-used drugs in spaceflight. And zolpidem is metabolized through cytochrome P450 3A4. Many drugs are, probably half of the drugs will go through this pathway. So we've got the normal trajectory of zolpidem when we're prescribing it for sleep. But one of the interesting things happens is in a study here, they gave clarithromycin, which is a 3A4 inhibitor. So what happens to the half-life, what happens to the Cmax, what happens to the duration of symptom management if you're inhibiting that enzyme? And this was a study that was done. They first loaded zolpidem 5 milligrams for 5 days and then introduced clarithromycin. And you can see that area under the curve, Tmax, T-half, and oral clearance all changed. And so what you could take away from this potentially is that if someone is using Ambien, they're going on an EVA or under some kind of a strong obligation of work in space, and now let's say an infection emerges, the clinician decides I'm going to use erythromycin or clarithromycin or another 3A4 inhibitor, they would want to understand that that would have the potential to prolong the zolpidem half-life and carry over its effects into the mission. And so these are the kinds of decisions that can be thought through and built in to a research paradigm, but also to a clinical paradigm. So nutrition and metabolism. Now this is going to be a little different because this is not in space, but I wanted to share something in particular here. So this is really a frequency distribution we did in an elite athlete cohort. So why are we using an elite athlete cohort for this spaceflight discussion? And the reason is we're looking at metabolic status, nutritional status, etc. However, this was an NFL and an NBA cohort, pre-NFL combine, active NFL players, and they all had full-time nutritionists and dietitians. So that's the context. So even though they're being given regular and constant care with professionals, this is what the patterns that we're going to see that show up. So this is a baseline value that we have on the omega-3 index. So this is a red cell measure of EPA and DHA. You see in the green shaded area should be the optimum. And we just have a couple of athletes in the optimum. So the ideal should be 8 to 10%. The mean here is 4.66%, but you can see some all the way down to 2%. Now this involves inflammatory status, bone metabolism, circulatory function, clotting. There's a system-wide implications for changes in fatty acid status. So that is pretty extensive deficits in that case. This is the AA-EPA ratios for arachidonic to EPA. The ideal should be below 3. That would be for most of the Japanese literature. A lot of the American literature might say below 5, but you can see here the mean was 29. And this has a heavy influence on circulatory function and clotting, inflammation, pro-resolving mediators, and a whole class of restorative repairing compounds. And so these would be the kind of markers that we might, for example, if we looked at jugular vein stasis and those individuals who were forming clots, would this be among the set of biochemical markers that would influence that? But we would certainly look to here as one potential contributor. We'd certainly want to consider it in model building. But again, it just gives a profile of the frequency distribution. This is vitamin D, and I think, JD, you mentioned vitamin D earlier. And in this cohort, the deficits were quite extensive. And this is looking at homocysteine. Now, I drew a different distinction there. If you look at most laboratory reference ranges, it'll say 9. But if you look at some of the cognitive literature, it says it should be at least 9, or I should say 11 for standard labs and under 9 for optimal cognitive function. And then iron saturation. So we proposed back in 2013 in our precision medicine paper that we should look at iron status and consider those with high iron status as potentially at risk to more adverse effects from radiation, basically because of oxidizing potential in situ. Here we found in a very elite cohort high amounts of a signal consistent with hemochromatosis. And genetically they tested out this way as well. And then finally, I want to talk about magnesium just for a moment. You can see here that low magnesium status, which we know has been an issue in space, is a very common phenomenon in elite athletes. And Melchior, you and I were talking about people operating in suits and the amount of perspiration at the leader's level that is lost and the electrolytes that get lost. Usually sodium, potassium, chloride are restored, but quite frequently we found magnesium is not restored nearly to the degree it should be, and it has metabolic implications. So if we go back to our metabolic map, and we start to plot this, magnesium is involved in over 600 different independent enzymatic reactions. If we use the others on here, omega-3 fatty acids, all cell membrane structure. Vitamin D, about 10% of the genes are involved with vitamin D. Iron, about 15% of the enzymes have iron as a cofactor. And then the whole inflammatory cascade being regulated in part by EPA and arachidonic acid. And just as I mentioned earlier, so we don't pick all of these signals up. If we go back to the untargeted versus targeted paradigm, we may not detect all of the off-target effects if we're using targeted methods only. So that's another value, is what are the metabolic effects of these aggregating deficits? How do they scale across metabolic networks? And so the multi-scale omics is one way to query that. So as a final paradigm, I wanted to finish off with, I think, some really interesting work that came out of our work with the NASA twins. And so if you remember, we found a signal. And obviously, back to what Rob and I were talking about and the rest of it, you know, if you find a signal in an N of 2 in a multi-omic study of hundreds of thousands of features, it doesn't necessarily mean much. So how can we begin to understand if it means something, and then what does it potentially mean? So paracreosol is the molecule that you see over here, and if you remember, we extracted the signal out of the metabolome data, but then paracreosol is formed in the gut by dietary tyrosine, so that's converted to paracresol. Cresol is absorbed back into the body, and it's distributed into the liver and then systemically. This is how it emerges in the body. And so if you look at this model here, you can see down in the colon here, one of the things that happens with paracresol, in addition to being absorbed, is it facilitates the growth of clostridial species and inhibits the production of butyrate species. So recall, butyrate is used for maintaining integrity of the GI mucosa, especially the colonic mucosa. It's the primary source of energy. So to be inhibiting butyrate producers is a really negative signal in terms of intestinal integrity, colonic integrity in particular, but it also facilitates the growth and is protective of clostridial species. Turns out the clostridial species are a major producer of paracresol. So what are the implications? And that's where, when I talked earlier, we said we want to get from features to pathways and networks to biological meaning, and then ask the question of whether or not this could be a new hypothesis or a new countermeasure target. One of the things that happens here is paracresol goes to the liver, and it has to be metabolized by sulfur groups. So you can picture as more paracresol is feeding into the liver, it's gobbling up sulfur groups that conjugate to it, and then it's being excreted as a paracresol sulfate. So picture now a lowering of the sulfur pool in the liver. We have all kinds of normal metabolites that have to be metabolized by sulfur conjugation, and drugs like acetaminophen. So we already know that when you give acetaminophen to somebody who has high levels of paracresol, that their acetaminophen sulfate levels start to fall and fall and fall and fall. The acetaminophen glucuronide levels climb. So what it's essentially saying is it's leaving more acetaminophen to go down this pathway down here, the 2E1 pathway, and form this toxic intermediate called NAPQ. So we all know what happens with acetaminophen poisoning. Go into an emergency room. If a person is sulfur depleted, they have real hepatic risks. They immediately give them N-acetylcysteine in an emergency room because those sulfur groups have to immediately be restored. However, now we have potentially a marker in space that's impairing that sulfur pool. And again, we're still saying it's a signal, but we're going from signal to mechanism to see whether there's something here important that needs to be followed. So our first look at this was, okay, it may have an implication with metabolism of some endogenous compounds, but certainly medication in the sulfur conjugation phase, that's an alert that we should keep our eyes open for. So then another interesting finding started to emerge, and that is paracresol seems to inhibit dopamine beta hydroxylase. And so that's interesting because it influences the conversion of dopamine to norepinephrine and epinephrine. So that would raise the question, is there any literature, is there anybody who's looked at the question of whether or not paracresol is implicated or it's found as a signal in Parkinson's disease? And the answer is yes, it has been seen in that environment. So as a final closing note on this, the mechanistic part of the discussion is here's what got really interesting. So we posed the question, to what extent does paracresol impact things like bone formation? Because then it would become particularly interesting in space. And so it does appear that it does have an impact on osteogenic progenitor cells, osteoblast formation and maturation, and calcium deposition. So to my knowledge, there's no human literature that has really answered this question. But the in vitro literature suggests that paracresol does have an impact on bone metabolism. So now we have a very interesting set of associations that warrant looking into a bit more closely. So here's the question. So do we have a novel hypothesis, or do we have a novel countermeasure target? Is it premature to even use the word countermeasure? So how would we begin to look at this? So first of all, we'd say, well, what are the analytes that would give us further information? So if we were going to test a new hypothesis, what would we look at? Well, we have the markers, right? We have paracresol sulfate, paracresol glucuronide. Those are the markers that we found in the twin study. And then we have glutathione, and that's part of the sulfur pool that's being depleted. Then we have nutrients. So might there be nutrients that could serve at some point as a countermeasure if we determine that this was actionable? That would be glutathione, N-acetylcysteine, and methionine. Now I have tyrosine up there in red because one might say, well, let's just reduce the intake of tyrosine because then we remove the substrate that the bacteria are acting on to produce paracresol. By the way, there's a lot of literature in the renal dialysis literature on this subject. So this is where paracresol is formed quite heavily, and it does have an effect on bone. It does have systemic cardiac and central nervous system effects. So then we go to microbial species. So this is part of what we're finishing up now. We have a paper that's going to come out in a couple of months on this subject. The initial paper is in bioRxiv, and we can include that if anyone's interested. But The full paper's coming out shortly in Precision Medicine. But essentially, we're looking at the metagenome, and we're looking at what the correlations are. But in principle, the well-known highest producers of pericresol are many different Clostridial species, Blautia, Robustia, and Olsanella. There's probably about 50 major producers, but these are by far and away. So these are the things we're looking at. So now, if we were to test a new hypothesis, we would be able to look at targeted metagenome analysis and ask the specific question of, are the pericresol producers changing? And then as we conclude here, so what are the foods potentially that we would look at as countermeasures? So in the literature that you see presently on pericresol on Earth, and like I said, a lot of it is the hemodialysis literature, we see that probiotics have been used and they reduce pericresol considerably. Resistant starch, quite dramatically. This is both in animals and humans. Inulin, which is an oligosaccharide form of fiber, and then high amylose wheat. So if we think about this contextually, we can say, number one, we found a signal. What we really need to do is repeat that analysis now with a targeted, fully quantitative measure of pericresol going forward. But we do have a target. We can look at pericresol sulfate and glucuronide. Now we can follow this in space. Number two, we've got a set of nutrients that we could consider. Number three, we've got microbial species that we could measure on a targeted basis. And then number four, we've got countermeasures in mind that we can already be thinking about. So the question is, and this is really a process question, then I'll conclude. So do we have enough information here to say we have a new hypothesis? And I would say, well, that's a fair statement, because we could easily just go measure on a prospective basis fully quantitative pericresol, and we'd start to gather that kind of data, and then we would begin to understand whether there's a persistent signal and whether it's repeatable. So that would be a yes. We also have some other markers that we could track, because there's a very clear association between the microbial species in pericresol, especially the Clostridium. So we could measure those. We want to understand the sulfur pool, and obviously this is more interventional in terms of this fourth quadrant here, but we certainly have enough to test a novel hypothesis, and you could argue that's important going forward. The other question is, well, is there anything here that warrants describing a countermeasure today? And probably most people would say it might be premature to describe a countermeasure. But would one want to make sure they had adequate sulfur pool going into space, just as one protective measurement? Or would they want to make sure that they had additional N-acetylcysteine in the diet going into space, just as a protective measure? And that's for further discussion, further debate. But I wanted to close with basically saying, the multivariate analysis is very complex. There's a lot of patterns that emerge. Some are noise, some are real patterns. When you have a signal, what do you do with that signal? And what I really wanted to illustrate is, this is a signal that came out of this data set. But why were we able to see it? And this gets back to an earlier discussion, which is simply only because we had the 19 time points were we able to say there was a pattern here. Because had we had small numbers of intermediate time points, one baseline, one endpoint, two intermediate, we wouldn't really have had enough to say there's a signal worth looking at. So the value when we're thinking about multi-scale omics or really any kind of measure, the more longitudinal serial measures that we can get, the better, because it allows us to see more pattern in the noise, the big noise of these big data sets. And then we have to be reasonable about taking it from that feature selection down to describing molecular networks, down to describing biological meaning, till we get to really the question of, is there something here that's worth following up on, or is there actually potentially a countermeasure? And finally, is it of a nature that we want to accelerate this along? And so to me, finally, where this came down to, we may need to accelerate this discovery process a little bit more, is when we started seeing the bone signal. Obviously, central nervous system, yes, but the bone signal now says, is there a hidden or nascent, molecular process that is also affecting bone in space? And I'm not saying the answer is yes, but we have some associations that are forming that tell us, yes, let's look a little bit more detailed there. So Very quickly. So this is really what we're describing, and Eric went to this. We're really talking about getting as much data from space as we can with these full profiling. And so we develop these data sets, and then when we get any new individual who's going to fly into space, we start to profile those individuals. They become characterized, those data sets end up increasing the scale of what we're doing. And just to add on as a final slide to what Eric was saying, so these data sets are really difficult to interpret as they get larger and larger. And we will need tools like artificial intelligence to help us do that, to find patterns. I think there's a clinical decision support role for artificial intelligence, machine learning, models and prediction, and then, as Eric also mentioned, digital twins. So I went just a little over there, but appreciate your patience on the afternoon here. I think we're going to a break. Yep.
And then we'll do Bill Quill.
Yeah, so we've got a break coming up until what time?
Let's take the break for 15 minutes.
Okay, 15-minute break, and then we'll come back, and Bill Queel is going to talk about the translation to terrestrial applications. So, thank you.
The discussion will have to be briefer. Yeah, it's not a big deal.
have to go, I have to teach tonight.
Okay.
Unfortunately.
Tonight? Oh,
Tonight,
my
no,
goodness.
it's the ridiculousness of teaching online. It still happens no matter.
Are you flying out tomorrow?
I'm leaving tomorrow at 2.
Oh, you're not flying?
Yeah, I'm busing tonight. So I'm leaving at 2-ish tomorrow. So I want to thank you for everything, and what's the best? Do you want me to fill out the form again? Just email people, like what?
You don't have to fill out the form. I think you already sent your stuff to somebody.
I did, but.
We'll keep track of it.
I did, but I've heard everyone else, and so now I have, I want to nuance what I said.
Oh, no.
I don't want to make it more coherent.
Rewrite it.
Okay, I do want to make it coherent because I don't want to make it a lot of extra work. And I'm really happy to help go through submissions. I know I offered to do the read through, and then one of my kids got sick and we couldn't do anything. But I'm really happy to be part of editing your document. I really genuinely mean that. And so how is that going to work? Are you kind of just, are we look at all the input? Are we getting a lot of input?
Not as much as I was hoping, but maybe after this we will. I haven't looked since I got here.
So I imagine there might be some people from today who are going to ask questions or say things who didn't quite get to it.
I agree. And there's also
Testing.
on the chat for the Zoom people that sometimes we just didn't have time to get to it. So we'll have to address that.
Right.
Zoom
Yeah. As long as somebody pushes the right button.
So thank you very much for coming, and it was a pleasure to meet you.
Yeah, same. And I really appreciate all the work you're doing. This really matters. It's going to make a difference. And I'm just grateful to be part of it. And I know it was so much work for you.
Yeah,
it's a lot.
When it became live, it became a lot. But I'm glad that you've gotten the opportunity to do the connections.
Yeah, I think it mattered. I think people made better connections. I mean, it's always, I always feel this. I don't want to go. I don't want to go to the thing. I think people know I'm there. I think, oh yeah, we have to do this stuff. We're still human beings.
But I mean, it's tomorrow morning.
Oh, is it? Oh, yeah. I missed that somehow. Just remind me or tell me.
Yeah, so there's going to be a tour in the morning of the facilities and what they are working on. And the researchers will talk to us about what their projects are. And yeah.
I would love to go there if I can. Do you know what time it is?
No, because they didn't send me the information. I'm going to have to get it from Paul.
Okay.
So I could forward it to
That would be great. I am really interested, Doug. I'd love to hear
Yeah,
that.
because you're here.
I am here. I have to probably on my way by 2-ish.
I think I need to be on my way a little earlier.
Yeah. So I'll probably be arriving before I get to them, checking out of the hotel.
So ladies, they're going to put my luggage in my car because I have a rental car. So you can do that too.
Okay, and you will have your car where we're meeting tomorrow morning.
Okay, so where are you staying?
I'm at the Holiday Inn.
Write it down because I will forget if I don't. That's all. And I got to figure out where the other people are, and I'll just be a taxi. You know? Yeah. And then we'll all go
Oh, really? Oh, okay. Okay. Yeah, and thank you for asking, and thank you for extending the invitation. I always find these smaller groups just way easier on my brain anyway.
Yeah, I agree.
So much. It's a lot. So I have an 8-hour bus ride. I think I'll just sleep the whole night. Damn it. That's my plan for tomorrow.
Get my plane and hotel
but you're a wonderful representative for the project, and we're lucky.
Thank you.
And by, I mean sort of we in a large group right now. I mean, this initiative really is going to work.
Yeah, good thing that my car just ran.
Yeah. Is he okay? Did he just zoom in because?
He can't fly. There's some medical reason.
Okay.
Yeah.
And he's smart enough not to do the 2 buses and 2 trains thing.
I don't know. But also his wife ended up having surgery this week. So, yeah, so he's been going to the hospital and missing some of the sessions. Yeah. We'll hear from him one more time at the end. He's going to speak over the Zoom.
Nice. So we are recording, right?
Yes.
So theoretically, so I can catch up on the ones that I missed
Yeah.
at some point.
Yeah. And we talked about, I'm assuming, that Oklahoma State University is going to transcribe what has been said.
Or they'll get a box to do.
Yeah, a bottle. Boy, I'd like to see the one from Michael Schmidt's talk.
Yeah.
It'll just be a bunch of
It'll just
gibberish.
be, it'll be, poor little bot. Poor little bot.
I don't think we should make it do it.
Poor little confused bot.
Okay, so let's see. You have email, and so I'll email you?
Yes.
Okay. Hello? I'd like to introduce Bill Quill, who's going to talk about terrestrial applications for the program, and we're referring to that as HRP-C.
Good afternoon. Thanks for having me. It is really a pleasure to be here and represent the terrestrial medicine provider community out there. I'm going to start and talk a little bit about terrestrial medicine because the fact is we're really not doing too well. We have this epidemic of chronic disease, which has been talked about here. In fact, most of us know these chronic diseases, but diabetes, heart disease, cancer, dementia, arthritis. These are very prevalent. These numbers got thrown out a couple times. CDC numbers, 6 out of 10 adults have at least one chronic disease, 4 out of 10 have two. What hasn't been talked about is the financial toll. They represent 75% of what amounts to be $4.5 trillion. So these cost us a lot of money, but they also cost a lot of quality of life and cause a lot of suffering. If you add mental illness to the mix, everything gets worse. 1 out of 5 people have some mental illness, such as depression and anxiety and PTSD. My guess is those numbers are probably higher. People just don't like to talk about it. 2020, 1.2 million people attempted suicide. Over 45,000 were successful. And a year later, 100,000 people died from a drug overdose. So we humans are suffering. What's the toll of all this? Well, we have about 34 million hospitalizations every year. It's been fairly consistent for a while. The cost of those hospitalizations is $1.4 trillion every year. Well, that's a 2022 number, but $1.4 trillion in hospital care. So I got to be thinking, about this, and I'm like, 0.1% of that number funds this whole thing like forever. It's a staggering, it's a staggering number. The other thing about that number is most people think about a third of those hospitalizations are what we call avoidable or potentially avoidable. So a third of that, what, $400 or $500 billion of care that is, I won't say wasted, but unnecessary. That's a ton of money that's out there. 36 million falls, 32,000 deaths. A lot of that stems from something called frailty. 1 out of 4 people suffer disability. We've thrown this number around, and I just thought it was fascinating. This notion of the disability is really relative to the context of the environment in which a medical condition occurs. I suspect that number is higher on some level as well. Again, $4.5 trillion spent in 2022. And here's another interesting number, $1 trillion estimate. I've seen this number from a couple different places. $1 trillion estimated in lost productivity every year. That says to me that chronic disease really impairs human function, which is something I think of great interest, or performance. Performance is of great interest to this group. So chronic disease is not good. All these numbers, though, they're not disconnected. They tend to kind of aggregate in some kind of temporal relationship, maybe causal relationship. We tend to go from states of wellness, which I'll just say feeling well, meaning not sick. That's not health, by the way, it's wellness. And for some reason, people end up in these chronic disease states that seems to predispose people to acute injuries and illnesses that often causes them to go into the hospital, which costs the system a massive amount of money. So I've asked this rhetorical question many times. Is there any way that we can mitigate the progression of disease and the subsequent acute injuries and illnesses and hospitalizations? So from a health system standpoint, a lot of people have been trying to solve this problem at a public health level. A lot of very good, smart people. I've had the privilege over the last 12 years of doing some policy work, a lot of work in regulatory compliance and quality improvement. So I kind of got some on-the-job training when it comes to policy. I just put this up there. This is the Affordable Care Act. This is just a timeline of implementation. I found this and it just showed me like, now that's a big statute, but these policies and regulations, there's just a massive number of them that have been put out, honestly, over probably 50 years. So again, not without effort to contain these costs, So how have we done? Well, here's a graph of national healthcare expenditures over the last 62 years. That's an unsustainable trajectory. That is just not, it cannot continue. It's about 17% of GDP. People can quibble over some of that stuff, but the trend itself says we have a problem. My opinion is that despite, with all due respect to my, I'm sorry, so where did the Affordable Care Act fit in? Here. While the ACA, I think, did actually do some good things, people have opinions about that, but one thing it did not do is have any effect on national health expenditures. So again, my opinion here is we can't regulate ourselves out of this problem. More regulations, which tend to be constraining, I don't think are the answer. We need good policy, not anti-policy at all. I think we need really good policies. I believe we need science to get us out of this problem. Everything I've heard the last 2 days, today and yesterday, everything, I think applies to terrestrial medicine. Now, I'm a primary care doctor, so I'm an internal medicine physician, adjunct faculty at Hopkins. I have a primary care practice, been doing primary care for 25 years. And I'm sitting here listening to all these talks and just saying, yep, we need that. We need that in primary care. We need that in terrestrial medicine. I think there's two general approaches to this, the way I think about it. There's this what I call reductionist approach, which I think could be considered a targeted approach or a hypothesis-driven approach. But we're going to focus on tackling diseases, specific diseases, particularly the diagnosis and treatment of diseases. But I also think there's an opportunity to take a systems approach, take a step back, look at the system as a whole. And it's not one to the exclusion of another. I think we can do both. As far as this more targeted approach, the fact is spaceflight operations have generated many advances in technology that have helped with diagnosis and treatment of disease. Here's a list. The ones in blue are specific to healthcare. We've talked about specific conditions, vestibular disorders, osteoporosis, sarcopenia, which is a component of the frailty syndrome. We are learning a lot, and we will learn a lot, and we need to continue to fund efforts to study diagnosis and treatment of individual diseases. But I think there's another opportunity here, and there's been conversation. In fact, I think I listened to these talks over the last couple of days, and I see this systems approach. People are looking at this from lots of different levels. The way I think about it is 4 components to this systems approach. The first is that we can incorporate precision medicine into clinical practice. The second is we can improve the resilience of what I call biosociotechnical ecosystems. 3, create a more coordinated network of medical providers. And 4, approach medical care not so much as a series of discrete events, our kind of payment system lumps medical illnesses into discrete events, but they're not. We need to look at them as a care continuum over time. So, this was to remind me that I'm not totally crazy by taking this approach. The American Medical Association put this out a couple of years ago. They also embraced taking a systems approach to both human health and healthcare delivery. So let me jump a little into the weeds here. So Michael Schmidt and Chris Mason, I appreciate your talks and Mike, our conversations. I agree. We need to be looking at human beings as complex, adaptive biological systems that emerge from the bottom up, from genes to molecules to cells to organs, all of which function together in this biological network to produce a biological phenotype. Likewise, diseases emerge up in that fashion as well. And then, all the multi-omics, I'm in on the multi-omics, the untargeted multi-omics in particular. And I'll tell you why. Here's like one of the biggest problems with me as a primary care doc. I don't know what I don't know. I can have a patient sitting in front of me, it happens all the time. I have a generally healthy population. Somebody comes in for their annual exam and they're feeling well, and I do the blood work, everything looks great, and then 6 months later they have a heart attack or they get cancer. So I'm missing something. I don't know what I don't know. Multi-omics is going to tell me that. But that's not the end of the chain, right? Because humans organize into families, who organize into communities and society as a whole. And it turns out that families and communities have a big impact on the health of the individuals, those constituents. In part, why? Because when we get sick, we need a network of resources to help us manage these injuries and illnesses. and families and communities often provide those resources. But it's even more complicated than that because this giant multi-scale system of systems exists in an environment of all kinds of exposures and stressors. And everything is interacting with everything else. This is what Eric was talking about. So we have these giant networks that all affect and converge at the human, who's the point of interest of ours. But I do believe with the DAGs and with the modeling that Eric talked about that we're going to start to understand resilience of this entire system and hopefully be able to improve it so that we can achieve an objective such as keeping people out of the hospital. And that's just showing whether you approach it up or down, it doesn't matter. They all converge on the individual human. Okay, speaking of networks, this is our health system is a network, a giant dysfunctional network of providers and hospitals and other facilities. You can see the entry point to here. This is somewhat directed. Oftentimes people enter the system from hospital emergency departments or specialists. Only about 1 out of 4 people have a meaningful relationship with a primary care provider. And I can tell you as a primary care provider, navigating this is nearly impossible for my patients. This isn't going to work in space. I suspect that people are going to say, maybe we should have this be a little more coordinated so that we can have some kind of initial entry point into this medical system. Maybe that's going to be autonomous, probably will be. It definitely will be. And then when needed, we can reach out to our specialists. And only in rare situations, will somebody end up going to the hospital. So I mentioned that we need to get beyond looking at these as discrete events. It's just the way the system operated. The fact is, it's my experience that there is a massive amount of information to be gathered in between injuries and illnesses. We tend to have a system where everybody just lives their life. You get sick, you go to the doctor or the emergency room, you get better, you go home, and then you live your life for a period of, I don't know, days, weeks, months, years, and then something else happens. We need to capture that. Our medical delivery system, I think, should be this, and it kind of is, at least those of us in primary care. If you start in the upper right in quadrant 1, most of our efforts are focused on prevention. And we've talked a bit about, what that looks like. But inevitably, despite our best efforts, chronic diseases will happen. We then mitigate those diseases as best we can, usually with lifestyle interventions, trying to modify that environment, those conditions that cause the dysfunction in the first place, or with medications. Appropriate use of medications is to compensate for some of these disease processes. But invariably, despite our best efforts, they get pushed over the edge. They get into acute injury illness, go to the hospital, we treat them, and then they go through this process of rehabilitation if they survive, and come back to a state of wellness, and then we can kind of reinstitute preventive medicine protocols. So I think of it a little bit more continuously over time as opposed to episodic and capturing all the data over time. I think about the fact that maybe we can short circuit this a little bit so we don't have to go, patients don't have to go through all this terrible acute injuries and illnesses, and maybe the research that you all are going to do can help us accomplish that on Earth. So let me talk about implementation. If I'm right, if there is, all the work that you're doing is applicable, and I argue that it is, how would we implement such a process? Well, we could disseminate those findings through traditional means, right? Peer-reviewed journals, conferences, medical grand rounds. But I think there's an opportunity here, and I'm a little bit biased in my experience in healthcare quality, but I think it's something that we could leverage. I'll spare you the details, but there was a legal case in the mid-90s that basically led to something called the Caremark Doctrine, which effectively required directors of publicly traded companies and health organizations in particular to have processes in place to oversee compliance with regulations. In healthcare, that included, and this was a bit unusual, quality care and patient safety, meaning that if a bad event happened and healthcare organization did not have these processes in place, they were going to get in a lot of trouble. So what this did, aside from driving a lot of fear in the directors of these companies, was it drove the creation of a lot of these very, very sophisticated and robust quality improvement programs. And it strikes me, having been chair of a board of directors quality improvement program, that we really could use your help. These are fairly disconnected from the research community. I really think this is an opportunity, and maybe it's a consortium of academic medical centers that agree to kind of work with this group. But I think that because they really need these, what they call process improvement programs or quality improvement programs, and all the data and the information is gathered from the work that everybody here is going to be doing is extremely relevant to their mission of keeping people safe in the hospital or their entire health system, and also having these oversight processes in place. So if and when, not if, when a bad event does happen, and people come in, they have shown that they've done all their due diligence. But one of the things I think this could work both ways. There's some reference to, there are some things done here on Earth that I think could maybe benefit the space community as well. Certainly inform research questions, maybe civilians on Earth serve as controls and case control studies for, rare diseases. But I think this can, I think this relationship could work both ways. And it struck me when, by the way, when Mark was talking about the Human Systems Risk Board, that is effectively what these board of directors do, these quality improvement programs. That's kind of the function they should serve. I can tell you they could really, really benefit from the lessons learned at NASA and the HSRB for civilians as well. On some level, this has already happened, and this actually just came out, but principles of aerospace engineering, particularly a systems approach, are actually already being implemented in some of these patient safety programs. So this is tangible. There's a real appetite for this in the healthcare industry, and I think we can leverage that. So in conclusion, our terrestrial healthcare system, it's broken, it's financially unsustainable, we need help. I believe research on civilians in space can help inform strategies for us to do a better job mitigating the effects of chronic disease or chronic disease itself, keeping people out of the hospital, and stop this massive consumption of limited resources. And I also believe cooperation between providers and the research community is the key to success. Thank you.
Yeah. Well, thank you for painting that rosy picture of the state of our healthcare industry. We're now going to have the general discussion about track 3. So if I could have Dr. Kingston, Dr. Mason, Dr. Shellhammer, Dr. Antonsen, sorry if I said that wrong, and Dr. Schmidt come up here. And that's a lot of you. That's the most we've had, so we're going to have a fight for some of the chairs. But there's a chair right there and one there as well. So as a reminder to everyone, track 3 was about the operations, programs, and capabilities. It's about the overarching organization and offices for the HRP-C. The different kind of subsectors of that were the space health and reporting systems, specimen and data repository, human system risk board, AI modeling, prediction and countermeasures, precision medicine, and then this terrestrial application. We didn't have presentations on it, but it also included an IRBC, physician continuing education, civilian training, preparation and contingencies, and food, nutrition, and metabolism. So again, this is a time for you guys to provide your comments, your questions, your remarks, and suggestions about track 3. So if you have something to say, feel free to come up, say your name and where you're from, as always, and keep your remarks as quick as possible. We don't have as much time, but hoping to have a robust conversation about track 3 here.
I have a question. Tina Beard from Ames. This is a question for Bill Quill. Do you know if other countries are in as dire straits as the U.S.?
Yeah, great question. Short answer is yes. We seem to be doing uniquely poorly around the world, at least in developed countries. We are 2 to 3 times as expensive. We spend 2 to 3 times as much per person and as other countries, and our outcomes across the board are generally either last or near last in kind of accepted outcomes. So that's in developed countries. Obviously, developing countries have different public health issues, but I've had conversations, or having more and more conversations about this need for every country. There are some countries that do it better than others. Most of those that do, Portugal, I think, Sweden, Scandinavian countries, anyone who does do it well, they do it because they invest in primary care. So we know that's the answer, we just don't know how to do it.
Please keep the microphone because it's a question for you too. About a number of years ago, Jim Bajan, astronaut, physician, when he left NASA, he implemented the first medical error prevention program in the VA the Veterans Administration. And that was based on what we do in commercial aviation sector. We have crew resource management, we have checklists. Every 6 months you go to a flight simulator, simulate all kinds of emergencies, and you have to pass that. You have flight inspectors, you have alcohol and drug detection programs. All of those have implications for medicine because we have issues on all of those in the medical part of the problem, particularly in the United States. So, and it became, if I remember correctly, within the first 2 to 3 years, they decreased medical error by about 25 to 30%. I haven't seen the transition to non-VA networks. But that was very successful there. So it is not reinventing the wheel. Those tools have existed for years, could be applied to other networks.
Great point. I know it has been. So at Hopkins, there's the Armstrong Patient Safety Institute. Peter Pronovost has been, I don't know him personally. I think Mark might. But the checklists in ORs have been a game changer and drawn directly from aviation without a doubt. I know Hopkins does it. I'm pretty sure that that's almost universal, at least in the operating room situation, and they've made just great advances. So great point.
I forgot one more thing.
Yes.
I know of a couple of hospitals that are starting to consider, particularly for surgeons, and in particular neurosurgeons, if there should be neurocognitive testing to determine whether or not they are still performing at the level they are supposed to prevent errors in surgery, particularly sensitive surgery related to. That has happened in some European countries. In fact, they have established age limits for physicians in surgery that after that age, just like pilots, after age 65 you can no longer fly. Some surgeons can no longer perform those functions. Is that something that is being looked here in your organization?
I have not heard that. But I think when you look at performance, physician performance, there are most of these quality improvement programs. They have, there's performance reviews, there's quality metrics that people need to meet. I haven't heard testing, but there's a lot of attention paid to physician performance in these health systems. So, and again, it's so analogous to other industries where the performance of other people's lives are on the lines. So again, if nothing else, there's a parallel, I think, to what's being done in aviation and probably space medicine as well.
So I want to add to this because I think this is one of those areas that if you don't start to parse out some of the data, you're going to overlook some of the major causes, right? There are plenty of people who have plenty of money who can get the best care in the world in the U.S. The reason why our metrics are so low is because we do crap worth for the bottom of the pile in terms of our socioeconomic investments. And I work at Ben Taub, which is a county hospital, level 1 trauma center in downtown Houston, Texas. I take care of the sickest, and by sickest, I mean people who do not have any access to primary care. We have an acute psychiatric ward in the emergency department. We have no place to send these folks around the city. It's a dumping ground from all the private hospitals who actually have all the money and resources to provide that to the people who can pay for it. So before we get to physician performance, which I think is an important aspect, safe nursing ratios, capabilities that are, bigger chunks from the healthcare system are things that need to be worked as well.
I'll just add one thing. I was on a QI meeting about last month, and there's a big emphasis on patient satisfaction, in part because hospitals get paid more money if people say they like us. So lots of efforts to make patients happy. One of those, which I just laugh at this point, is on the apps where people can get all their test results. The ease of access for patients it's amazing, but they get the results before I do. The displays that we do on the EHRs are very not intuitive. They're very laborious. I've gotten to the point now where very often I will have the patient hand me their phone and say, "Can you show me your lab results? Can you show me the graph? Can you graph? Oh, you can graph these 3 things and show me a trend line for 3 different variables at one time in 3 different colors on your phone? I can't do that on my computer." So the reason I say it is because I would say physicians are struggling. And when this came up and everybody was talking about how well their patient satisfaction scores are, how well they're doing, I said, "Does anybody measure physician satisfaction?" And the answer was, we've never even thought about it. We've never thought about it. So your question is absolutely appreciated, but I think we need to do a good job of kind of encouraging all of them, not just doctors, nurses, and techs, and everybody that's providing care to feel rewarded and to be supported in their work.
Sorry, that was, so a comment from one of our participants. We as physicians have to go through maintenance of certification annually. We have, no matter which group that you are in as a physician, you have ways that you have to get evaluated for these things on an ongoing basis. And so that aspect of things is done. Whether it's done optimally, I don't know, but certainly, you know, the burden of all the extra paperwork and administrative stuff that we probably didn't have to do before doesn't help us do our job better.
Fair enough. Hi, Dwight Holland. Mel, when you brought up the age of the pilots and the doctors, it made me think about, I've flown with a few 75-year-old pilots that I feel a lot better flying with in challenging situations than 55-year-old pilots, or even 40, depending on their status health-wise, emotionally, and everything else. And I'm speaking here, age is not, we all know this, it's not chronologic, it's physiologic. And we now, for the first time in history, I think, have reasonable tools to assess some of those things. It's a matter of whether we want to put the resources in it to tease it all out and then to implement it as sort of policy and guidance. And with the pilot shortage, Mel, you know, I'm sure you guys have been working on this really hard. There's been a lot of discussion about that. But the other thing about fatigue and how people handle that, and this is pilots and physicians, some people are more resistant to the degrading effects of fatigue than others. It's a little bit of genetics and how they cope with it, both pre-events, long events like 30-hour calls as an example we used to see all the time, or just what they've done in their life and the distractions they have going on. Some people, and there's Drosophila studies that show that some Drosophila, fruit flies, are much more fatigue resistant than others to certain things. And so I know surgeons that I wouldn't want to be on call with too long, deep in the night, and others who just like the ever-ready bunny. Take a licking and keep on ticking, right? And you've seen it, Eric, in the ER. You know what I'm talking about. So at the end of the day, some of this isn't just there's an age or there's a work hour requirement. If we really do this right, we have to think about individual profiles for like maybe longer missions or missions where a lot of fatigue will be absolutely required, you know, in specific situations. And Eric, your slide was fascinating. We saw this at AIAA too, about how it's that bathtub type of thing where early on in your mission, you have human interventions that if they didn't occur, we would have a serious accident or loss, and that the human intervened. And that's the good part of humans. It's a two-edged sword. You get a lot of good, but there's a little bit of bad in there, but tons of good when you look at the math. A lot of saves that didn't ever become true emergencies that were averted. But the thing that worries me from having been in these remote environments and flying in newer systems on occasion, flight test, is that when, and you made this comment, when they first come online, there's always that, you called it the burn-in period, absolutely true. And when if you go to Mars, after you get stable on the mission, once you then get there, if you make it through the atmosphere, the Mars atmosphere sucks because it's not thick enough to help you, but it's thin enough to kill you. I mean, it's the truth, right? So the point is, once you get there, there's a burn-in period, right, where you're going to have all kinds of possibilities. Your model doesn't include those. It was just the perfect healthcare model. But I'd like to know, since you've really lived with this data and thought about this a long time, for Martian operations, let's say, and let's just make it simple, the moon. What do you think the risks are beyond what you stated medically for a mishap to occur, assuming people are just people and they'll occasionally make mistakes or machines will break, and you can't immediately fix it because you've lived with this data. And I'm really curious what you think about that. I know it's going to be really wide estimate, but I'm curious.
I don't know how to answer that in a quantitative way, so I can give you a qualitative answer. And you know, when I was chairing the risk board, I had to spend all my time going across all the risks and looking at them and trying to understand them, and where possible, trying to get quantitative estimates out. And people haggle about, oh, how good is this estimate or that estimate? I think that we have done a disservice over the last, 20 years of really just talking about radiation as the big scary thing in the room for a Mars mission. And if you ask me, my number one risk that I think is going to kill the crew is the failures in human systems integration. And we have a formal risk for that we follow. In part because I think there's a lot of people who confuse systems engineering with human systems integration processes. I think that there is a very big bias against trying to do upfront investments for that, even though it is very well shown to decrease the back-end costs throughout the systems engineering lifecycle. And if I go down from there, I think it's, so human systems integration, because people talk about the unknown unknowns, but those are the known knowns. Those are the things that people assume somebody's taken care of, and then they don't get taken care of, right? NASA Standard 85, the human rating standards and the systems engineering standards, they do not put in a human systems engineering plan until SRR, Systems Readiness Review. So you already had conceptual development stuff all up to that point. And now we're asking for, in a Mars mission, the decrease in function, cognitive performance and other things over time because of the ongoing pressures of the spaceflight environment, but we're asking also for an increase in autonomy of the crew, right? They're going to be degraded. Oops. And the system is, how well are we going to design it, right? So HSIA, behavioral health risk, food and nutrition. We don't have a food system that can get us to Mars yet. Medical, and then it goes down from there. So that's I'm not sure if that answers your question, but I can't really give you like a great quantitative sense of that.
I didn't expect a true quantitative answer. I just remember accidents and bad judgments occur when you're under fatigue and pressured situations in exploration environments. I've seen that. I've been blown into the earback explosions in Antarctica. I've gone down in 00 in aircraft in Antarctica. And so things happen on exploration, things that aren't, they're just part of the chaos of being in the universe. But if we do good HSI like you're talking about at the front end, the back end cost is lower and the risk is much lower. It's not perfect.
I'll say we've done a good job at getting better at it because NASA used to focus, especially when it wasn't the Health and Medical Technical Authority doing the analysis, it was all on human error analysis, right? Human error rates, and not anything on, well, why did they cause or what led to that error? Right? So when you see what I put up there for that behavioral and cognitive function DAG, and it's like, hey, here's all these things that we know are factoring into this. We might not yet have the capability to truly quantify their magnitudes, but at least we have a starting point for understanding the complexity of the problem.
If you have a question from the audience, I have a microphone I can bring if you can't make it up to the front. Our guests that are visiting remotely can't hear when we speak from back here.
Thank you.
Or if you could just repeat the question for them, that would work as well.
Thank you.
Yeah, that was long.
Does anybody else on the panel have comments on that, or go to Simon?
So this comment, this thought, suggestion speaks to the civilian training element of Track 3. We all know that with regards to a medical emergency in space, if we've got a physician on orbit, that's much better than not having a physician on orbit. Government space flight at the moment, we can't get a physician on orbit all the time, so we have CMOs. CMOs help the situation a great deal. I'm a part of an association called the UK Space Life and Biomedical Association, where there's a lot of student medics, a lot of young professional life scientists, a lot of young docs and the like. If there was a course that was effectively a civilian CMO course, half of them would jump at doing that. If it's a course that enables them to be more qualified to go to space, there's a community across the world of individuals who are getting themselves high G trained, getting themselves zero G trained, etc., so that they are more qualified and would be picked more easily if there's an opportunity for them to go to space. This would be one of those items that sort of individual might do, but certainly the cohort I just mentioned would do. And then what we've got is, as the spaceflight participants are going up to space, a number of them are going to be CMO trained if there's a standardized curricula that we were able to come up with. And one would help with any emergencies in orbit if there's no physician up there, and two, actually would then be able to take our measurements, take our blood samples in a more standardized manner and help with the research that's going to be done for that particular mission anyway. So it's just an idea. I'm not saying that we need anything in detail here. I wanted to throw it out there. Maybe talk about a civilian CMO course that comes down the line to support the process that we're talking about.
I think it just graduated from a human research program to the Human Spaceflight Academy.
I think so.
So CMOs, just real briefly, right? When NASA sends up a mission that does not have a physician on it, then the crew medical officer gets a certain amount of training. That training has been provided historically by KBR. They've sent the astronauts through a number of different experiences. About 40 hours of training, includes emergency department, ORs, ophthalmology, dentistry, and a variety of other things. The intention of it is to get enough experience to be able to function with a flight surgeon on the ground to resolve issues, because much of the decision-making is done by the folks on the ground in medical, as well as for other aspects of the mission. So that's where the term CMO comes from when we're using it in this way. And then the question of what's the right training for that, that's a good question. I don't think that there's a standardized thing out there when we think about commercial space flight. In part, it's going to depend on the medical directors of those companies and what they think is important, and potentially an opportunity for those groups to work together on, hey, our responsibility for safety is all of ours, even though, productivity is competition.
Mm-hmm. Yeah, I think you're probably all familiar with the Wilderness First Responder Program, which is, the Wilderness Medical Associates is one of the groups that offers that training. There's other, but, it's generally been around a 7 to 9 day training as a first responder, and it's very tailored, obviously, to remote areas where there's, usually 2 hours from appropriate medical care. It would be interesting to see, and you're talking about a program that's similar to that, probably a little shorter than a WFR program, but that would be another example of established programs that of a certain duration that have been proven to be very successful. They recertify every 3 years because everything deteriorates without repetition. But I think the I-4 crew did their training in Ecuador. I think they got some wilderness first responder training down there, and so they usually do it in a wilderness environment. There's lots of simulations, lots of mass casualty stuff with them, and then so lots of drilling, very practical. It's associated with avalanche or marine or jungle, right? They tend to tailor them a little bit, but I can envision, and we've thought about that ourselves, having a program like that for those going into space who, because obviously the better prepared they are, the less that a crisis, if it were to happen, would adversely impact them. There would be sort of there's a triangle process of working through progressions of an evaluation that are system-based and that are pretty quick, actually. You can get pretty quickly from the first triangle to the third one, and that's just a stepwise set of evaluations of systems. So you can envision where a program like that could be really valuable. And in our view, the more of those people that you had trained in that way on a mission, the more responsive they might be to something off nominal or something that happens to the whole crew or to one individual.
Yeah, I think it's really interesting when you talk about going to Mars, though, we have a 7-minute communication delay and 14-minute round trip. We don't have that human on the ground that can back you up in real time. And so what are the types of, how do we adapt the programs that we have today to these new circumstances?
Well, and that's a good point. And one of the ways that this Wilderness First Responder Program, and I'm not saying that solves that problem, but conceptually, so you've got to get trained so that there's several things you can do in the field under that certification that you wouldn't do if you were an EMT. Because if there was a dislocated shoulder, if there was an open wound, an EMT would just stabilize everything, get them to the ER as fast as possible, and these guys would take care of them there. But if you're in the wilderness, the risk to perfusion loss and infection accelerates so quickly. You have so little time. So in the field, you would wet dress an open wound, right? You wouldn't dry dress it. You'd have to treat it as though you were now the one that had to make sure that person survived and that was going to be sterile. Or a dislocation, you'd have to fix that in the field because the perfusion changes would be potentially too severe if you didn't do it there. And so you can envision a kind of training where you'd have to assume they couldn't communicate, so now it has to be done by that person there. So that would be an interesting evolution of that kind of training.
This is something we have struggled with at NASA for a long time. Dave Francisco working on standards. There used to be a standard that said any mission beyond 210 days would be required to have a physician for that reason. Where does the 210 days come from? If you dig into it, it's because that's like was the certifying time for the Soyuz at the time or something like that, right? It had nothing to do with what the actual risk reduction was. And, you know, that standard went away, and it's an open question. Who would you bring? What skill sets do you need? And they're investing in a lot of research to try to understand that. I don't think it's a cut and dry thing, because even inevitably I go to every conference, they're like, well, what if somebody gets appendicitis? Well, the answer to that is actually that medical science and medical capabilities have evolved, and what you're probably going to do is put them on antibiotics. I mean, there's a lot of good data out there that says that you can delay surgical interventions. So it's not the question that people think it is anymore, because things are changing, right? When are we going to do surgery in space? I don't know, because the challenge around that really wraps up in how much mass power volume do you have for all the things that you need to support that, and what is the likelihood of good outcomes afterwards, as opposed to, yeah, go train people to do these interventions. When we get to the lunar surface and we have a permanent, you know, presence there, maybe that's the time. When we do these initial missions to another planet, probably not going to fit into the equation, right? And honestly, if you ask me who I would send to Mars, I would send 2 mechanics, 1 software IT guy, and a doctor. That's who I'd send. There's not even room for any science, because he's just trying to keep the damn thing working.
Very quick last comment from me on this topic. With regards to the matrix I was talking about earlier on, if you think about where the number of boxes, where the impact, if there's a physician on board or a CMO, that impact is sorted out, and there will be a whole host of boxes like that. That could help actually identify what the curricula would be for a civilian CMO physician or a civilian CMO non-physician, and having that matrix populated.
Let me just make one statement. Being a emergency doctor who practices very regularly in a trauma center, the most valuable thing in my mind that physicians can do is know when to not do something. I mean, I can't tell you how many times I've stopped my residents from killing somebody because they thought that, you know, they wanted to intubate this person and turned out they were just drunk, right? It's the experience brings that value to not do something and to not intervene when you don't have to. So
yeah, there's an old adage in wilderness medicine, and WFR means wilderness first responder, so the term is WFR for that reason. But anyway, there's an old adage is you want to know the number 1 cause of failing perfusion in the wilderness is a bad WFR. So it's basically, you know, not managing that person properly when you really, that has to be your priority.
I just wanted to get back to some basics, maybe with a little bit of balance. You know, when we talk about elderly surgeons or surgeons staying up all night, you know, Indy drivers would train experience for loss of reaction time. So there are balances there. There have been studies on sleepless nights, particularly in cardiac surgeons, and maybe that's a subset, like Dwight was talking about, but the results are no different. But the other thing is, remind all of us that fallibility is a human condition. We're never going to get rid of all of it. And you guys all know from the James Reason work and such that it's not just the events that occur, it's the system, as you've mentioned, and what we do about it. And from a human factor standpoint, every major aviation accident, every chemical nuclear accident has had 4 identifiable things. Every congenital heart operation that's been studied, 4 things go wrong. But a successful completion is not that the events didn't occur, but that the team identified them and rescued and got to the results. So there are balances here, and some of these are just the basic human factors things that the system has to deal with.
You know, we struggled for years in the medical profession trying to figure out whether or not we should be doing these 36-hour shifts like I had to do my intern year in the MICU. And then, you know, data came out that said, hey, that's a bad idea. And so they put caps on residency training hours, and then other data came out that said, oh, look, the number of handoffs that you do between teams now causes more problems. And it's like, you know, is it better to have the fatigued but person who really knows what's been happening throughout the entire day and night continue to work with that critically ill patient, or is it better to have the fresh mind who's catching up? we've struggled with these for a long time. And I think one of the biggest issues that we have in trying to apply medical models to things like these is that we don't take into account that fallibility. And we don't take into account the fact that no matter what we do, we're not going to drive the risk to zero. And that's true for spaceflight as well as it is for medicine. But accepting that has always been a hard part for us.
So I have a quick question. As the moderator, I'll use my power. So we talked a little bit about adverse event reporting, and how, particularly in the spaceflight environment, do you deconvolve the fact that things happen with things being caused by spaceflight, particularly when you have such a low number of data points. So you can't run like big statistical models on population on the ground versus population in orbit.
This is a super hard problem. And so when they passed the TREAT Act for NASA, which said that NASA was the insurer of last resort for the astronauts, they realized they needed to come up with some mathematical way to say, hey, is the cancer they get later in life due to spaceflight or not, right? And they ended up basically settling on a statistical approach that was like probability of, there was some specific probability that they calculated. And hey, you know what? If the chance that it was due to radiation in spaceflight is 51%, then we're going to give it the benefit of the doubt and we'll pay for that. But if the chance is below that, then we're going to chalk it up to all the bacon they ate, which, by the way, is also a carcinogen. And it's hard to separate out. What was the cause, right? We don't have really strong methods to do that. So we rely on these probabilistic approaches, and we try to develop better approaches. It's a weakness, right? We don't do well with that when we have such little data. So we're trying, we're learning.
One addition is just also, I mentioned briefly, getting more data context from other large-scale databases that have clinical and molecular and other metadata on the patient. So it gives you, anytime you see a perturbation of a cytokine, of any change that is in a medical record, it's very powerful to be able to say, well, how often does this occur? And is this related to a medication? A lot of you probably remember early days in COVID, there were, one example we published is it was thought that ACE inhibitors would lead to worse outcomes, and everyone stopped taking their ACE inhibitors. But then it turns out when we analyzed 50,000 patient records from EMR data at the hospital, between two hospitals, it was actually the opposite. So the first study that came out in March of 2020, it had only about 100 people, or like 90. And then when you've got enough data sets, it was a way to contextualize it. So I think that's true for like all of science, but definitely for any of the changes we see.
You know, one other thing is that when you're looking at the adverse event reporting system, the information, you have to remember that it's designed to be signal detection, not necessarily causality, especially if you're talking about the civilians who are going to be involved. So what your challenge is that you got to come up with a hypothesis. So that data that you receive, those reports you receive, you know, how frequent are they? How are they changing over time? You look at all these different factors that come together to help you make a decision as to whether or not it could potentially be a causal relationship. So you've got that hypothesis generating opportunity. And I think the biggest challenge I've seen with adverse events is somebody getting one and thinking, oh, I know what that is, and then they don't look anywhere else. And then all of a sudden they get 3 more cases and 5 more cases and 6 more cases and didn't have anything to do with what they originally thought it was. Basically, you've got a diagnosis that keeps perpetuating. You know, it's a circular reference. And that's one of the things you have to be careful about.
Yeah, I just would add one thing to that. So one of the questions I think important to that is it expected or unexpected? And then if it is expected, is the severity or duration beyond that which was expected? And at least that adds a little bit of a frame of reference to it.
That's a good point. Oftentimes when we're taking a look at, even for reporting to FDA, certain types of events, things they're most interested in are the unexpected events. If you've got expected ones, okay, well, everyone knows that, you know, ibuprofen is going to cause stomach upset, and, you know, non-steroidal anti-inflammatories cause those kind of effects. But if you've got somebody that's serious and unexpected, those are the ones that you focus your time and energy on.
My question is for you, Richard. The NESC, which stands for NASA Engineering and Safety Center, has shown that if you look at information about when pilots have saved the day, it's very valuable toward keeping things safe. And so in the, what do we call it, the health, space health reporting system, we want to also collect positive things that happen when people go into space. Have you ever seen a system that does that? Because they're typically referred to as adverse event.
Kind of depends on the interaction that you have. I mean, a lot of times we have, in our staff, we have like over 300 clinicians that are managing these adverse events. And you get tangential information when you're talking to people. You know, they may think that they had something going on, but then they say, oh, by the way, for some reason, my memory is great, you know, or they have some other type of situation that they report that goes into your big picture, and you're looking for those types of trends as well. So you need to probably have other compatible ways of collecting the positive experiences, because, you know, everything is a risk benefit in life. So you got to, when you're trying to, you know, characterize risk, it's always in the context of benefit. So it's going to be really important that you talk about the benefits of space travel, because that helps people accept the risk that's associated with it.
The FAA and the military do some collection of this, and there is data that I show in other talks that looks at how often do near misses happen in commercial airlines and other things like that that are caught by the pilots, and it's a pretty significant thing. Human systems integration experts like to say humans bring safety, right? And then engineers like to say, oh, it was human error or something like that. It's not a tried and true thing like that, but it is at some point in the process, whether it was a pilot making a mistake, a pilot fixing something happened in the machine maybe, and if that was something that happened, somebody designed it, or something failed on a manufacturing line, or something like that, right? So it's actually humans all up and down the train here. It's pretty rare that it's like not some aspect of human intervention that does something. It might be something we've forgotten about, or we don't want to attribute it to, but this is why I think human systems integration is such a big deal. It's up and down the chain.
Just to add back to the terrestrial application, so at the heart of every quality improvement program or quality program in every health system is an incident reporting system, adverse event reporting system. It's kind of foundational, and that's kind of expected from you know, compliance on down. But some do it better than others. And, you know, inferring causality, I mean, what happens is some event that falls outside of some normal variability, and somebody decides that meets criteria for root cause analysis, which really should be a contributing factor analysis, because there's never any one cause. And my experience is there's just variability in terms of the quality of the quality program. Why do I bring it up? Because this is really relevant. This is extremely valuable, in my opinion, to terrestrial-based healthcare organizations. The way you all understand and can analyze this longitudinal data and picking patterns and finding these needles in haystacks and saying, yeah, well, don't worry about that, you know, but that one over there, that's really important. We've got to focus on that. I just think they could benefit by experience.
One more, so go ahead.
Yeah, okay, 1 minute 35, that's easy. We can, clock's running. So I was thinking about, in our astronaut studies, we've got data that suggests, and correct me if I'm wrong, that your medical selection takes you out to about 40 days into the mission, roughly, maybe 50 days, till you can start to have noise. So selection and medical and all the stuff we do takes us about that. Now you can.
That is a very wishy-washy number, but what I will say is that the analysis is published, peer-reviewed, and there's a lot of uncertainty around that. If you asked me to pin it down, I'd say somewhere between 40 to 180 days.
Fair enough. Yeah, so that's good. So, but that's with pretty highly selected trained folks. Now do commercial longer duration flights, so that gets even noisier, right? And then the last thought is, we're using astronauts that have pretty strong intrinsic reward systems and extrinsic reward systems to keep them from going off the shoulder of the road. That's going to be less true with commercial stuff, and we've already seen some challenges in that. So we have to be careful about how we design our reward structures also for commercial space flights, indirectly and directly, psychologically as well as systemically.
Just wait until they try to do the first Ultimate Fighting Championship on one of these commercial space stations. I mean, this is the type of stuff that's going to sell the tickets, right?
Okay, thank you so much to all of our panelists and everyone for their feedback on track 3. Again, if you have more feedback, the form is on the website, so feel free to send along any other thoughts you have.
Thanks for coming.
Hello? Yep. It's my honor to introduce Dr. George Neild, who is going to tell us about his recommendations, his and his team's recommendations for implementing the HRP-C nationally and internationally.
So we're going to start with the international, and we are very fortunate to have some comments by Simonetta De Pippo, who is a rock star in the international space community, and she is currently a professor at an Italy university, and she has had very high-level positions in the Italian Space Agency, the European Space Agency, and served as the director of the United Nations Office of Outer Space Affairs. So I'd like to hear from her comments as soon as we can get the recording rolling.
Good morning, good afternoon, and good evening, everyone. It's really a pleasure for me to be here with you today after 2 very interesting days of exchanges and conversations with ideas in proposals expressed by a lot of top-level experts around the world. Now, it's really a pleasure, as I was saying, for me to be here to provide some strategic considerations and some concluding remarks. Before I enter a little bit more into the subject matter, I would like to briefly introduce myself. Currently, I am Professor of Practice of Space Economy at the SDA Bocconi School of Management, and I'm also Director of the Space Economy Evolution Lab there. I'm former Director of the Office for Outer Space Affairs at the United Nations, and also former Director of Human Spaceflight at the European Space Agency. Currently, I'm also involved in the World Economic Forum Global Future Council on Space, where we deal with a lot of different topics. I have to say that it's really interesting for me to, first of all, provide some statistics. And here I'm referring to something which has been published by the Space Foundation. These few elements of this publication have been collected into an article published on astronomy.com. So, referring to the 7th of November 2023, Space Foundation counts for 676 human beings who had the journey to space in line with the US definition of an altitude of 50 miles, which means more or less 80 kilometers. 643 have reached the Kármán line, internationally recognized at 100 kilometers, so 62 miles. Government astronauts typically fly several times over their careers, but we also witness government astronauts right now retiring from the government itself, so from the space agencies, and they're becoming space travelers, private space travelers. And so we have few examples of them. In particular, there are few who flew already a lot with NASA as government astronauts, and now they're flying with some private commercial companies a few times already. In the last 3 years, 69 private astronauts reached space for the first time. Still, we are considering statistics at the date of the 7th of November 2023, because, counting and counting, as we say. And 46 of these 69 were above the Karman line, and 23 above the US definition of space. There have been a few isolated spaceflight participants before, but we will see what is happening right now, and in particular, how this, let's say, trend has been developing or blooming, if you want, very recently. This is a map of our globe, still is related to the end of last year. So it's not taking care of the latest developments, and so few countries are not mentioned yet. However, at that date, the 7th of November, so when we are referring the statistics to, we counted 43 different nationalities, mostly still being, mostly of the astronauts still being coming from Russian Federation and the United States of America. But, we also see, also in this case, the fact that the number of countries involved in human spaceflight, thanks to these private commercial flights, is also increasing. And in particular, I would like to mention the last Axiom 3 mission, which lifted off from the Kennedy Space Center from the historical launch part of 39A with the Falcon 9 and Crew Dragon Freedom. This mission had on board 4 private astronauts, 4 different nationalities, even if on the mission patch you will find 5 different flags. Reason being that the commander of the mission, Michael Lopez Alegria, is bearing both Spanish and US flags. And then you have an Italian, a Swedish, and a Turkish. And so Turkey, for the first time, is flying into space right now. They lifted off the 18th of January, as I just said. So they're currently on the International Space Station. The flight was nominal. And the Italian participant also had quite a good technical role, because he is Villadei. He is fully trained in Star City and all the main centers around the world where astronauts train, and in particular is also qualified to do extravehicular activities. So in reality, as you can see, there is a mix of rookies, but also very experienced astronauts like Mike L.A., and also different nationalities on the same flight. Also, as I mentioned before, we have to consider that these flights really, suborbital flights in particular, but also private missions to the International Space Station are quite recent. In particular, I would like to mention the first flight of Unity, a Virgin Galactic with Sir Richard Branson on board, and the first flight of Blue Origin, and these both suborbital flights, and again also with Jeff Bezos on board. And both flights took, they lifted off and took place in July 2021. So bottom line is more or less 2.5 years that we started this new adventure. And I will say the number of flights that both companies have been performing quite successfully until now, even if, there are always technical issues, but this is part of the game, as we know, is still, counting for the new, the upcoming missions. And so we are really keen to see what is going to happen soon. So just to demonstrate that in reality, there have been a certain number of attempts in the past and everything successful. But in reality, what we are experiencing right now is really the fact that this sector, so suborbital flights, with people who never had the possibility to fly before, with no training or just a little bit of training, they're really able to fly and to enjoy, suborbital flights for the time being. Well, we may say what we have to do from now onwards, how we have to act all together on an international basis, considering that the number of nationalities that we are counting, as I said, is already more than 43, because as I said, 43 was referred to last November. And therefore, what we have to do, what we can do in order to improve our knowledge, how we can share information among all the participants, how we can benefit from the flights that are taking place during these very days in order to prepare for an increasing number of people who really want to enjoy going to space. So this is not a minor issue, and we have to think about that. And the sooner we do that, the better it is. So what I would like to do is really to make some examples of potential, let's say, tools or even frameworks that we could use, or we could start thinking about using them to improve the exchange of information that we do need in order to better understand how to prepare for a massive presence of human beings to work and live in space in the very near future. So it's not only an issue, not a question related to suborbital flights, but it's also related to human outposts on the moon and beyond. So I'm thinking about private and commercial space stations in low Earth orbit. I'm thinking about the moon, but frankly, I'm also thinking beyond, because when we will start this systematic solar system exploration, which will be both human and robotic, well, for sure, we will have government astronauts, but also plenty of private commercial astronauts. So one of the places and one of the platforms that I would like to suggest you to think, to think about, just to see if it can be the platform for further discussions, for improving also the exchange of information that we may have around the world. And it's the UN, so the United Nations. This in particular is a picture of the Vienna International Center based in Vienna, Austria, where also the Office for Outer Space Affairs is located. The Office for Outer Space Affairs, as you know, together with the Committee on the Peaceful Uses of Outer Space, have the role of facilitating discussions among member states. You have to consider that currently the member states, the number of member states which are members of the Committee on the Peaceful Uses of Outer Space went above 100. So during my tenure, this was in the period March 2014, March 2022, so 8 full years, we had an increase of more than 32% in terms of number of member states, which for the first time entered into this family, this is space family, which is the Committee on the Peaceful Uses of Outer Space, because the platform is really good for exchanging views, for facilitating also bilateral, trilateral collaborations, and in order also to discuss global governance and how to cooperate for also the exploration of the solar system have been really topics deeply debated. And by the way, one of the things is that in Vienna, what is applied is the so-called Vienna spirit. The Vienna spirit means that all the discussions are conducted extensively up to the point that the final decision must be taken by consensus. So there is no voting procedure in Vienna, unlike what happens in New York, which means that every single document is approved, and so there is consensus by all member states, more than 100, as I already mentioned, word by word. And this is, for sure, a long process, but at the same time, it's also, a sign for profound commitment from the member states which approve the given document. It's also a place where the Committee on the Peaceful Uses of Outer Space is also used to create some working groups of experts on different topics. And this may be also something that you may want to think about, because it may be in the future also something to eventually propose in the field we are debating here at this workshop. And in fact, this is a typical meeting of the Committee on the Peaceful Uses of Outer Space. I have to admit, this is I like it a lot, but it's an old picture. We have plenty of them. Reason being, then, when the member states reached the point of more than 100, this meeting room, which has been the historical meeting room for the Committee on the Peaceful Uses of Outer Space, was not sufficient anymore space-wise. And so we had to move to another big meeting room in order to be able to host all the participants. And this is quite a good sign. In any case, this has been the historical boardroom D, which was in Vienna, the room which was hosting all the discussions around, governance, global governance, and the way, really, which way we have to find all together in order to improve relationships in a multilateral environment. Another example that I would like to mention, which is also a good platform, is the Association of Space Explorers. The Association of Space Explorers is encompassing all the individuals who flew into space. So, quite a huge number. The Association of Space Explorers, they do a lot of events. They meet every year or together in order to discuss the future of space activities, but also to do a lot of, communication and trying to increase also the general public awareness about the importance of space activities. The Association of Space Explorers, among other things, they are also permanent observers at the Committee on the Peaceful Uses of Outer Space. You have to follow a certain process to do so, and they did it. And so they made, from time to time, they make very interesting suggestions or proposals. One of that, among all the proposals they've been making, one I took it as an example. It is the fact that they proposed to declare the 30th of June the International Asteroid Day. UN declared International Asteroid Day. Why the 30th of June is because it was the day of the Tunguska event, which is probably the most important event related to an asteroid, a sort of interaction between an asteroid and our planet in the recorded history. And so now this important day is recognized by a lot of different organizations around the world. And, the main goal is really to increase awareness. Now, the point is that also the Association for Space Explorers may be a platform for discussing the topic that we have at stake here. Also because, for example, they may be interested, and we could check if you like so, they could be interested in sharing on a voluntary basis some information, some experiences, the knowledge they have since they've been flying, and few of them or several of them several times in space, and also for very long periods of time. And so they could share with us, some information, as I said, on a voluntary basis, which could improve and increase our knowledge of what can happen when we start flying back and forth so frequently and with a so high number of individuals. So this is, again, another example that I wanted to offer you for further reflection for the future. Last but not least, this has nothing to do with the topic we are discussing here. However, is a very good platform, or at least a very good example and tool, which could be replicated in different fields. This specific case, this is an activity put together by the World Economic Forum, in particular the Global Future Council on Space. What we did was to put together what is called the Space Sustainability Rating. And also this is really a system which is based on a voluntary, on a voluntary basis approach. So companies which want to demonstrate that they're really in line, that they are committed to maintain a safe, secure, and sustainable outer space. And so therefore their activities will be safe, secure, and sustainable. Well, they voluntarily subscribe in a way, and they voluntarily share their experiences, their knowledge, but also they try to demonstrate that they are really committed to fulfill the requirements, in particular in line with the, in this case, if we talk about space debris, for example, is the international Space Debris Mitigation Guidelines, approved back in 2007, and then the 21 long-term sustainability guidelines of outer space activities, which have been approved by the Committee on the Peaceful Uses of Outer Space back in June 2019. So, in reality, as I said, is a voluntary process. But clearly you need a database, you need people working on it. And so the World Economic Forum then, after it was shaped internally, then what we did was to make a call, and it's currently this database and this system located in Switzerland, which is in a place where there's an institute which won the competition, and so they are hosting this rating, this system, and it's mentioned several times here and there. So it's a bottom-up approach. It's a bottom-up system. It's a tool. But again, what I want to underline is the fact that this is voluntary. So the first one that I was mentioning, the Office for Outer Space Affairs, the Committee on the Peaceful Uses of Outer Space, yes, it's voluntary, but it's a multilateral system where you have the only or main stakeholders are the member states. So the UN is, by the way, a member states-driven organization. While the other two I've been mentioning, so the Association of Space Explorers and the World Economic Forum, and in particular the Space Sustainability Rating, are two bottom-up systems. So group of individuals, organizations, NGOs work together in order to raise the issue, or to put the issue on the table, and trying to increase awareness, to raise awareness, to raise the issue, and therefore increase awareness about the fact that there is a need for all the stakeholders involved and interested to work together. So clearly, there are a lot of points that we could discuss here, and I don't want to, to go too long with this discussion. What I have here, I have collected a certain number of pins that, if you want to fly with one of the companies which are currently, going to space, well, you see, you may go from 1 to 10, 1 to 10 is the highest, 10 is the lowest. So 10 is the highest, 1 to 10 is the lowest. So you may go from upper left, and you see that's the pin that you will get from SpaceX, or the one bottom left are the two pins that you can get from the Association of Space Explorers, one for suborbital and the other one for orbital flights, or the wings that you can get if you have been traveling as a commercial astronaut from FAA, or the NASA pins before and after your flight, etc., etc. So just to say that it's now once, when you have the system that is really also blooming, as I said before, well, also the number of pins, which at the very beginning was one, right? Only the NASA one, now is really going ahead with several pins, and is also a sign of how broad is the field and what is happening right now. So just to conclude, I would like to say that for sure, when we will start, and we're ready to go, we, humanity, at a global level, when we will start a systematic solar system exploration, so we will go on other celestial bodies like the moon, Mars, and beyond. That this is a rendering of a potential city on Mars. Well, for sure, we will be there. We will have to travel. Traveling to low Earth orbit, to the moon or to Mars will be different. We know well that there are a lot of different requirements, a lot of different issues, and we the community, we are working on that. But all these elements have to be considered, in particular for the well-being of the humans, which will go back and forth, or we stay for long periods of time on another celestial body, or in low Earth orbit on commercial space stations, which means that we do need to collect information. We are here also to listen to your suggestions, to your ideas, to your comments, to your proposals, and with that, I pass the floor to my good friend George Neild for other considerations, and eventually also for discussing with the audience what I just said in terms of comments and proposals, because we do need to have a shared vision on how we want to proceed. And thank you very much for your attention. It's been a pleasure to be with you.
Okay, if you could put up the slides for my presentation, please. I want to thank Professor DePippo for her comments. She is very supportive of our effort and is looking forward to supporting us in the future as we talk about implementation. That was my task, to lead a subcommittee on taking all this great information and ideas that we've come up with for the last 2 days with respect to the draft report, and try to figure out, what are we going to do with it? What happens tomorrow and going forward? So at the end of 2 days here, now, as we talk about that, I'd first like to step back just a little bit and remember, how did we get to this point, and why, and where are we headed? So let's see if we could do that. Ever since the Soviet Union launched Yuri Gagarin into space more than 50 years ago, almost everything that has happened in space of an historic or major achievement nature has been done by governments. Whether we're talking about the X-15 program, Project Mercury, Project Gemini, the Apollo moon landings, 30 years of flying the space shuttle, or building and living and working on board the International Space Station, it's been governments who have been responsible for planning, conducting, and carrying out those programs. In my opinion, going forward, that is not necessarily going to be the case, because private industry is playing a very important role. And why is that? I think we're learning now that, properly done, the increased involvement of industry can mean lower costs as compared to a government program doing the same kinds of things. It can mean increased innovation. As a former government employee, certainly, I would say that once the government learns how to do something, we like to keep doing it that way because we think it works. I think industry can bring a greater risk tolerance. Once again, government is historically very risk averse, which has its advantages, but it also can prevent innovation. Industry can bring new opportunities for different products, markets, services, and customers. That's not government's job, but that's what business is all about. And industry can also bring new sources of funding and investment so that we don't have to rely solely on congressional appropriations and taxpayer dollars. So how's that working? Well, here's a chart of FAA licensed launches per calendar year. The first FAA license launch was back in 1989, and for a number of years, we had a handful every year. And then 8 years ago, it started increasing exponentially. Last year, there were 117 FAA licensed commercial launches, and there is no sign that that is turning around or even leveling off. Spaceports. There are currently 14 FAA licensed spaceports in the United States. So those are the ones shown in blue on the map. And there's another dozen waiting in the wings, shown in the left-hand part of the chart there. Of course, there are also government-owned and operated sites and some private sites. But that number continues to increase, and it's not just in the United States. We see dozens of locations around the world where we are currently launching rockets or they have plans to do so in the future. Everyone's familiar with the global space economy. Space Foundation estimates we're now at $546 billion per year. And an interesting point about that is that government spending is only a small fraction of that pie. So, for example, U.S. government space budgets is the gray slice. Non-U.S. government spending is the yellow slice. That's less than a quarter of the total. The other 3/4 is commercial, whether it's infrastructure, space products and services, and so forth. That's pretty amazing. And if you talk to the economists and financial experts, there's a pretty strong consensus right now that by 2040, say, that global space economy is going to exceed $1 trillion or more. How about when it comes to human space flights? Well, human space flights from the United States, just since July of 2021, if you look at the flights conducted for government customers, NASA, we had 5 flights to the International Space Station that were carried out by SpaceX with the Falcon 9 and Dragon. Grand total of 20 people, either from NASA or our international partners. During that same time period, there have been 17 human space flights by the United States for non-government customers. We had the Inspiration 4 mission, 3 flights for Axiom customers, 7 flights for Virgin Galactic, 6 flights for Blue Origin with the New Shepard program, and those flights carried 90 people to space just since July of 2021. And those numbers are to continue to exhibit that trend, in my opinion, especially once the International Space Station is retired and we have multiple, probably, commercial space stations in low Earth orbit. And so, interestingly, NASA has a lot of data on how spaceflight affects human beings, and with the exceptions shared by J.D. Polk, for the most part, those people have been at least selected to be rather young and in excellent health and outstanding physical condition. How about recent commercial flights? Well, We had Wally Funk fly, and she became the oldest person ever to fly to space at age 82. But her record only lasted a few months because shortly thereafter, William Shatner flew, Captain Kirk from Star Trek, at age 90. Haley Arsenault flew on Inspiration 4. She's a childhood cancer survivor. We recently had John Goodwin, age 80, flew on Virgin Galactic, and he had already been diagnosed with Parkinson's. I don't see any of those people as being allowed to fly by NASA. And in fact, I think they're more representative of what we're going to see in the future in terms of people who are living, working, or traveling to and from space. So that brings up a challenge and an opportunity, right? Future flyers are going to be older, with a variety of existing health conditions, and be less fit than their NASA counterparts. That's what HRP-C is all about. Can we gather the data to help those people understand the training, the treatments, the medications, the countermeasures that will allow them to fly safely and perform successfully? So the subcommittee on implementation gathered, recognizing the great work that the rest of the group had been putting in to come up with a draft report, and started asking a lot of questions. Who's going to oversee this? Who's going to fund it? What kinds of activities are we talking about, and who would the test subjects be? So lots of questions, talked about that for a while, but we really focused on what kind of possible scenarios could be used in order to implement a program of the kind that we're talking about here. And there's an infinite number of ways, and there's not just one right answer, right? Almost any of these could work and could work successfully, but we decided to focus on several different options to at least narrow our thinking as we talk about what the future looks like. You can keep doing exactly what we've been doing, right? The status quo. You could have a government program, maybe bigger, maybe better funded. You could have a public-private partnership, or you could have a non-government program. And of course, it's not black and white. There's a lot of fuzziness in between those options, but just for discussion's sake, let's go through each of those briefly and give you a sense for our thinking as we analyze those particular options. The status quo. Some research is already being done. Fantastic. It's being conducted, some by industry, some by NASA, some by academia. Individual companies can certainly choose to have the people fly on their missions, carry out some of the research objectives. A university somehow could obtain access to the data and do some good analysis on it. Heard excellent presentations by Trish on what they're doing. They have access to some data from some flights. Advantages. Oh, don't need a new organization. Don't need any new federal funding. Everything's good. On the downside, the research program is probably going to be slow, and there's a high risk of duplication and inefficiency because there's no comprehensive grand plan to look at where are the gaps, where's the duplication. Are we doing things smartly with the data that we've gotten? Okay, how about a government program? Absolutely, NASA could do this. FAA, CAMI, Commerce could do it. How about NSF or NIH? There's a lot of different government organizations who have an interest in this or have experience doing it. The NASA Human Research Program is an example of a kind of a program that is a government program, right? FAA had a Center of Excellence for a number of years that did some things that CAMI was heavily involved in related to human performance and so forth. Advantage of that, if we can get some substantial federal funding, that has a lot of benefits. You can do more with more money, and also substantial federal funding could encourage widespread industry participation. If they see that, yes, this is important, it's credible, there's a possibility of getting reimbursed or paid for some of the work that they might carry out. Disadvantages, given the world we live in today and the budget deficits, it's pretty tough to get approval for new government programs right now. And even if you do get some, government programs typically come with a number of constraints, limitations on what you're allowed to do, who you can do it with, where U.S. taxpayer dollars can go, and typically government programs can be rather slow and can be tough to respond to changes. How about a public-private partnership? For example, you could have an FFRDC, a federally funded research and development center like Aerospace Corporation or MITRE. You could have a new FFRDC, although again, that has to be approved by Congress. You could have something that the FAA was looking at and recommending a few years back, a commercial spaceflight research alliance that would be funded by NASA or by FAA or some other government department. TRISH really is sort of a public-private partnership in a way, and at least originally was focused on solving the challenges of human deep space exploration. And in 2016, they were given a 12-year cooperative agreement by NASA with a total value of $245 million. So again, if you average that over 12 years, about $20 million a year to do what they've been given. And they've said, yeah, we're doing good, and we heard all about that from Jen Fogarty, but more money would help, right? Well, that's how much they have. Advantages, congressional approval for a partnership might be easier than a strictly new government program. And again, federal funding is going to encourage industry to play. Those are pluses. At the same time, it's not a guarantee that Congress would approve an FFRDC or to give more funding to an existing one. And if we don't have money right away, it's going to be a while before we can start doing anything, and that's not ideal. In addition, if we're having to wait for federal dollars to come along, it may be difficult to get widespread industry participation if they think this is all coming at their own expense. How about a non-government program? You could have a program that's managed by a university or other academic institution. You could have an existing nonprofit organization. There's several others out there who might be interested, or you could create a new one specifically for this purpose. Examples, several years ago, UTMB and Virgin Galactic did a study with a centrifuge at the NASTAR Center that we've heard about several times. And I think that was really something that opened people's eyes that, gosh, there's a wide variety of people who can, if not thrive, at least be comfortable going through a similar profile as to what we see on some of these suborbital flights. And so that got people's attention. You don't have to be a perfect, young, healthy individual in order to survive at least some of these suborbital flights. So advantages, you don't need congressional approval. And in fact, if you want to just start with a sort of a bottoms-up approach, whoever thinks this is important and they want to play, if they can provide some funding for what they contribute, we could start tomorrow. And that would allow us to at least get started and make some progress while we're talking to governments and other sources of funding. If you're not completely reliant on the government, the program could be, at least in theory, faster moving, more innovative, more collaborative, and it wouldn't be directly tied to the congressional schedules and appropriations and so forth. On the other side, it may take a while before we get that set of grants from the federal government. And so at least at the beginning, it would be reliant on grants from foundations or philanthropic individuals and investors and so forth. And it's going to be probably more of a challenge to get the industry providers to start playing if there's no guarantee of those federal dollars coming. So that's just an overview of some of the options we looked at and talked about. Again, I think any of those systems could work, and if we were to get a lot of federal dollars and NASA and FAA were told, go make this happen, fantastic, let's do it. If that's not going to happen, then maybe we can look at some of the other options, and that's what we tried to do. So the recommendation from the implementation subcommittee goes like this. We think we ought to have an HRP-C that's a nonprofit, a non-governmental organization, a 501c3, as we refer to it, and the basic principles would be all interested parties from government, industry, and academia are welcomed and encouraged to participate. It would be focused on research and data sharing, not regulations. Collaborative in nature, international in scope. Oklahoma State University has really stepped forward and recognized the value of what we're talking about, and the perfect example of that is this very workshop. They have raised their hand to volunteer to take on some of the functions that would be required for a program like this. For example, serving as the central hub for communication and collaboration across the program, exactly what we're talking about these past 2 days. Managing a human spaceflight data repository. Developing and maintaining a space health reporting system database. That's that adverse event type system that it was mentioned earlier. But if you look at the track 3 tasks that were discussed earlier, there's a number of different things that need to be done. And so we're not talking about putting all of the functions in one place, in one organization. We need help with who's going to be the IRB, who's going to do precision medicine, who's our expert for civilian training, how about food nutrition and metabolism. There's lots of pieces of this, and they don't have to all reside in one place. Here is an example of what an organizational structure could look like. Just to be open-minded and maybe strategic in terms of how could we make the maximum benefit of this type of an organization. We put, again, an arbitrary name for it, Commercial Spaceflight Research Alliance. It's a 501c3 at the top, and it could receive, hopefully, government grants, grants from foundations, funding from investors, donors, benefactors. And it could deal with a variety of different commercial spaceflight subject areas, like vehicle research and technologies, mission operations research, spaceport research, policy and market research. Those are all important, and NASA and DoD are not doing that. They're doing other kinds of important things for space. Those are the kinds of things that were part of the Center of Excellence that the FAA had before that timed out a few years back. What we're talking about here, though, is the center one, human spaceflight research, basically the HRP-C. We'd want to have a board of directors, we'd want to have staff, including scientific experts, medical experts, finance and business people. You'd want to have an advisory board, lead scientists, and then you'd have some members. And the members would include industry, universities, associations, even individuals. Why not? This is an example. It's not the final answer. Who are some of those potential members? Commercial spaceflight companies, government space agencies, universities, insurance companies, pharma, health, life science companies, venture capital, industry associations, individuals, lots of possible folks who have something to contribute to this effort. So where do we go from here? My opinion, if we say, boy, that was a fun and interesting conference, and we all go home, and we put the reports on the shelf, and maybe we meet again in a year or two, that would be a huge missed opportunity. The timing is right to actually do something. So what would we do? I think the first step is to determine the interest in participating from workshop participants and other stakeholders. If we were to head out on the road to put together something like this, that yes, NASA could play, Trish could play, Oklahoma State University can play, other places can play, SpaceX, Blue Origin, Virgin Galactic, yes, yes, yes. What would you like to contribute? What would you like to get back? Simultaneously, we'd want to start engaging with potential donors, investors, and benefactors. We've already started having some discussions. There's a lot of interest. The space is just so exciting, and here's a chance to make a difference because it's not happening on a comprehensive and broad and collaborative scale today. And then, go ahead, yes, pursue government grants. What would that take? What would that look like? But recognize that'll probably take a while, even if we're successful, which is not guaranteed. So, my suggestion is that you think about what we've talked about here these last 2 days, and especially how do we actually implement something. And as you know, the website has this nice feedback form to recommend inserting a sentence here in paragraph 3 and changing this word to that and so forth. There's also a big block of comments. If you want to play in this, please write a note or contact Jamie Jacob from OSU, our host here. He's going to be the, at least interim focal point for this to collect feedback and people who say, yeah, we think that's great. We want to play. We don't know exactly what that looks like, but I saw some of those areas on that, and we have something to contribute there. So let's keep talking. We need to know that. How many people and from what organizations, with what talents, what products, what services, what capabilities would potentially like to play in a program like that? So if you would please provide that feedback to us, then hopefully we can get started, and this can be the beginning of a very exciting initiative. Thank you very much.
Okay, we're going to wrap up now. First, we're going to hear from Mike Marge, who is the person who instigated this entire thing. And I guess, Mike, you would just turn off your...
I'm available. Can you hear me now?
No, can't hear you.
You can't hear me? My sound is on. Can you hear me now?
Don't hear you. It doesn't indicate that he's...
Can you hear me?
Yes.
Okay, good. Well, I hope that all of you agree with me that this has been a splendid, innovative, and informative workshop. I applaud all the speakers, the presenters, and all the participants for your excellent comments and recommendations. Thank you so very much. We need your input for several reasons, and one is that we want to improve and to refine the HRP-C.
Very long.
Can you hear me?
Yes.
Oh, good. The second item is that we want your consensus, your interest and participation in this concept, as George beautifully pointed out in his discussion, George Neal, that this should not be a document that sits on a shelf and collects dust. This is the time for us to move forward and to implement this program, this human research program, for the benefit of all humanity. Now, I want to say that during the 2 days of the workshop, you must realize that we're talking not about a static workshop proposal. I mean, human research proposal. We're actually talking about something that is dynamic, because there will be new discoveries and new developments in time. So therefore, what we're talking about today, frankly, is the best knowledge we have currently about a comprehensive program, the elements of a comprehensive program that should really be put in place as soon as possible. And whether we like it or not, the industry is going to move ahead. The providers will start sending civilians into space even before we have answers about how to counteract some of the space hazards that individuals will be facing as they go into space. I must admit that those of us in the field of health are somewhat disappointed about that rush, because we've taken an oath which says, do no harm. And I'm afraid that even though individuals or civilians who wish to go into space are willing to take the risk, it becomes a concern from a health perspective, those of us who are working in trying to make space as safe and as healthy as possible. But anyway, we will continue with the HRP-C to reduce the risks to the greatest degree possible for all humans in future space. And I should point out that the editors of the report of this meeting, as well as the HRP-C refinement, including the incorporation of your excellent suggestions and recommendations, are Dr. Tina Baird, Dr. Schmidt, and myself. And we will develop a report and incorporate those relevant and significant recommendations. When we're completed, we will send you the link where you can get a copy of the report, where it may be accessed. Again, thank you for your interest and participation as partners for a better future in space.
Thank you, Dr. March.
I'd like to second Michael's comments and thank everybody for their participation over the last 2 days. We've been honored to have you here and to host you. We hope you have enjoyed your time here and learned a lot from all the great presentations that we had. If you have any additional recommendations or suggestions for following up, obviously additional comment on the report, we'll still be taking input from that, so that way we can parse that and be able to provide that input directly into the report, as well as any additional comments about the event. We will be posting the presentations as well as the videos online, so we'll follow up in emails in regards to that as we get all those parsed. I know we've gone over today, so I want to make sure that we're mindful of your time. We've already taken a lot of your time over the last couple of days. We also have a class that's going to be coming in here very shortly. So we'll go ahead and convene this session. There's still space outside, as well as some additional snacks to continue great discussions. So thanks again. Safe travels. If any of you are participating in the CAMI event tomorrow, Dr. Antunana will be happy to chat with you more about those details. Thank you.
I'm Audrey Florum Smith to everyone. Thank you for an absolutely informative and inspiring workshop.
Who was he, the guy that spoke?
Who's